Good morning, everyone. I believe that you enjoyed last night as well as a daytime meeting, but it seems some are still enjoying it, even right now because we have a limited numbers. But I hope that others will soon come. Okay, today he already mentioned that we have a 3 session, but for the first session we will have 7 talks, including 3 invited speakers. And of course, our session is a field experiment and the multi-platform measurement of precipitation over monsoon region. First speaker is invited speaker from the WCRP, Dr. Hindmasi Palamisamy. And her present title is GPEX, WCRP's Global Precipitation Experiment. Okay, time is yours.
I'm going to keep it. Okay, perfect. Thank you. Good morning, everyone. I see that many are still maybe in the sleeping mode. We're not many here today, but that's okay for me. So I'm Hindumati Palnisamy from the World Climate Research Program Secretariat, and I'm the science coordinator for the Global Precipitation Experiment. So this presentation is going to be a very brief programmatic overview of GPEX, because GPEX is relatively a very new activity in WCRP. It began a little more than a year ago. So the scientific activities are just spinning up. The leadership is in place, and they met just a few months ago, and we have identified some science objectives. I would like to thank Annalisa and Jeff, the 2 co-chairs of GPEX, and the entire GPEX science leadership. So before I delve into the global precipitation experiment, a very brief overview on the World Climate Research Program. So many of you here are already aware. So it's been more than 40 years that WCRP is in existence and has been coordinating and facilitating international climate science research to be able to develop, share the climate knowledge to the well-being of the society. It is a co-sponsored program, co-sponsored by the World Meteorological Organization, UNESCO's Intergovernmental Oceanographic Commission, and the International Science Council. Around 2018 and 19, WCRP revisited its science strategic plan to ensure that the scientific objectives are up to date with respect to the needs of the society. As a part of this science plan, it has identified various overarching science topics, science priority topics that you see here. And these topics, for instance, cover the basic of climate research, advancing, which used to be one of the objectives and still is. The observational modeling aspects, process understanding, extremes, and also you will see there is now the climate information, making sure that the climate knowledge reaches out to the society. So the motivation for the global precipitation experiment within WCRP, since several decades, there have been lots of advancements with respect to precipitation science. However, we still face challenges in terms of the process understanding, data, in situ satellite measurements, etc., when it comes to prediction and projection skills, especially with respect to extreme events like floods, droughts. So to be able to address these, back in 2020, several United States agencies under the United States Global Climate Research Program, Global Change Research Program, they explored the concept of bringing in an international initiative, coordinated initiative for global precipitation experiment. So this was discussed with the WCRP, and they revisited the science plans and ensured that different aspects of precipitation, they are within the overarching science objectives that WCRP wishes to address. You will find precipitation, in the basic understanding of climate science, observational modeling issues, and also when it comes to extremes. So there were various aspects that had precipitation already in place. So they decided that this should be something that WCRP should take on. And a science team was then created that came up with a science plan for the global precipitation experiment. So this was approved in 2023, following which GPEX was launched as a WCRP LIDARS activity. So what exactly is a WCRP LIDARS activity? So these are short-term, 8 to 10 years maximum, projects that aim at addressing priority science questions. The criteria is that it needs to be transdisciplinary in nature, and also making sure that it integrates various WCRP activities. So it has to integrate the core activities that address the various components of the Earth system science: atmosphere, cryosphere, ocean, hydrology, and also bringing together the modeling and observational aspects. And then the last objective of climate science, reaching out to the society. So if you take a look at precipitation, it fulfills all of these, and it is also cross-cutting across all of WCRP activities. So it is rightly a LIDARS activity, and this was launched in 2023. So the aim is to take on challenges to improve precipitation predictions around the world, also including complex terrain and also the polar regions. So moving into the aspect of GPEX and its science. As a part of the science plan, there were 4 scientific questions identified. So I will talk about these 4 questions right after. And these 4 questions will be addressing 4 specific activities, 4 specific precipitation drivers: atmospheric rivers, mesoscale convective systems, tropical cyclones, and monsoons precipitation, using various tools such as satellite measurements, ground-based measurements, in situ data, radar, etc., models, and also machine learning, AI-based tools. And the last part would be the capacity development, focusing on vulnerable regions. So what are the science questions? So the first one would be identifying sources and the magnitude of uncertainties that we see in precipitation-based data sets. So yes, we have made advancement in terms of satellite-based measurements, but we still have challenges to face when it comes to measurements in the tropics and also in the open ocean, where the surface measurements for precipitation is still very sparse. And also the complex terrain regions, high altitude regions, etc. So one of the scientific goals would be to identify the sources and the magnitude of these uncertainties in these vulnerable regions. The other one is the process understanding. So how is precipitation produced by complex moist processes, and also its interaction with respect to the various Earth system components. And the third one is addressing model biases, especially in climate models, and our efforts to reduce these biases to be able to improve the prediction and projection capability, especially when it comes to extreme events such as floods and droughts. And the last aspect is regional and local capacity building. How do we ensure the precipitation database is equally shared with resource-challenged regions, and also making sure that this science faces a bottom-up approach. We need to know the needs of the local area through the med services, and how GPEX can internationally coordinate these things. How do we implement the science plan, the science questions? It is highly ambitious, and our motivation is not to reproduce what is already being done, because we acknowledge that precipitation is a subject that is being handled and done by various other institutions internationally. So our aim is to make sure we provide this opportunity of international coordination of such activities. So WCRP came up with the years of precipitation, which will last around 8 to 10 years, the same timeline as the Lighthouse activity, with a core of 2 to 3 years in between that will bring around all of these 4 focus questions together. And there would be a pre-YOP phase where we connect with international agencies, national funding bodies that are already planning for field campaigns, bring them together, work on these field campaigns, and the core years of precipitation, and the post phase where all of these results will be shared as scientific outcomes and also in terms of community needs. How do we make this happen within the Lighthouse activity of GPEX? So we have 4 working groups that will address each of these scientific questions, or in several cases, the interconnection between these 4 scientific questions. I'm going to briefly talk about each of these 4 working groups and where they are at the moment in terms of the scientific activities. So the first working group is also a part of the pre-years of precipitation, and this working group has just begun its activities. So what it basically does is coordinating global field campaigns that involve in situ, satellite-based measurements, airborne satellite-based measurements of the 4 precipitation drivers. So their ideal goal is to get in touch or engage with scientists and funding agents internationally and identify potential anchor projects that are already being executed or in future plan with respect to the atmospheric rivers, mesoscale convective systems, monsoons, and tropical cyclones. You will see here that we already have discussions going on with a few of such projects. So atmospheric river recon from the US, which is already being executed. For other regions, the TPEX, Asia PEX, Toru will be talking about it right after. And in Africa, potential uncertainty analysis. They will just have to combine the data and produce the state of climate report. So our objective is for this activity to feed into providing input for these reports. We will also focus on the research aspect of predictability and projections of precipitation. And the last working group, as I mentioned, would be the capacity development at national and regional scales. So this would be informing the overall GPEX science strategy on what exactly the needs at local and regional levels are. So one of the first objectives identified by this working group is to look for, identify a few regions in vulnerable zones, and then get in touch with the national and the regional Met agencies to see what is lacking in terms of precipitation-driven events and how GPEX as an international coordination mechanism can help address these issues. And it will also work on in training students and scientists from the global south, and also promote sharing of precipitation database for research challenged regions, and then supporting existing regional activities as well. My last but one slide. So the implementation, I spoke about the science plan, the implementation, and briefly on the timeline as well. So as I mentioned, we are currently now in the year of precipitation pre-planning phase, where we are getting in touch with different national countries, agencies, national agencies, on the ongoing and potential futures field campaigns to request for endorsement to see if they fit within the GPEX initiatives. And the mid-years will focus on all the 4 activities, bringing them all together. And then the post would be all about producing scientific outcomes that come out of GPEX and making sure that these scientific outcomes reach out to the national agencies or the societies in need. So the strategy is trying our best to focus on few activities. This initiative is not going to do anything new. It is all about bringing together in an international coordination manner existing activities and making sure the outcomes of GPEX initiative is also equally shared with all the nations. A small advertisement, we are looking for new working group members. So for each of the 4 working groups I just mentioned, we are looking for new members, experts in these working groups. So if any of you here is interested in joining and being a part of GPEX, please do visit the WCRP website. You do have a page on GPEX, and the application process is clearly mentioned there. And we would also like to connect with potential field campaigns that relate to the 4 precipitation drivers. So if you are involved in such field campaigns or aware of field campaigns that could be a part of GPEX initiative, please do get in touch. We are interested in engaging with you and working with you. And also, we are currently discussing with various modeling and forecast agencies, NCEP, ECMWF, and we would like to extend this to other countries as well. So if you would like to interact with me, please make use. I'm happy to come talk to you. We can discuss and we can collaborate on this. Thank you.
Thank you, Hindumati. So any question, comment to her from the audience? Right. Yes, please.
Very good morning. Thank you so much for your very informative presentation. And I am excited to learn that you use the term local level. So could you please tell us what do you mean exactly by the local? How much local it is? And my second question is that who are going to be your stakeholder that you intend to engage at the local level? How much local? What do you mean by local? And who are your stakeholders? Thank you so much.
Thanks a lot. And these are tough questions, but I'm going to try my best to respond. By local level, what we intend to, or at least try to do is, this is one example that the working group 4 is currently working on. For instance, they have identified an institution in the Himalayan region, a high altitude terrain region, where they are aware that they do not have sufficient precipitation database to help understand the processes in that region. So they are going to get in touch with this institution. And because we know this institution is already working with the local communities, so agricultural sector or other sectors, so they have an understanding of what is needed, for example, to understand better the impacts of precipitation on agriculture in that zone. So they already have this knowledge. So we are engaging with this institution to get some input from them on what is expected in terms of precipitation database. What do they need? And is it possible for an international coordination mechanism to provide such database? So this is how we are trying to relate to the local community. And on your second question on who we are engaging with, as I mentioned, we try to look for local institutions already in place or some regional national med services which are ready to discuss with us. So we do have in a few countries where our experts are directly in connection with the national med services. So our objective is that at some point, we will be able to engage better and transmit the needs from that region to the international community. I hope I've answered. Yeah, thank you.
Any other? Yeah.
Yes, exciting and excellent presentation.
Thank you.
In fact, it's very much required for our region, Southeastern region. And we started a program we call STORM, Severe Thunderstorm, Observations and Regional Modeling. The severe thunderstorm
Yes.
and regional modeling
Mhm.
that we started in India
Okay.
in 2005. Up to 9 we worked, and in 2009, we converted it to 8 countries, neighboring countries, Afghanistan, Pakistan, Maldives, Sri Lanka, Bhutan, Nepal, Bangladesh, and India. So in this region, we are seeing the rainfalls, convective activities before monsoon, during monsoon, and collecting data. And it was on the program called SARC, Southeastern Regional Cooperation. Unfortunately, that SARC Meteorological Center is closed in 2015. Though all the countries' meteorological services, they are involved because they are the backbone of this program. And some of our scientific institutions like IITs, IITM and others, they have also participated. So a lot of data is gathered. IMD also, India Meteorological Department, preparing every year a report from 2009 to 2014 or so. But due to that incident of SMRC closed, so it is stopped. So is there any possibility to revive such program in this region?
So I would say that we do not have the authority to, tell countries that, okay, this program is needed. But what we can do is, as a scientific community, we can mention this as a potential research gap. So we can provide recommendations to initiate this consortium again. So this would only come as a recommendation from the GPEX community. And I think this is something important, and GPEX can take on to analyze the gaps with respect to data and the research in the region, and why it is important for an initiative that had to unfortunately close in 2015 to restart. So this recommendation can be given, but in the end, it will be up to the regions to adapt the recommendation and reinitiate this or not. Thank you.
So it's a recommendation. I think most of these 8 countries' meteorological services, they are really excited because that was one good platform under SMRC to bring them, because they are working earlier by deporting scientists to Bangladesh, where our center was there. But this is the program which bring to the field, and they work together in a very coherent manner, sharing their observations, putting the new network, and sharing all the information on time. Every year meeting at one place and discussing the results. They all are meteorological services, and few, as I told, academic and research institutions like IITM and so on. So I think I will talk to you
Yes.
further, perhaps,
Yeah, sure.
how to revive.
Thank
Thank
you.
you.
Yes.
Sorry.
Oh, no, don't worry.
Or any other question, comment, or how about online? Someone check. No,
No,
nothing.
it's not connected here, right? Online? No.
Okay. Anything else? Is it okay? Okay.
Thank
So,
you.
Thank you so much.
Thank you.
I would like to request session chair to kindly present the mementos to the speaker.
Okay, let's move on to the next speakers. Next speaker is Professor Toru Terao from Kanga University. His present title is The Experiment at Coordinate Field Campaign, Asian Monsoon Years. You okay? Yeah.
Okay, thank you very much. Good morning, everyone. And so today we enjoy the next sessions and we enjoy science of that the Asian monsoon. Many different monsoons that they are in the globe. So today I like to talk about the ASIAPEX program. It is the ASEAN precipitation experiment is launched and already working. And it is, we have one vision to have a coordinated observational and modeling initiative within the 2020s. So it is our goal, one of the goal. After that, we will have some very good scientific experiences, maybe using that data set. But so it is our goal. So we are now progressing this project. So we are now talking about this program, how it is. And so it is a kind of global partnership for the ASEAN monsoon research and hydroclimatic research. So sometimes it is extended from the monsoon. This is a kind of very big hydroclimatic system. So we make research about these systems. And firstly, we talk about the hierarchy of the projects in the perspective of WCRP. So firstly, GUX is there. GUX is under the WCRP, and it is one of the core projects of WCRP. And under GUX, there is some panels. So GHP, Global Hydroclimatology Project, panel, hydroclimatology panel, is the one of panels of GUX. And ASIAPEX is, where is ASIAPEX? ASIAPEX is one of the regional hydroclimatological projects under GHP. So there are many different locations and areas. They have different RHPs, regional hydroclimatological project. So such a very much focusing on the land surface process and also the observation and field campaigns under this GHP perspective. So we like to be one of the RHP focusing on the ASEAN region. So this is our location on under that hierarchy of the research projects. And we launched in 2019, and so we had a very nice research discussions in Sapporo in Japan, northern part of Japan. And we had 10 countries people coming, and including many Asian countries also, USA also included, East Asia and Northeast Asia, and also the West Asia, South Asia and Southeast Asia is included. And we discussed about that. And also after that, we had some discussion in the South Asia also in 2020. After that, we had some problems about the COVID-19, but we had some continuation of the projects. And we had a very nice discussion in the virtual mode in 2021 AOGS. So at that time, we had much more than 27, maybe abstracts from the globe. And so we had a very good honor that we had a top conveners award from this AOGS. So such activity is going on. So 2023, we had a very big milestone. So we had a review paper publication in the BAMS in 2023, and the very last phase of 2023 we had in May, sorry, and we had many co-authors, and they forms a kind of SSG, science steering groups in the Asia PEX. And after that, in last year, we enjoyed some workshops and also the sessions in the UX Open Science Conference held in Sapporo. And we had many other countries also included, and we enjoyed this discussion in Sapporo again. And we had many workshops. For example, this is some workshop for focusing on Southeast and Northeast Asia. And some workshop focusing on the South Asia also is there. And we also have one big session in the UX Open Science Conference. And such a activity is now going on. So we like to be a kind of parasol or umbrella. Under that, there are many different research activities, including field campaigns. And we will like to coordinate these observational activities. And if we make at the same time and some coordinated way, we make some observations, it may have very big impact on the Asian monsoon science. So it is our perspective. So I like you to join these activities from different countries. And so some history, and it is objective of the JAPEX. We decided it in 2019. And it is understanding of Asian land precipitation over diverse hydroclimatological conditions. So in this region, terrestrial region, there are many different aspects of the land surface settings are there. Also the orography, topography has very complicated settings. So I think to understand the ASEAN monsoon system or the hydroclimatic system, such a different land surface situation have to be understood. So we are focusing on these diverse hydroclimatic conditions in these regions. And also nowadays, it's very needed to respond to the social needs, including the predictions, disaster mitigation, and also the sustainable development. It's a very important aspect for our research project. And our activities, maybe you have some memory about that. So we have game and also Mahashri projects under GUX, RHP. And so we had a game from 1996 to 2005. And after that, Mahashri take over, and so from 2006 to 2016. So we are a kind of succeeding project from these projects. So we are developing activities following these activities. And there are many outcomes of Mahashri, but we have somewhat different perspectives from these past RHPs. Past RHP is basically focusing on somewhat the region-oriented perspectives. But this time we decided some different way that research perspectives will be set. So this is one figure about that. So this is the past two projects. They are focusing on some regions. But now we focusing on some different approaches to the same object. It is the ASEAN hydroclimatic system. So we try to have 6 different approaches to solve the problems of the ASEAN monsoon system. So we like to introduce such a which approach we will take. And we have 6 approaches. First one is the observation and estimation of ASEAN precipitation itself. It is not, we have so much uncertainties about that, as you know. So it's very important first topic for our project. The second one is the process understanding of the ASEAN hydroclimatic systems based on the land surface change also there. So such a atmospheric and land surface coupling is very important for our science. The third one is some larger view. So we have very different time and spatial scale phenomena, and it has a very from that subseasonal to the sometimes interannual, sometimes the decadal variability also there. And so these different time scale and spatial scale phenomena are there. And so their interrelationship is very important for the predictability of different time scales. So we focusing on such a predictability of the somewhat larger subseasonal to seasonal and sometimes the decadal scale. So it is our third approach of our project. And the fourth one is the high resolutional hydrological modelings, focusing on the anthropogenic effect and also the glaciers in high mountains. So such a very different type of hydrological system, very important player in the Asian hydrological systems. So we focusing on such a high resolutional modelings activities. And fifth one is the synergy effect. It is a kind of the collaborative observational and modeling initiatives. It's very important. It's also a kind of science, how to plan that, how to coordinate them. So we put the fifth approach to this point. Sixth one is the somewhat social needs is there. So we have to have somewhat much more reliable climate projections and useful climate projections for that the Asian hydrological system. So how we can get such a advanced and useful and reliable climate projection is very important topics of our project. So some researchers are working on this also. So there are very different approaches. So we have already done several different, much more, so much people working on. So one is, for example, this is a trim PR climatology, but it is very high resolution climatology have already been settled like this by Hirose-san and Okada-san. And so here the 0.01 degree climatology is created. It's very high resolution using trim PR. And this is another somewhat very ambitious project plan is there. This is the brain. It's there want to coordinate all the existing radar systems in the Southeast Asia, East Asia, and also South Asia. And sometimes we can extend it to the Northeast Asia also. And such a collaborative, coordinated system of the radar information system may be very important. It has to be very important for the measurement of the rainfall itself, and so how it is moving. So this activity also very interesting, but it may take some time, but it may solve within the 10-year period or so. So it is within our AsiaPEX period, we would like to get good insight for this project. And this is process understanding, the second approach. So Teramura-san et al., so Sato-san also do this, and it's a very interesting result coming up. And so they are analyzing about that where, when that the method scale convective systems is developed in the northeastern part of Chinese continent, and here. And so they tried to analyze the effect of land surface heterogeneity, and it is related with the temperature heterogeneity. So because of that, the land surface heterogeneity, so such a heterogeneity develops in these regions. So they analyzed the result very carefully, and they found that such a temperature heterogeneity has good effect on the making the mesoscale convective systems in these regions. And this is not when the topography is very have effect in some regions. So this that time no effect, but the very flat regions it occurs. It's clearly understood by their research. And also the Chinese people doing. It is one problem there for the precipitate troubled water estimation. So many estimations like MERA and also the NSEP and also ERA also there. So, but they have a big problems consistently. So the estimation of the water vapor over the Tibetan plateau is overestimated in many, many models. And they try to understand this, and they try to use the very high resolution mesoscale models to simulate the moisture behavior. And they find if they use the high resolution modeling, at that time, this problem reduced and solved. So it indicates that the very small structure of the slopes of Tibetan Plateau has very big effect on that. So such a process studies is very important topics in our research. And multiple precipitation variability is also related with each other. For example, the larger scale westerly phase and easterly phase has very different diurnal variability in this region. It is Yokoi-san done, so maybe he will talk this much more clearly and better. So I talk only this. And also that there are many, many different scale interactions. For example, over the Bengal Plain regions, diurnal variability creates the very strong southerly flow that is impinging to the Meghalaya Plateau here. It makes very big rainfall in nighttime. Such a very small scale is creating large scale structure of the monsoon precipitation. And also that for observations, we also have different activities like this. For example, the southern slopes of Tibetan Plateau, people have some new project, Hyplex, at the beginning in the 2018 or so. And so it is still going on. And they have oriented several rain gauges and the automatic weather stations in the very steep regions. And they are making observations to have a very good results, observing about the very clear view about the diurnal variability of the rainfall and which aspect and mechanism is controlling this, the diurnal variability of this region. And also, I'm also doing the same. So different regions over the Bangladesh and northeastern part of the Indian continent. We are now developing new projects, so on. And this is a risolometers situated in the Sylhet and Dhaka, and also we have the risolometers in the Cherrapunji and also Mawsynram also, and Shillong also. So such a observation in this region may have very important activity for it will be fill up that our Asia-Apex activity, big activity. So such a small different activities, they have a different view and different understanding. But if we combine with each other and getting that good data set, we have a very good advancement for that. So such a collaboration is very important in this synergy effect. And for the climate change detection and also projections, and also the modeling, how is the climate models are reliable? It's a very important topic. And Takaya-san, he also talk later much more clearly, but for example, the ENSO IPOC mode has very big impact on the predictability of this Asian monsoon precipitation. So such a large scale predictability is also very important. And so how we get that good predictability is very important topic for us. And so Hassan from Korea has such a very interesting result. And so for East Asia, some different regions of Asia, they have a different future perspective of the extreme events. So it's not the uniform, it's different from region to region. So such a estimation of future variability also very important for us. And this is another by Takahashi-san. So there are many, many researchers are doing this under this project. And we would like to make one field campaign within the 2020s. We may name it AMY2. AMY is Asian monsoon year. It has already been conducted from 2006 to 2012 under the Mahashri project. So we would like to make the next phase within this decade. So this is our plan. So for that, we need some discussion about that such a planning. And for this, we need some time. And 2026-27, we will have a big conference to fix up such a plan and so how implement these observations and how coordinate. So we are doing this activity, and recently we have some updates about the science plan. And we decided to have some goals as apex. So several goals. It is not everything, but if we attain this one, so everybody may happy. So this is very important. So we like to have such a several topics. We have to be achieved within these 10 years is very important. So we're discussing that. One is that the description, the past also include, and projection of precipitation extremes. Extremes is very difficult, and sometimes it's very different uncertainties are there. So we should solve this problem as much as possible to get much more reliable estimation about that such a precipitation extremes. It is our one goal. And the second one is improvement of S2S predictability. We should check current predictability and how it is extended in the future under some new observation system. It's very important. And third one is prediction of freshwater availability. It's very important for the people in this region. Anyway, in these different regions, they have different problems. And fourth one is coordinated field campaign. So it is Asia monsoon year itself. So such a goal has to be very important. So we are decided, and also organization very important. So now we are organizing science panels, regarding the 6 approaches. And this is a project steering group. It is the project working groups also needed for example, data center or for the capacity development. Some other very different problems are there. So we are doing the 2 different groups. One is panels, and also groups have to be very important. So we are now organizing these panels. First, we begin from science panels, and we are now organizing this. It will be within the former half of this year, we will be in this one. And the GPEX is now a very important collaborator from our ASIAPEX. And name is very similar. So sometimes they think that this is ASIAPEX is a kind of GPEX under GPEX, but different maybe, different. And GPEX is basically very much focusing on the precipitation. So it's very important aspects of the understanding of the global climate. But we are some different. So we are now, we have a history from game, Mahashri, and other places. So we are very much loving monsoons, especially Asian monsoons. So anyway, so such a people is gathering to our project. So we are now very much focusing on rather the hydrological system in Asian monsoon region. So it is our goal. So this is not confined to the precipitation, but we have to collaborate anyway, so too much. And so ASIAPEX, as Hindumati-san told, that they will have some anchor projects regarding 4 different types of the rainfall. So fortunately, there is a monsoon precipitation inside these 4 different types. So we are loving monsoon precipitation anyway. And so we like to be one of the anchor projects under the GPEX regarding the monsoon's precipitation. Is needed maybe. So it is a plan. And in South Asia, so here is South Asia, so many younger generation from Asia is coming. So this is, for example, especially in South Asia, there are so many people now they are 20 years old. It is a peak of this pattern, as you see. So it's a very important timing to develop, including these people coming to these activities. So such a capacity development for this region also very important. So we are thinking of that also. Now doing many things, especially the organizing science plan, very important. Science panel is very important. So we are now doing this first. And after that, we have many different conferences and so some sessions. We will have some sessions also. And the funding is needed. It is very important. And it also, there is a criteria for that anchor project. So $5 million. So for that, we have to apply for many funds, including Japan and other countries. And also under our umbrella, there are many projects they want to becoming that they want to contribute to the PEX. So they will have different fundings also. Such a way we will attain these goals. Maybe we can do. This is my. And also, IITM Monsoon Year 2 is approaching. So how we coordinate and how we focusing on that daily aspects is very important discussion now. So within 2 or 3 years, so 2026-27, we'll have one conference for Asia PEX planning for the Asia Monsoon Year 2. So it is our plan, and I hope many people are having that some intention to have field campaigns in the different regions and some different aspects. Then please come into our umbrella. So we are like to invite you to our project as Apex. It is my talk. Thank you very much.
So nice introduction of the Asia PX project. And we can take, yeah, quick question.
Right. And you nicely compared Asia PEX and GPEX. And yeah, I'll talk to Indumati-san also. Yeah, I think IIME2 told 26 to 2030.
So 26 may be difficult.
Yeah.
So
2029, it will be like we had that Monex
in
1979.
Okay,
Now
okay.
2029 will be completing 50 years.
I see.
So there was a suggestion in one of our big
Mhm.
meetings that we should have the next phase of Monex in 2029. Yeah, so that will be exactly 50 years. So that also kind of aligned for the Asian precipitation experiment.
Yeah.
And IITM and Indian government ministry, they are also thinking on the same line. So maybe we should take it to a bigger level and start the Monex 2.
Thank you
So
very much.
that's a
It's very exciting for us
Yeah.
to joining these activities.
Yeah.
And also maybe year of presentation may have some similar timing.
Yeah.
So I hope so we will be able to coordinate this like that. Thank you very much.
And the brain is also very good.
Yeah.
Brain.
Brain.
You have one slide on brain.
A brain. Yes, brain. Yes, it is very fascinating program. Yeah.
Yeah,
Thank
you
you.
very much.
This is a good opportunity to discuss such a collaboration during this workshop.
Yes.
Okay. One more. Yeah. Yes, please.
Thank you very much, Tino-san. It's a very good, ambitious program. I have two comments or questions. The high resolution TRIM climatology that from Hiroshi and Okada. Yes, is that data available to use? Can we download that climatology if we want to use it? Because I'm not aware of whether it's free to download. So that's my first question, whether you want to answer that, whether you know.
Yeah, I know. Yeah.
Okay.
It is available
Okay,
and you can download it.
okay, I
Yes.
just haven't found it. That's the question. And then the second one about the radar compositing, I mean, the BRAIN project. Regional radar networking is a huge challenge. Have you engaged with the people who have done this over Europe and the opera program? Because I think there might be a lot of good information there for you to maybe learn or use their lessons, because there were many lessons, the opera program. But yeah, I don't know if you know about the opera program and whether you've talked to the people.
Yeah, thank you very much. So I learn from you, and so we will do that. But the difficulty is there anyway. So it is some country and different countries have very different perspectives and observations. So how we coordinate it, not so easy. And so for that, we may begin from some coordinated observation campaign, combining some countries. And for example, 2 countries, for example, for the first, it's okay. We can do something and we can get some good results. They may some fact are changing some their thinking. So it is we do something, and we will get the good result in 10 years later. So it is our plan.
Last one.
Oh yeah. So a lot of the things you mentioned in that talk, the kind of targets, things like the cryosphere, the kind of pan-Asian extremes and freshwater availability are going to need really good observations over the Himalayas. But I don't think it's controversial to say that the Himalayas are probably the poorest observed region in the world, except for Antarctica. So how are you going to reconcile the fact that we've got really bad observations there with, and you're going to need them for a lot of these plans, right?
Yeah, so really not so much easy, and as you understand. So maybe, for example, that people are working on the glaciers. So they have a problem, facing the problem about the quality of the rainfall data, precipitation data set in the high mountain regions. So, for example, they are trying to validate that ILA5 using their own glacier data set. Such a way, we like to contribute to the improvement of such estimations using satellites and also the such models also. And so this one is very new project, and they're trying to understand the process in these regions for the precipitations. They have 2 peaks, but it is very not clear in not only in the satellite data set. So they are also observing the process. So for example, wind and temperature change also be observed. So using the data set, they are doing very good modeling activities. So such a way, we are anyway developing to solve these problems. So we like to collaborate with you. So thank you very much.
Okay, thank you. So thanks. So our online participant, I'm sorry because the time is running out. So if you have any question, please put a chat. I'm not sure chat is available. If so, put in. Maybe Toru will answer by chat or something. So
okay.
Okay.
Emails are not so good. So anything okay.
Thank you.
Thank you.
Thank you. I would like to request the session chair to present the mementos to the speaker, sir.
Okay, let's move on to the next speakers. Next, I have 2 names, but Dr. Radhir Singh is okay. Okay, from the ISRO, the India, and his talking title is Space-Based Rainfall Measurement, Present Capability and Gaps. Okay, and the time is yours.
So good morning. Actually, I'm here on behalf of Director Space Application Center, ISRO. Actually, unfortunately, he could not make it and due to some other commitments. And he has sent actually his regards and best wishes for the best, actually, a good discussion on this work. So I'll discuss about the rainfall measurement from the present and the future sort of satellites, which can sort of cater the application of monsoon understanding and different processes to model the monsoon and then we sort of predict it in a better way. So I will walk you through this recent development, particularly in the ISRO as well as other space agencies. So just to start the, or just sort of set the tone of the presentation. So this is basically shows the recent floods. If you see the trends in the floods over Indian region, and these are taken from the MOES. So where you can see that flood events actually are increasing at a rapid rate, almost 3 times. I mean, if you compare 1980s and now, so floods events are almost 3 times now. And if you just segregate these figures, actually you will find that mountainous region actually are getting more extreme rainfall events. And where we don't have the, particularly if you see the northwestern Himalayas, where we don't have much rain gauge observations. And most of these studies you will find is basically based on the satellite observations, if you talk about the mountainous regions. And then if you see the casualty also, a lot of casualty, mainly actually because of the heavy rainfall like thunderstorm and floods. So to better understand this rainfall variability at shorter time scale as well as spatial, so what we need is the space-based measurement. So that is what actually I will be talking, how space-based observation can actually sort of help to understand all these events. So this is in ISRO, I'm just showing the only this last 2.5 decades. So what sort of satellites we are launching. So we have basically two programs if you talk about meteorology and oceanography. So we have geostationary and then we have low Earth orbit satellite. So in geostationary, we have started with the very simple, like it's imager and sounder. So it's basically 6-channel imager and this 16 or 18 channel sounders. It's typical like goes, I mean, in mid 80s or 90s. And it provided the information about vertical temperature and moisture information, as well as other parameters like rainfall and your outgoing long wave radiations and cloud informations. And now we have, at present, we have InSat 3DS. And it's again a 16-channel sounder and then 6-channel imager. So data you can get about something like, if you talk about rainfall, it's about 4 kilometers. And if you talk about the temperature and moisture profile, it's about 10 to 15 kilometer resolution. And again, this sort of information is only available from IR in the clear sky. Once there is a cloud, so you may not get the temperature and moisture information because of the inherent problem in this physics and other things. And in future now, what we are planning is a very advanced sounders, like hyperspectral sounder on geo platform, where we can have something like thousands of channels. Like already we have in other polar satellites like ERC and AIRS. And also spatial resolution will also be in something like sub-kilometers, like 0.5 kilometers, where we can target the heterogeneity in the rainfall. But again, this is based on the infrared sensors. Okay, and then we have InSat 4th generation also, which will have also like lightning mapper. When you talk away like a heavy rainfall or thunderstorm, it is generally actually associated with the lightning. So if you can sort of measure the lightning, you can indirectly convert it into the rainfall or a lot of like your vertical velocity in a cloud. So in future, we will be having the lightning mapper also. That will also be very helpful to actually to understand the extreme rainfall events. As far as LEO satellite is concerned, so we have satellite related to the oceanography and meteorology, where we have wind speed and temperature and moisture profile from the microwave sounders, because microwave is only possible in the low Earth orbit. It's not possible in the geostationary. So we have at present, we have megatropics, and which had Saphir, where actually we could have this ice clouds. Okay, so those sort of observation we are already from the megatropics, and it was basically with the CANAS, that is French Space Agency. It was a great successful collaboration, and now we have planned this like microwave sounding, that is for humidity as well as temperature. So this is again we are launching out in this coming year 25 only in December. That will have something like 14-channel temperature sounder and then 6-channel humidity sounder. So that can, the advantage of microwave is actually it can provide the information in cloudy region also. So once there's cloud, even then you can sense what is the moisture profile inside a cloud. And also you will be having the precipitation estimate with a much better spatial and temporal resolution. And then we have also Trishna. Trishna is actually again sort of, though it's particularly for the land application, but then you will have a resolution of something like meters, like 100 meters. Okay, so that can again provide the rainfall information at much smaller spatial scale. That will also again can contribute to the monsoon processes and understanding of these events in your modeling the cloud processes. Okay. So if you talk about why space-based observation, so if you can see that we have a different way of measurement the precipitation. We have radars, then we have satellite, and we have rain gauge. So all actually, if you see all these sort of measurement have some issues. So rain gauge, like, I mean, it's sort of well known. I don't have to stress it, like it's a variability it cannot pick up because it's very sparse and very inhomogeneous distributed in space. Then we have satellite, which sort of sees actually cloud from the top. What is happening below the cloud or inside the cloud may not always available from the satellite. Though there are some satellite which can penetrate through the cloud. That is what we call radars. Okay. But if you take simple microwave or infrared sensor, it cannot actually penetrate the cloud. What you get is basically top of the cloud. Okay. And then we have radars. Then again, you have a lot of problem near the surface like cluttering and other things. Okay. So, but when you combine all this information, then we get the sort of we can say is a most accurate and a best representative of the rainfall processes. If you can combine all sort of this information. Okay. So if you talk about rainfall from space, so we have different like platform, frequencies, techniques, and then we have a lot of modes. Like, so if you talk about platform, as I mentioned, we have two platforms like geostationary and polar. So advantage of geostationary is it always sees the same area. So you can continuously get the information at a very high resolution, temporal resolution, like maybe 5 minutes to 10 minutes. As well as space, you can get nowadays, we have advanced sensor, like you can get information about half a kilometer. Okay. But then they are only in the IR, that is infrared. So once there is a cloud, you cannot see below the cloud. Okay, that is the actually disadvantage of this. Then in frequency, if you talk microwave, we have different microwave frequencies. Okay, then in particular the polar satellite, if you talk about, so we have like gigahertz frequency where like higher frequency where we can actually explore the ice, and then we have somewhere like lower frequency, something 30 to 40 gigahertz where we can target the cloud or the liquid water. So we can actually understand the different cloud physics using the multiple frequencies, like higher frequency and lower frequency, because they have different signature in the in this different spectra. Then if you talk about technique, we have active and passive. When you talk about active, it's basically radars, where we can get the entire cloud structure. Okay, precipitation radar, for example, GPM or the stream. Okay. And if you talk about modes, we have imaging and sounding. So basically imaging is nothing but two-dimensional view of the your phenomena which you are trying to study. And sounding is basically vertical profiling. So that's what we call sounder and imager. So if you talk about their advantages and disadvantages that I already mentioned, so geostationary good for nowcasting application because you are getting a very frequent measurement every 5 minutes to 10 minutes, and you can sort of see the evolution of your cloud system or rain-bearing system. Okay. When you see the polar satellite, they are actually, but in the geostationary, we cannot have microwave because the height is actually too high. It's about something like 36,000 kilometers, where microwave signal cannot reach. So it's very too feeble. So we cannot place a microwave instrument on the geostationary. That is the disadvantage. But polar, we have microwave instrument, but their footprint is quite large. So we may have something rainfall information of 5 to 10 kilometers, not higher than that. So because the energy constant, because the microwave has, less energy compared to the infrared. So that is the disadvantage here. And then we have low inclined. If you talk about orbits, so low inclined mean like more tropical coverage. If you put satellite in like TRIM, we had a TRIM satellite, and then also megatropics around ISRO and this CANAS. So it was a basically low inclined. You can get the frequent measurement of the tropical region, that like for hydrological and energy exchange processes. So these are, different ways actually we can have the precipitation measurement. So currently, if you talk about geostationary, we have 5 major, space agencies where we are operating the INSAT 3D series, and now currently we have INSAT 3DS in this. And future we will have INSAT 4 generation, which will have very, very advanced, sounder and imager capability with the lightning mapper. Then Meteosat is operated by EUMETSAT, that is European, and then Himawari, Japan, that is, now we have Himawari 8 and 9, I think. So these are advanced sensors, both. But our INSAT 3DS is slightly off, one generation back, compared to other things. So we are actually gearing up for the next generation now that will be compatible with other 2 also. Then we have GOES. We have also another very advanced sensor here also, getting information about something half a kilometer of sort of spatial resolution and 5 minutes in temporal resolution. Then we have Chinese, that is FY series. We call it geostationary FY series. They have also very advanced mapper, lightning mapper, as well as your sounding capability. As far as polar orbit concerned, so these are all satellites which actually have contributed in the rainfall from something like 1980s or 1975s. These are all different satellites which are not meant for the rainfall as such, but they are meant for like temperature and moisture sounding, but they are also contributing in the rainfall, estimation, because there are certain frequencies which are sensitive to the rainfall processes. So if you talk about here or India, that is Madras Safir. It was basically a polar satellite, and CANAS and ISRO, and it has contributed in the GPM also, that it was part of a GPM constellation where we could have this rainfall measurement. And this is a DPR, that is GPM, that is Doppler precipitation radar. It's now still this in orbit now currently. And now we have recently launched this MHS. It has also again the ice cloud you can get from this microwave 183 gigahertz frequency. So these are our ISROs. And then these are all, I mean, different agencies and I mean, like ESAs and Chinese, Japan's, all sort of satellites are there, which are giving the rainfall informations. And these are part of the GPM also. So if you see the, I mean, best example of the rainfall measurement mission is GPM. And it is basically a constellation where all geostationary, polar, microwave, infrared actually are sort of combined to get the rainfall information. And then they have also what you call is a core rainfall observatory, which is nothing but a radars. So once you have a radar, it can penetrate through the clouds and it can give the vertical profile of like what you call it the reflectivity. And from that reflectivity, then again, using some relation, you can get the rainfall. So what we do is like we calibrate these sort of all the sensors with these radars and then get a unified product. Okay, so this is a successful mission. Currently, it's in orbit and it has something like 30 to 40 satellites in this constellation. So this is a different signature. If you see a rainfall bearing system from different frequencies or different satellite, how actually it looks. So you can see this is 19 gigahertz, basically a microwave channel. So you can see the rainfall here. This is a rainfall here. This is a cloud basically. So it's actually your ocean. It is the warm signature. So because cloud emit more than your, let's say, the clear sky part. So if there is a rain, actually it reflects as a warm or the more brightness temperature. But same thing if you see from, let's say, higher frequency, 89 gigahertz, you see it's cold because this is scattering based and this is emission based. So same rainfall bearing system, you can actually see the different way. Okay. And then this is basically infrared measurement. Again, you see here cold because it's a cloud, higher, it is at height more. So temperature decreases with the height, so it will have a colder temperature. So that's actually, but now if you combine all these three channels, you will get a best product because this shows the scattering, basically ice particle, whereas it shows the liquid particle, okay, in a cloud. So that's where actually if you combine all this information, so we can get a better rainfall product. This is now present inside 3D. We have the 3DS, 3DR, and these three satellites. Currently, we have only two, 3DR and 3DS, because this 3D life is over. So that is, again, I told 6-channel imager and 18-channel sounder. And these are different images or different channels. And this is a rainfall product from this. That's what we call hydro estimator. So which is a 4-kilometer resolution. And it is half an hourly. So this is a particular rain event in tropical cyclone. And this is, again, that, as I mentioned, that if you can estimate this height of a cloud, that is what we call is a tropospheric or sorry, high cloud, basically high altitude cloud, which can sort of sometime it can even cross the tropopause level. Okay, they are generally associated with the lightning activities, okay, because there is a lot of updraft and other thing. So you can easily find out using some algorithm that which are those clouds which are sort of what we call overshooting clouds. So once you understand the overshooting cloud, you can actually calculate or estimate the lightning activity inside this. And that lightning activity can be used for nowcasting purpose, like half an hour prediction time we can have. And we can propagate this image using like some kind of like optical flow technique. And you can actually have the lightning information for next half an hour, not more than that, but half an hour is also a good time, I think, to sort of evacuate this from the extreme weather event. These all products actually are available at our MOSDEC. There are some of the samples product, but there are many products, like 40 products are there with the oceanography, meteorology, and other things. So this is one example here. This is a rainfall, particular day, and this is cloud microphysics. So you can also understand what are the like sort of composition of the cloud, like cloud microphysics, cloud liquid water, ice particle, their thickness, their drop size distribution. And then using some optical flow technique, you can sort of propagate this information in time for next half an hour using past 3 to 4 images, and then in future, where it going to have like a very extreme weather event. So this is just, we are putting only the satellite based information. We are not doing as a like weather prediction or something, but this satellite based product actually we are trying to propagate. This is one example of, as I told, megatropics. That was sounder and this thing, humidity sounder as well as imager. So you can see the rainfall product, and they are compared with the trim rainfall 3B42. So you can say there is a good match between these two products. So that is another a good, this collaborative effort that CNES and ISRO. So that was. Now, if you see the another application of satellite-based rainfall is iMerge. iMerge is actually basically again a multi-satellite sort of product, which is available around 10 kilometers spatial resolution and 30 minutes if you take in temporal scale. So you can see this is the extreme or the heavier rainfall events. So basically it's a climatology over like 20 to 20 years. So extreme rainfall events or say heavier rainfall events, how in space they are looking, like spatial variability of extreme rainfall events, where rainfall event is so more than 60 to 60 millimeter per day. Okay, so that shows the how these are actually over the east coast and then over eastern India. So how they are. Now you can study the trend also using the satellite observations. You can study the trend also, how actually they are in global warming, how the trend is actually behaving. And then this is Western Himalaya, as I mentioned earlier. So these are purely satellite-based observations. They're also, this is basically paper I'm referring here. So you will see that this is actually basically, if you study this trend, you will find that mountainous regions are getting more heavier rainfall in recent decades. And that is again purely based on the satellite observation. So if you see here, rain gauge observation, I mean, you won't find any rain gauge here. I mean, very, very limited, one or two, maybe something like this. So that's where you have to, I mean, take the satellite observation for this particular this thing case. So now what are the gap areas in if you talk about space-based observation? So as if you see the visible or microwave or IR, if you see all this frequency, so when we talk about IR sensor or visible sensor, actually we are just seeing the top of the clouds. We are not getting any information below the cloud. So when clouds are shallow clouds or warm clouds, okay, they are like their brightness temperature is very similar to the surface temperature. So we may not get the rainfall accurately for the warm cloud or low level clouds. So that is where infrared sensor has some issues. But then advantage of infrared is they are very, very high resolution, half a kilometer. Right? But when we talk about microwave has advantage. They can penetrate the cloud and they can actually study the cloud microphysics, how cloud drop size are there, what is the, I mean, their interactions. But then disadvantage is we cannot have very high resolution in the microwave, right? So except radar, you can have a high resolution like active radar, but then we cannot afford so many radars because they are very costly and operating this thing also is very, very costly up here, right? So that is the, now what we can do, I mean, what is the future now? So one, if we can demonstrate like on geo platform, if you can put like microwave sensor, okay, like it can continuously see something like a half an hour or 5 minutes image. But the microwave at geo platform is actually very, very challenging because that energy is not reaching up to that high, that altitude. But if we can sort of develop some technique where we can place microwave on geostationary, so that can give very, very high resolution information about the cloud microphysics as well as the accurate estimate of the rainfall process. So that is a challenge, but that people are working on this. I mean, maybe someday we will have this sort of, I mean, this sensor also. And then if you talk about active passive, now we have currently we have a radars. So we have, I think multi-channel or multi-frequency radar. So we can have the drop size distribution also. Like if you have a single polarization or single frequency, we may have sort of vertical distribution, but we may not be knowing their shape size and their particle size. Okay, so if you have multi-frequency as well as Doppler facility, like if you have Doppler capability also, then we can also estimate the updraft and downdraft velocities. So in future, if we actually plan dual frequency and polarization as well as the Doppler capability, so that will be actually the way forward if you can, if you want to have a better estimate of the rainfall. Okay, so that is how we should, I mean, look forward. And if you see the ISRO's future, so this is GISAT, geostationary satellite in infrared. So where we will be having a rainfall measurement like every 10 to 5 minutes in different areas. So if you target this area, we can have measurement every 10 minutes with the resolution of about 1 kilometer. And if you target this area, so we have information every 30 minutes. Okay, so like that. So that all those things have been finalized, and the satellite has been actually in the this thing integration phase. So I think soon it will be launched. So we can expect a rainfall of something like 1 kilometer resolution from the infrared sensors and a temporal frequency of something like 5 to 10 minutes. Then you have another like INSAT 4th generation also, where we have this again same like 0.5 to something like 1 to 2 kilometer, and then we have lightning mapper also, which can again cater this extreme rainfall event and their sort of microphysical processes. Then we also have this in the LEO orbit, that is microwave. We have a temperature and humidity sounder, and then we have a dual frequency scatterometer. Okay. And then also we are also planning GNSS RO. That is this advantage of GNSS RO is actually it can penetrate the cloud also, because the frequency is actually it's about 1.4 gigahertz, which is 20 centimeter. So it can easily penetrate all those cloud and ice particles. So you can get the temperature and moisture information inside the cloud also. So that is all are now in future, maybe in next 2 to 3 years, I think that sort of satellite we will be launching. And microwave also, we will be also launching the hyperspectrum. Okay, hyperspectrum, more number of vertical information we can expect. Now, these are the recently launched mission or are in planning phase. So this is EarthCare is actually recently launched by JAXA and ESA. So this is actually very, very advanced sensor. Now, like as this theme actually is a monsoon process, understanding and prediction. So if you see the monsoon process and all this numerical and climate model, basically we are having some problem in understanding the cloud and aerosol interaction, right? So this satellite actually has got all sort of information. It has got aerosols, also the cloud particle, and then Earth radiation budget. So this satellite alone actually can cater many problems which are actually faced by these modelers, where we don't have the proper understanding of cloud and aerosol interaction and precipitation processes. So single satellite can give the all sort of observation. So that is now already launched, and data is now already available from the satellite. Then another this NASA and JAXA, like already this GPM mission, they are planning a Doppler enabled DPR. That is, as I mentioned earlier. So you can have the updraft and downdraft velocities of the ice and cloud particle, and then you can actually estimate the rainfall rate with a much more accuracy. So that is also they're planning now. I think it's in development phase. And this is the European satellite Meteosat 3rd generation. Again, that is very, very high resolution infrared based measurement, less than like 0.5 kilometer, and temporal resolution is about 5 minutes. So that is already launched and it's providing the lot of meteorological observation for understanding the monsoon processes. And this polar satellite, this is again European only, but in polar. So a lot of instruments are there again, like spectrometer and your sounder, micro humidity sounder, temperature sounder. So this is also now in plan, and it will be launched soon, I think. Now, another very, very this advancement actually they are now doing is the startups. Now, this is basically tomorrow. R is basically a startup, US-based startup, and they are planning to launch about something like 30 satellites. So in 30 satellites, they will be having radars, precipitation radars, as well as the sounder, microwave sounder. So once you have more number of radars, so actually you can get the more sort of temporal and spatial coverage. So if you have 20 radars, so you can get every 5 kilometer spatial resolution and every 2-hour rainfall measurement. So that sort of advancement is going on. So they have already launched 2 satellites, and they will be launching about now some remaining 28 satellite in next 2 to 3 years. So that will be again a constellation which will provide the very, very useful information for about the 3-dimensional mapping of the rainfall. Now, if you have seen the all sort of this observation, we have some limitation in each of these. Okay, maybe IR, visible, radars, rain gauge. So best way actually is how we can synergize this, how we can actually sort of combine this information. So we have rain gauge. So if you have rain gauge measurement, so you have a very, very what we call the representativeness error, because it is a very local measurement. It may not represent sort of cloud scale. So, but if you take a satellite also has some problem. That's what we call a beam filling problem, because it may not see the entire cloud, okay, or it may see like a very big FOV, but cloud is a very small portion of that FOV. So it will underestimate the rainfall. So all sort of information, if you just combine with radars, rain gauge, and your satellites, so then sort of we can make a unified this product, which will be having more accurate than each individual of this product. Okay, so that is how actually we should do in future. We should actually integrate all this information. This is one of the example like this in GPM itself, multi-constellation, multi-satellite. But then again here radar is only one. Okay, this is one single radar only. So if you add up these multiple radars rather than one radar and with the Doppler capability, so it will be actually very, very nice and very high resolution product that we can get. This is another example of where we are working with JAXA, and we have generated one rainfall product. Okay, this is a very high resolution rainfall product combining all rain gauge and this other satellite GS map, that is actually a JAXA product. So you can see there is a large error in the western Ghat, where rainfall underestimation and overestimation is quite large because of the topographic influence. And when you combine when you integrate rainfall, these rain gauges, then you have sort of error are reduced here. Okay, so this is one of the example where JAXA and ISRO are working, and now this product is available for last, I think, 20 years for daily scale. I think hourly scale now they are working on this. Okay, so I will stop here. So
Thank you so much. Time is running out, but we can accept one quick question. It's okay. Otherwise, also the online participants, please send your message through the chat. Okay, yes.
Okay, thank you, Mr. Chairman. I am Professor Tiwari from Uttarakhand and live in the heart of the Himalaya. You know, the Lesser Himalaya, which we also call the Middle Himalaya in the entire northwestern part, is the most densely populated and the rapidly urbanizing mountain of the world. And we are facing high frequency incidences of heavy rainfall, extreme rainfall, whatever you, and it is generating flash floods, highly localized at a very, very local level. So how far this space-based technology can help the policymaker in these small areas at the local level to generate an early warning system, not only of the high intensity rainfall, also the flash floods in the region. Thank you so much.
Actually, currently, if you talk about one problem, actually, the mountains area is whether it's a satellite, you have a lot of heterogeneity because if I have a, let's say, satellite resolution of 5 kilometers at present with the maximum, 5 kilometers basically is a radar. So I can at most get the resolution of about 5 kilometers. So if your rainfall variability is even, I mean, smaller than this 5 kilometer resolution, even satellite can't help as of now, right? So only thing is with this 5 kilometer, and if you can have sort of climatology, okay, maybe let's say we have something like 20 years of data using some radar observation. So can we generate a climatological map? Which are the prone areas where we have these extreme rainfall events? Okay, because as far as observation from institute is concerned, we don't have that much, highly dense network of the rain gauge. So first step should be, I think, let's have a climatological information using the, past observation and see which are the prone areas where all these frequent observation or frequent extreme rainfall are happening. And after that, once we have the climatology, then we may have planned maybe something radars, network, or some rain gauges observation there to sort of understand the different processes and then to model it. And another, if you go to next step, then we may have something like high resolution observation. Like we have from infrared, it's about 0.5 kilometer. But then we may not get the entire cloud structure with that. And mountain region are the cloud structure, and this process are very, very complicated because there are so many, what we call is cloud burst and other thing. So I think using this infrared, high resolution and micro, we should combine and then have a climatology, and then let's have some sort of a in-situ observation network to model it. I think that will be the, best idea to cater this sort of problem.
Thank you so much. And as I say that the online participant, please send your message on the chat. Maybe Randy will answer later. So because we have a 30 minutes behind the schedule, so we should move on to the next speaker. Thank you so much.
Request you to kindly present the moment to the speaker.
Next speaker is Satoru Yokoi from Jamstec, Japan. His story is a precipitation diurnal cycle over coastal region in the tropical Asian monsoon domain, intensive observation and model evaluation. Satoru, time is yours. You have 15 minutes, include Q&A.
Thank you very much, Chair, and good morning, everyone. I'm Satoru Yokoi from Japan Agency for Marine Earth Science and Technology, JAMSTEC. And today I will show you some results of our recent field campaigns over the tropical monsoon issue. And first of all, I will thank my collaborators or the co-authors of the papers I will introduce in this presentation. Okay? Needless to say, the diurnal cycle is one of the fundamental components of the precipitation variability in the tropics. And its behavior is completely different between land and surrounding coastal waters. Over land, you have afternoon precipitation maximum, while over the coastal waters, we often observe the nighttime offshore migration from near the coast to at least 100 kilometers or farther. And this migration feature has been a subject of interest of researchers for more for decades because it seems the physical link between the daytime insolation and nighttime precipitation is not straightforward. And it is still challenging to simulate this migration feature using the numerical models. So the researchers have focused on this, this offshore migration and proposed several mechanisms. And some researchers focus on the role of the gravity waves excited by evaporative cooling associated with land convection or radiative cooling of mountains. And some focus on the gravity currents such as land breeze or a convective cold outflow from existing convection and to generate new convection to the offshore side of the existing one. And others look at the advective effect of environmental winds. And these mechanisms, these studies heavily relied on the numerical simulations and satellite data. And which of these, which of them are more plausible than the others, or which are important, and where and when each of these mechanisms are important is still under question. So to verify these mechanisms, we think we need to know much more about what's happening in the coastal waters, where the in-situ observation is a little bit scarce. So therefore, we conducted, we take the west coast of Sumatra Island, Indonesia, as an example. We conducted 2 field campaigns using our research vessel to get observations. That is, and in this study, we will argue the mechanisms using these observation data. And the 2 field campaigns are conducted under as a part of the Years of the Maritime Continent YMC project under collaboration with JAMSTEC and Indonesian meteorological agencies and research agencies. And the first one was conducted in the Boreal winter season of 2015, and the second one is in 2017. And for both campaigns, we use our JAMSTEC's research vessel Mirai, and we deployed this vessel at about 50 or 90 kilometers off the west coast of Sumatra Island and stayed there for several weeks. And we also use the weather station at Bengkulu, it's the coastal city in Sumatra, and we the vessel has the sea-bound weather radar at the top, and also the Bengkulu station has operational weather radar. So we can, by combining the observations of these 2 radars, we can observe the precision signals over a wider range around the coastal areas. And furthermore, we conducted a variety of observations, like 3 hourly radio zone observations at 2 sites, and so on. So we can know the contrast between land and surrounding oceans about the atmospheric conditions. And in this talk, I will focus on Dian cycle, but these campaigns are not limited to the Dian cycle, but also targeted, for example, torrential rain and Mountain oscillation, and also the Indian Ocean dipole, IOD, and its relevant processes, ARC processes. Okay. So the first, this slide shows a Hofmiller diagram of radar estimates precipitation as a function of the distance from the coastline, shown by these purple lines. And time goes down, and there are very contrasting features between the 2015 campaign and 17 campaign. In 2015 campaign, we have very regular Dian cycle showing by these bands almost every day as before the December 13. Okay? And after that, this feature has totally disappeared, probably because of the arrival of the Mountain oscillation convection. In contrast, in 2017 case, sometimes there is offshore migration like this, and sometimes not. So it's kind of an intermittent, not regular, but an irregular feature. So it's very contrasting between these 2 campaigns. First, we will focus on the 2015 case. This is a mean down cycle of a precipitation for these 20 days, very regular down cycle. And you can clearly see the land convection in the afternoon and offshore migration during nighttime and early morning. And also you can see the two different characteristics migration speeds. And edge of the precipitation signal moves offshore a little faster than the precipitation maximum. These features has been pointed out already by previous studies using satellite observations. And as I said, at this campaign, we conducted a radio zone observation every 3 hours over the vessel and the Bengkulu station. So next, I will compare what is the thermodynamic profiles are between these two sites. This is a mean down cycle of potential temperature anomalies from the daily mean over the vessel and over land site. And they are very contrasting features. For example, at the land site, Bengkulu, the daytime anomaly is vertically in phase, at least below the 800 hectopascal level. But over the coastal waters, the positive anomalies is kind of tilted. And you can see the cooling in the lower free troposphere before the cooling in the boundary layer. This means the atmosphere becomes more unstable just before the arrival of the precipitation signal shown by this umbrella. And furthermore, comparison with the specific humidity data taken from the radio zone as well, we found that this cooling is associated with, accompanied by the moistening, from which we argue that this cooling is probably caused by the ascent motion. It's an adiabatic process. And furthermore, comparison with the radar data suggests that this ascent motion is maybe due to a gravity waves excited by some cooling of the land convection associated with the convection over land. So presumably it is cooling due to the evaporation of rainwaters. So this results suggest the is an indirect evidence that show the existence of propagating gravity waves ahead of the migrating precipitation signal. Okay, let's move on to the 2017 case. As I said, we have, in some days, sometimes we have offshore migration, sometimes not. And we focus on the wind component, wind environment difference between these two categories. And we found that for the days with clear offshore migration, we have a low-level onshore jet in the evening hours, which cannot be found in days without offshore migration. And the jet axis is located at 950 hectopascal level, so it's just near the top of the boundary layer. And this jet is considered to play a role in the regeneration of convection due to the convective cold outflow coming from the coast. So these results suggest that importance of the gravity current hypothesis for the offshore migration. And such difference in the environmental wind cannot be found in another place in the tropical monsoon Asian region, which is in the Luzon Island. And this campaign has been introduced briefly by Terao-san. And actually in 2018 summer, we conducted a land-based field campaign at the Lawag City, northwest part of the Luzon Island, under the collaboration with the Philippine Met Agency, the PAGASA. And we conducted the radar observations and the radio zone observation, etc. And we found that the offshore migration is observed only in monsoon break periods when the free troposphere wind is a little easterly, and also there is a maximum in onshore wind in the boundary layer. So it's very consistent with previous slides. And in addition to analyzing the observation data, we use this data to to evaluate the model performance. Jamstack has developed a global cloud system resolving or cloud permitting model, atmospheric model, a NICAM, for more than 20 years. And here we compared 3 versions of NICAM because they have a very diverse diversity in the reproducibility of the offshore migration. For example, NICAM 1 outperforms NICAM 2 and 3 two other versions. And we hypothesize that this diversity in the reproducibility is caused by the reproducibility of the regeneration process of the convection by the cold pools. To test this hypothesis using the shipborne observation data, we compare the mean cold pool intensity observed and simulated by the 3 versions of NICAM. And in short, all of the NICAM models underestimate the mean cold pool intensity, but the NICAM 1 is a better job than the NICAM 2 and NICAM 3. So it's consistent with the reproducibility of the offshore migration. So in short, this result further suggests that the cold pool intensity is important, which means that the regeneration process done by the gravity current, like a cold pool, is important for the offshore migration. So I will summarize my talk. We conducted 2 shipborne observation campaigns of the west coast of Sumatra, and analyzing these special observations together with routine observation, we found that a lower free tropospheric cooling, which suggests the existence of gravity wave propagation. And also we found that in days with offshore migration, we observed the environmental low-level jet in the boundary layer, which is considerably favorable for the regeneration of convection by cold pools. And furthermore, we compare with model outputs, and we found that representing the cold pool realistically seems important for the models to successfully simulate the offshore migration. So that's all. Thank you very much for your attention.
Thank you. So any question or comment? 1 or 2? Yes, please.
Thank you very much for your presentation. So I just want to know what will be the role of Kelvin waves in this kind of the diurnal cycle, whether it has any role like fast moving Kelvin wave or slow moving Kelvin wave has the role in this diurnal cycle?
Thank you for your question. Talking about the Kelvin wave, of course, its period is longer than the diurnal cycle. So, and I think the role of the Kelvin wave is to set the environmental conditions, conductive or not conductive for the diurnal cycle. And for example, if you have a very strong westerly Kelvin wave, westerly anomalies associated with Kelvin waves to hit the Sumatra Island, so the wind condition is not good because the strong wind blows the convection inward or something like that. So I think the Kelvin wave is important for the such kind of environmental setting.
Thank you. Anyone take the online participant question? No? Nothing? If no, yeah, thank you so much.
Thank you very much.
Let's move on to the next speaker. Thank you. This speaker is Dr. Sachin Deshpande from IITM. His title is the Lane Type Classification and Compact Organization in Polarimetric Radar Observation and Compact Permitting Simulation over the monsoon cover zone. Sachin, okay. Time is yours.
Good morning, everyone. I'm Sachin Deshpande from IITM. I'm going to talk about the rain type classification and convective organization in polarimetric radar observations and convective permitting model simulation over the monsoon core zone. This work is done by Harshad Hanbante, who is a PhD student with us. And I would like to thank my co-authors Subrata Das, Medha Deshpande, and Manisha Tupsundare. So this is a brief outline. I will talk about the convective organization and why it is vital for quantifying the convective organization through observations. The study area is obviously over the monsoon core zone, and what is the need for research test bed for process studies. I will briefly describe about the methodology for rain type estimation and the convective organization, and then I will have some results on the mean properties of convection during the JJS 2022. And then we perform a high resolution model simulation for knowing how well the model represents the convective organization when we have a reference with the radar observations. So as we know, in the tropics, the convection exhibits a hierarchy of scales ranging from few kilometers and hours associated with individual cloud system to the mesoscales of squall lines and cloud cluster to synoptic scales of tropical cyclones. The precipitation in the atmosphere comes from various types of clouds like convective and stratiform, and they exhibit the distinct vertical structures in terms of their vertical motions, divergence, and rotating profiles. When we see the organization of convection, sometimes it is scattered in the domain, other times it is spatially clustered in one region. So this variable spatial distribution of convection, we can consider it as an organization. And this organization of convection actually relates with the severe weather events. There are recent studies like Tan et al. So they showed that there is a regional increase in the tropical precipitation, and it is associated with the rise in the frequency of organized convective events. So hence the quantification or estimation of convective organization, or we can say the aggregation, becomes vital. Among the many observing platforms, the scanning radars are the best tools to study this convective clustering because they have continuous time aspect of the convection during the entire life cycle of the convective cells. And these radar-based convective clustering, they provide a reference for estimating how well the high resolution model represents the convective organization. So this is our study area. The figure to the left shows here. It shows the long-term mean rainfall during JJS. And as we see, there are three strong convection areas, monsoon zone, which is over the central India, Western Ghats, and Northeast India. Over the monsoon zone, we know it is prone to the passage of synoptic systems like lows and monsoon depressions, and that area is favorable for deep moist convection that frequently occurs there, which produces the widespread and heavy precipitation. So the proper depiction of convection feature becomes vital in terms of its spatial structure, diurnal cycle, the precipitation, the lifetime characteristics. So considering this importance, IITM MOS has established an atmospheric research test bed, which is a permanent observation facility in the core monsoon zone for improved understanding on the monsoon convection. So at ART, we have co-located multi-instrument observations. So basically, we are having measurements on convection, clouds, aerosol, microphysics, moisture, precipitation, and land surface. So that characterizes the different modes of the convection. So this, even though there are many pictures and text here, so this basically describes how do we estimate the rain type classification and how do we estimate the convective organization in the observations. So So basically, we are using the C-band dual polarization radar from the ART facility. It has a mesoscale coverage. So it has a good coverage to actually have a surveillance of large convective systems, which characterizes the convection and the organization. And the high resolution data at every 6 minutes and 1 kilometer resolution, we use this data to classify the radar echoes into different range types, like convective, stratiform, mixed, isolated convective core, isolated convective fringe, based on the intensity and the texture algorithm. And the output of that range type classification, we had fed it into the different clustering matrix. So clustering matrix, it actually identifies the convective objects and it estimates the how they are aggregated or how they are clustered within the radar domain. So it measures the strength of the convection and its spatial distribution. So among many indices, I'm just for presentation showing the simple cloud aggregation index. It's called as a SCI. So basically, there are two scenarios here. The one scenario which has a less clustered and small size cloud elements. And in the another scenario, we have more clustered and larger size clouds. So this index actually provides the state of the atmosphere, whether it is less aggregated or more aggregated, depending on the number of convective elements and the geometrical distances between different convective objects. So as the cloud organizes, as the convection organizes, the convective element and the distance between the individual clouds would decrease. So this is how this type of indices actually estimates the amount of a convective organization. So it gives the quantification in numbers. So one side is we are estimating the convection in the observation, and similar way we are estimating this type of organization in the model simulations. So this is a rainfall time series during 2022. And here we can see that there are periods of active convection. Also, there are periods of convectively suppressed periods. So if you see, there are major peaks here. So major peaks in the rainfall accumulation are well matching with the peaks in the stratiform occurrence, because that's how the stratiform clouds, because they are the prime contributors to the volumetric rain. And there are suppressed periods when we have the less rainfall, and that's mainly coming from the isolated convective activity. This is the mean diurnal cycle of rain, different types of a cloud, like a stratiform cloud or convective. And there are two peaks in the rain, one occurring at 14 hours and then the other occurring in the dawn to the morning hours. And if we compare the occurrences in the stratiform cloud and the convective, they explains the peaks in the rainfall. So peak in the convective objects occurs at 13 hours, whereas the stratiform clouds peak during the midnight to the early morning hours. So these are the observational evidences for how does the diurnal cycle behaves in the core monsoon zone, and then it produces good observational data sets. So from a given rainfall time series, we identified the days when there were heavy rainfall. Okay, so one of the event of 22 August, it produces very extreme rainfall of say around 293 millimeter. And then we selected this case for comparing the convective organization in the radar observation with the model. Okay, so there are animations from just to show what does the satellite provides and what does the ground-based observation provides. So satellite provides very large scale features. There was a deep depression that formed over the Bay of Bengal and it moved into the central Indian part. Whereas the ground-based radar provides the mesoscale features. So we can have the deep, intense convection, and we can see that there are families of convective cells. So they are organized in the space and time to produce spatially broad convective systems. Okay, so you can have the reflectivity animation as well as these rain types. So for this case, when it produces extreme rainfall, we tried to see how does the model behaves in getting these features, and how does the organization takes place, and what are its spatial structures. So then we perform one simulation experiment. It has a 3 domain. The innermost domain is encompassing the radar domain, and we performed the simulations. And what we did, we estimated the rain type classification and the convective organization indices similar way. Similar way means so that because we want to compare the rain type classification and organization in the observation and the model. So there is a apple to apple comparison. So these are the example scenes of convection for different types, like isolated shallow cells, small clusters of convection with limited stratiform. This is the squall line. You can see a nice squall line is here, which has a associated stratiform area. And this is a widespread stratiform where the convection really organizes. So the top panel shows the observed reflectivity, whereas the bottom panel shows the simulated reflectivity. There are noted similarities and differences in the observation versus model. One noted similarity is that when the convection really organization, you have the omnipresent stratiform structure. The full domain is covered by the stratiform cloud. So that is captured. Obviously, there are certain differences also here. Then we tried to see as a function of maximum rainfall, how does the different rain types evolve in observations versus model. So the black line here is the time when the maximum rainfall there, and then 24. Yeah. So this is the time when the maximum rainfall occurs, and 24 hours before and 24 hours after. And we have actually the convection organizes in the 2 phases. So the phase 1 is the 24 hours before the peak rain, and the phase 2 is the 24 hours after the peak rain rate. And by seeing all this plot, we can definitely see that there is an increased occurrence of all rain types in the phase 1. Whereas the phase 2, there is a decrease occurrences that is well captured in both the observations. Definitely this, I just wish to say that the scale on different, the model and observations are different here. One important point, what we observe that even at a very high resolution, models still overestimate the convective clouds and underestimate the stratiform occurrences that is clearly identified here. And we can see that there is a signature of a organized convection in terms of a broad stratiform. Then we move on to the how does the organization matrix behaves in observations and in comparison with the model. So the top panel shows the observed rain versus model rain, and then there are the elements of this organization index in terms of a convective element n. The D0 is the geometrical distances between different convective elements, and SCI is the indices, which varies between 0 and 1. So the smaller the SCI, that means that the more convective cluster happens, whereas the larger SCI, it shows that there is a less convective clustering. So if we see that in the phase 1, there is an increase in convective elements. So that is observed in both the data sets, radar observation as well as the WRF simulation. Whereas in the phase 2, as the convection become more aggregated, it gives smaller SCI versus larger SCI. So the phase 1 has a larger SCI, phase 2 has a smaller SCI. So essentially it tells that as the cloud organization, the convective element and the distance between the individual elements decreases. That means that the broad stratiform is formed. So once the organization takes place, there is a very less chance for new convection to form. It only just expands in the horizontal direction. And then there is a lag of 4 hours between what observation says and what the model says. But here the point is that we are not aiming for having the best simulation, but just want to know how does model able to organize the structures. Okay. Then we want to know how the depth and the internal vertical structure of a different rain types looks. See, the top panel shows the contour frequency of altitude diagram of radar reflectivity for different rain types: convective stratiform, mixed, isolated convective core, and convective fringe, whereas the bottom panel are from the WRF. So one important point that all rain types and for the heights below 5 kilometer, we can have the reflectivity structure. It reasonably matches with the observations. But in the model, the vertical extent, you can see they are much greater than the observations. Okay. In fact, here, you see these are isolated convective core and convective fringe. These are the shallow and isolated convective, but model still has a vertical extension, even though it has a smaller occurrences. Okay, then we try to see how does the vertical velocity in the model behaves for these different rain types. So the figure here, first one is the convective, stratiform, mixed, and there are other types. So for a convective cloud, we have the distribution is broader, which has all the updrafts and downdrafts. So that is simulated well by the model. And the main characteristics that the peak updraft is at of the surface. So it is above the surface at 5 kilometers it is peaking, and then it decreases in the higher altitude. In the stratiform cloud, that distributions become narrower. And we have the weaker downdrafts that are associated with the downdrafts, the precipitation falling in the lower troposphere. And then there is a weak updraft is there in the mid troposphere, because these are the MCS type of convection, which has an inflow in the mid level. So that is again captured here. Isolated convective core, the maximum updraft is just very close to the surface. That's why the vertical extent of the actual convection lies in the lower troposphere. But still, for all rain types, the vertical velocities are overestimated in the higher altitudes. And then we tried to do one experiment by running the cloud resolving model radar simulator. This is how we want to convert the WRF model variables into radar observation, because simulated reflectivity is not the prognostic variable. It assumes that it has a S-band frequency. But since we want to compare with the C-band frequency, so this type of experiment actually allows how does the hydrometers simulated by the model are seen by the C-band frequency. So it allows the direct comparison between the model outputs and the radar observations. So for sake of presentation, I just compared the radar reflectivity from CR-SIM with the observation, and then it really improves the vertical structure, the median and mode of the reflectivity, particularly the vertical extent that is overestimated. The reflectivity, simulated reflective structures are over simulated. That is improved here. You no longer see these overestimation in the reflectivity. The structure also is quietly reproducing. The melting layer structure in the stratiform cloud, that is also improved here. So as a summary, as part of this study, we use the convective matrice. There are different convective matrices to estimate the strength of the convection and their spatial structure during heavy rain events. This matrix actually measures the degree of organization for each snapshot of the value. So that's the advantage, because radar provides very high resolution from one frame to another frame. How does the organization has evolved temporally as well as spatially? And then it provides different metrics also. These are the different microphysical structures we can get from dual polarization radar. If you see the phase 1, we have the deep convective clouds, cumulonimbus clouds, and in the phase 2, we have the stratiform melting layer signature. So the idea here is to use the art observations for improved process understanding, as well as using these observational metrics for evaluating the model performance. Like, for example, how does the convective clustering behaves in the model? There are other presentations from the students. They have used the radar observations. So they are on the last day. So Harshad will give more quantitative results from the convective clustering. Ashruba will give the polarimetric radar tracking of how does the convection initiates and what is the upscale growth of a convection that happens in the monsoon core zone. And Manisha will provide some new results from the polarimetric signatures of this MCS. Yeah. Thank you.
Much. Time is running out, but we can access only one quick question. Yeah.
Oh yeah. So now you've got this nice database of convective aggregation.
Yeah.
Do you plan to look at maybe what synoptic scale conditions lead to aggregation? Because obviously we know shear is important in the monsoon. There's a lot more than just vertical wind shear.
Yes, yes.
Yeah.
Yeah, that would, because whenever the convection aggregation takes place, so the large scale atmosphere, which is away from the convection, is a convection free area. So there is a positive feedback between the large scale and the convective organization. So there are some plans to see the interaction between the large scale and the convection aggregation state.
Great, thanks.
Yeah.
Okay. Thank you so much. Okay, let's move on to the next speaker. Thank you so much. This speaker is will be online, right? So please prepare for that. Next speaker is Professor Fumie Murata from Kochi University, Japan, and she will present online. Her title is the validation of the rainfall distribution by spaceborne radars over the complex topography of Southern Mega Plateau, India. Murata, please, is yours.
Can you see my slide?
Yes, and we can hear you. So, yes, please start.
Thank you. Okay, my name is Fumie Murata from Japan. I would like to talk about validation of rainfall distribution by spaceborne radars over the complex topography of Southern Meghalaya Plateau. So, our group has been installed and operating around 40 rain gauges over the northeastern part of the Indian subcontinent. And once a year, we visited these rain gauge stations and maintained rain gauge and data collecting, and keep the quality of rainfall data. And in this study, we are using this data to validate the spaceborne radar data, such as TRIM-PR and GPM-DPR. As you know, these spaceborne radars are observe the global precipitation and improve the quality of the rainfall data sets. But there are many estimation errors, so the validation is with east observation data is important. So this is a result of the validation, and we divided the rain gauges into 4 regions, both plains and mountainous area. And the result is different by satellites and versions. And this is a result of pre-monsoon season data. And this data shows trim PR, both trim PR version 7 and trim PR version 8, and estimate the rainfall over northeastern part of the Indian subcontinent. While the GPM DPR version 6A underestimate the rainfall only in Meghalaya, the mountainous area. But the GPM DPR has still not sufficient data, sufficient number of data, so we need to continue the validation. And we also deployed the distro data, 5 distro data over the northeastern part of the Indian subcontinent. And these stations include the electric power conditions sometimes unstable, so we use the solar panels, solar power system to operate these distro. And we use these distro to validate the raindrop size distribution parameters of retrieved from GPM DPR. And this is a result of the validation. And upper panel shows the GPM DPR retrievals data, and the lower part is distro data. And horizontal axis shows the mass weighted drop diameters, and the vertical axis shows the normalized intercept parameter NW. And if we can see the GPM DPR retrievals has too little number of small drops for orographic shallow rains, and also too much number of bigger drops for drizzles. And also too much NW values for intense rainfalls if compared with disdrometers. And our observation field is located in the very complicated topography area. And also it includes the famous stations for heavy rainfalls, Cherrapunji and Mount Seram, which are located in the southern slope of the Meghalaya Plateau. And left figure shows the rainfall distribution, climatological rainfall distribution based on trim PR by Hirose and Okada 2018. And we can see the rainfall area is located to the south of the 1,500 altitude, that's the south of the high elevation area, and there is steep slopes. if we see it in detail, the Cherrapunji and Mauseram towns are located on the plateau, but the heavy rainfall observed by spaceborne radars are located in the valley. So there was some difference between the observations. So we analyzed the reason of the difference. Before showing the results, we show the shepherd of reflectivity of heavy rainfall area in Meghalaya. And the left figure shows the convective rainfall, and right figure is a stratiform rainfall. And if we compare these shepherd figures from other regions, this feature has very similar to the rainfall in Himalayas and also in the Papua New Guineas. And also there was some similarity with Western Ghats and the Myanmar coast in that it includes many shallow convections. And this is rainfall distribution only over the heavy rainfall area, but we divided the data into near nadir data and off nadir data. And we found that the near nadir data has a high probability of detection and false alarm ratio, the higher POD and lower false alarm ratio than of nadir data. So in this region, the near nadir data has better performance. And also we can find the near nadir data shows more clear contrast between valley and over on the plateau. And this is the vertical. So we used the only near nadir data, and we show the vertical profile of rain rate. And left figure is the profiles over on the plateau, and the middle figure shows the profiles in the valley. And we can see clearly the heavy rainfall is more heavy rainfall is observed in the valley. And also this heavy rainfall has more higher precipitation top height. So, and this is a vertical profile of GPM DPR radar reflectivity. And the only in this is a rain gauge matchups. So the red color shows the rain rate was observed. More than 80 millimeter per hour rainfall was observed in the ground. And orange color shows more than 50 millimeter per hour rainfall observed by rain gauges. And we can confirm the heavier rainfall has higher precipitation top height. So, and higher, if the precipitation has higher rainfall, higher precipitation top heights. So the ground clutter must be reduced. So now we conclude that this contrasting rainfall distribution between on the plateau and in the valley may not be an artifact from rainfall estimation errors. So this is a summary of my presentation. Yeah, thank you so much.
Thank you. Thank you, Professor Murata. Any question, comment, quick one? Yes, please.
Just something that caught my eye early on. You're doing this in Cherrapunji, the rainiest place on Earth, and you're powering your disdrometer with a solar panel. How is that possible? Oh, that's not gone through, has it? Do you want me to ask again? Can you hear me? Hello? Yeah, I think you're muted.
Sorry. Yeah. Yeah. Sorry. Yeah. Okay.
Okay. Yeah. So you're in Cherrapunji, the rainiest place on Earth, very thick cloud cover, as you've shown. How do you use solar panels to power your disdrometer? Do you need like a backup power supply, or have you got big batteries, or is it just a really low power load?
I see. Thank you very much for your question. So actually, the rainfall in the Cherrapunji area has a clear nocturnal rainfall. So rainfall dominate in the night time. So in the daytime, sometimes daytime we can get the enough solar power. So previously we thought it was difficult, but now we realized we can get enough power for solar power system. We don't use not so much big batteries.
Okay, great.
Yeah. Thank you so
Yeah,
much.
thank you.
Okay, since due to the bad time management, we are behind the schedule about 30 minutes, so we should take a break right now. So the next speaker will be first for the next session. Is it okay? So I don't know how many minutes we can take a break. 20 minutes or 10 minutes or something? 20 minutes. Okay, yeah.
Excuse me, here is the announcement for the ECR session. As you may find in the agenda that in Wednesday afternoon from 4 p.m. to 6:30, there will be a dedicated ECR session for the early career scientists. And we want to encourage interactive engagement for this session. And for the early career scientist who has registered for this session specifically, please stay in the front stage for 10 more minutes so we can answer some of the questions if you may have, and it will be a chance for you to meet with other members, same group that are assigned with you at this time in advance of the session. And for some of the ECRs, if you're still interested but haven't registered, it's okay. Stay with us and we can put you into groups right now. Okay, thank you.
Thank you for the announcement. Now I'd like to thank session chair, Dr. Kuniya Yoniyama, for chairing the session. And now I'd like to request Dr. E.N. Rajagopal, IITM Pune, to kindly present the memento to the session chair. Thank you, sir. Now we will disperse for tea break, arranged at the basement of this building and the guest house. And we will gather again here for the next session, session 4, after 15 minutes. And I have a short announcement. Anyone has query related to the registration, you can approach the registration desk during the tea time. Thank you. Yeah, okay. Okay. One notice, announcement is there. The last talk of this session will be shifted to the next session, session 4. Yeah, thank you. Hello, Praful.
Good morning, all, and welcome after the tree break. Now we will move to the next session, session 4, field experiments and multi-platform measurements of precipitation over monsoon region. The chair of this session is Dr. Hindumati Palanisamy. She is scientific officer in WCRP, and I request Dr. Hindumati to kindly chair the session. Please, ma'am, come on the dais. Now I request the session chair to please proceed for the next session.
Thanks a lot. The first talk is from Dr. Cuneo about the Jamstack Monsoons Research Platform. Dr. Cuneo, would you like me to give you a warning 2 minutes before the...
Okay.
Okay, that's perfect. Okay, thank you. Thanks a lot.
Hello, everyone. I'm Kunyi from Jamstack again, and forward. Okay. And today my talk is very simple because it's introduction of our research activity using this vessel, and the latter half just for the advertisement of our new research vessel. Okay. I'm not sure that how many participants are familiar with the SIP observation or especially for our research vessel Mirai, because we use this vessel to participate in any field campaign, international field campaign. But anyway, this shows the basic figure that our research vessel Mirai had various atmospheric and oceanic observation tools. The basic and major tool is the C-band Doppler radar, as well as the radio sounding system for atmospheric measurement. And also that's for the oceanic monitoring oceanic condition, we usually use the CTD, conductivity temperature depth meters. In addition to that, of course, we measure the ocean current, and also we monitor the ocean, the atmospheric surface condition. For example, when we sea surface temperature is one of the key measurement parameters to be observed. But maybe you know that usually from the ship, we take the water at the bottom of the ship, then measure as and we identify as a sea surface temperature, but usually it measures about 5 meter depth or so. But in particular, in the tropical area, the real skin sea surface temperature is quite different, in particular in the solar fine days. As you can see from this right figure that in the fine daytime, there are strong differences between the skin temperature and the 5 meter depth temperature. So we deploy the thermistor from the bow of the ship and to measure the about a couple of centimeters temperature like this one. And also, Mirai, our research vessel Mirai has a length over the 100 meters, a relatively large vessel as a research vessel. And it, in other words, it means that the iron mass. So it means that during the daytime, it must be warmed. And in the nighttime, it will be cooled compared to the standard ocean condition. We want to measure not for ship's temperature, but ocean temperature. So for example, when we the bow mast, we deploy our surface meteorology system. But when we conduct the stationary observations, we do not station. Usually, to obtain the upwind, we always cruise, even during the stationary observation, we cruise upwind to avoid the influence of the sea. And as I mentioned, that the Mirai is a large vessel, so we have a large deck spaces. We can deploy many instruments over the deck, wooden deck. So mainly, then we often deploy the LiDAR system to upward. Vertically pointing radar or LiDAR is very suitable to equip on the Mirai. And in addition, we sometimes deploy the long big balloon from using these big spaces to measure the some parameters. For example, this is one example. we had a cruise to the equator. At that time, my colleague joined this cruise, and he conducted the special radiation observations. Special means that he used a big balloon, 3 meter or something diameter, and attached several sensors, including ozone and high accurate water hygrometers. And you can see, for example, this shows one example that some sounding capture the high ozone value around 80 kilometers height. It means that apparently this is not a subside from upper side or upward motion. So actually, these are at that time he want to know that such a material transport between the middle latitude and tropics, maybe it should be associated with the monsoon gyres. Indeed, this figure captures such a evidence. Such a high ozone came from the middle latitude, like this one. Anyway, since Mirai has a wide deck, we can conduct various observations like this. And this map shows our recent cruises, which aimed at the studying the AC interaction. As you see that mainly my group's focus is we have two missions. One is the boreal summer interseason oscillation. It's shown by the warm red colors indicated by red colors. And the other is the more longer time period phenomena, such as the ENSO, El Nino, and such an event. For that purpose, we need to monitor the warm water pool over the Western Pacific area. So as for the first target for the BC or boreal summer interseason oscillation, we conduct a station observation using research-based Mirai. And as for the longer time period, of course, we use a Mirai, but we deploy a mooring system to monitor the longer period. So from that, I will show several results obtained from these two cruises. First one is the for the intensive observation for the interseasonal oscillation related to interseasonal oscillation. The first example is showed that already my colleague Satoru introduced some results obtained from this international field program YMC years of the maritime continent. I do not talk about this in detail at this moment, but anyway, we started such a field campaign from 2017. And this YMC consists of the two field modes. One is the intensive observation, focusing on specific topics such as diurnal cycle rain or MJO and of course monsoon, one of the key observation target. The other is the provision from the long-term data set from the local met agencies. The right list shows the conducted or planned intensive observation. But unfortunately, due to the COVID-19, the several projects have been canceled. But for us at JAMSTEC, my institute, we are lucky because we could conduct several field campaigns during this period. That shows that the red panel shows the we conducted observation in the off the Sumatra Island. As Satoru already mentioned that, and the other project is that we aimed to study the boreal summer interseason oscillation. This is so is shown by blue colors. Right. From that, I will show some example from the results taken by this campaign. In mid-summer of 2020, we conducted the observations using a Mirai, this Mirai. You can see that here is a track, and also thanks to the help from the local maritime continent med agencies, they conduct the enhanced radiation sounding at the Philippines and Palau and Micronesia, and to monitor the large-scale atmospheric condition. But unfortunately, you know that it was conducted just in the middle situation of the COVID-19. At that time, we cannot deploy our observation system by ourselves. And Mirai should conduct observation by alone. But even such a situation, when we deploy the Mirai, we also deploy the several autonomous surface vehicle as well as the monitoring system around the Mirai. But by deploying this system, we form the small observation array. And even one research vessel without any collaborators outside any country, but we can form the such an observation network, although the small one. But and also you can see that this circle indicates the range of the Doppler observation. So we can compare to any data set obtained by autonomous surface vehicle or monitoring system as Doppler system or more Mirai. And by deploying several ASVs around Mirai, we can obtain the data, not only those points, but also the gradient and even for calculating the Laplacian. From this Laplacian of the sea surface temperature, for example, we can know the convergence at the surface. So I will not talk about this, explain about the right panel, but anyway, by deploying several ASVs, we can calculate the convergence as a surface, and we can compare to this their value with convex activity observed the Doppler radar system. Actually, this result already shown in the previous Monsoon workshop and already published in the Monsoon special issue. So you can refer this later if you are interested in. Okay. And also, when we deploy the ASV, recently we already attached the GNS antenna to measure the water vapor. You know, maybe I think many of you are very familiar with that. Using such a GNS dataset, we can derive the total amount of the water vapor. So indeed, we did, and we confirmed, and we established such a technique. And based on the intercomparison with radiation sounding or any other measurement system data set. So we can obtain the various data set. If we deploy the such as ASV, we can obtain not only such meteorological data, but also the upper air condition as well as the ocean condition, because we also measure the using current meter or some temperature and salinity sensor equipped on this system. And the second point is another target is as I mentioned, the long-term phenomena such as ENSO. In such cases, only one cruise cannot capture any detail, so we deploy the monitoring system on longer period. Currently, we deploy the one monitoring system from the December 26, 16, so almost 80 years or so. At the 13 degree north and 137 degree east, just off the Philippines. You can see from this sea surface temperature distribution, we deploy this more here because we want to know the northern edge of the warm water pool to monitor because it's such a variation over this area directly affect to the meteorological weather and climate. You can see some configuration of our system. In addition to the surface meteorology, we measure this temperature and the salinity down to the 300 meters. Okay. And of course, we deploy such a data is all even now that anyone can access to our data site and obtain the data. In addition, we contacted with the JMA and we send our data set through GTS. So our data set, even now, they use for the weather forecasting, I believe. Since we deployed for more than 8 years, my current already started using this over the monitoring data set. This one example. For example, this today I will only show explain about the left panel. Anyway, left panel show the time series of sea surface temperature. Since our monitoring system capture every 10 minutes, but this time we converted every 1 hour hourly data set. But anyway, we can obtain the high frequency frequency data set like this. You can see that only in 2018 and 2019, abrupt sea surface temperature increase can be found with strong diurnal cycle. But other 2 years did not show that gradual increase of the sea surface temperature with small diurnal cycle. And in particular, if we compare this data set to the BCSO mode. BCSO mode can be defined using a satellite-based OIR data set. You can see, look at this bottom of this, each figure show the, when we observe the any active or any mode of the BCSO, you can see that then we found such a abrupt increase of sea surface temperature with strong down cycle found only those 2 years in early middle May. In such cases, BCs are also active. So from this comparison, we can expect at this moment, we do not know the cause or any mechanism. However, at least this shows that the tight relationship with the onset of the BCSO is tightly related to the strong diurnal cycle of sea surface temperatures. So if we want to know the real onset of the BCSO, such a large-scale system, we also need to know about the more detail, including a diurnal cycle, right? That is very indicative one. But anyway, by obtaining such high frequency data set using a more longer period data set, that is why we can obtain such a new idea. And also, our buoy is recognized as one of the key ocean site observation site. I'm not sure that you are familiar with or you heard about Ocean Site. Ocean Site is the international global network for the long-term measurement of the at several sites. Left panel show the black box indicate the especially we should measure these ocean surface heat fluxes to understand the weather and climate system over the entire globe. And you can see the our system, mooring system is recognized, identified one key site for tropical Western Pacific area. It means that we need to, or at least we want to continue deploy our system for more years. And so it means that you can also obtain, you can use such a data set for more study for the more longer term period phenomena. Okay, and another, this shows the another information because the very recently, my current also conduct the another cruise. They went to the dateline the equator. At that time, they again formed the small observation array deploying wave radar ASV as well as the mooring system to measure the that time. They want to know the variability and behavior of the eastern edge of the warm water pool. But anyway, the key point of this figure or observation is that after the observation, of course, the Mirai returned to the Japan, but at that time they left the mooring because the this buoy will be recovered by U.S. NOAA maybe 2026 because the NOAA is planning to conduct the another cruise. They call it TPEX, T-Post Equatorial Pacific Experiment. TPOS means that the Tropical Pacific Observation System is another project. But anyway, this TPEX is expected to contribute to GPEX already introduced this morning. So our observation is also contribute to the such GPEX project through the collaboration with US NOAA, like this one. Okay. And so far, our research vessel Mirai conducts many cruises, and the past 27 years, sea cruise the over 1 million kilometers. It's almost 29 laps around the world. But this by the last summer, so I think the we will lead to the 30 laps around the world. Within this year, but unfortunately, our Mirai is scheduled to end her mission by this coming December. And so instead, we will have a new research vessel. Okay. Our new research vessel is named the Arctic Research Vessel Mirai 2. And from this name, you can easily understand that our big differences is the new vessel will have a capability of ice breaking. And for example, ice breaking capability, the 1.2 meter depth, what is it, thickness of the ice. If the covered by ice with the 1.2 meter thickness, sea can cruise by speed at 3 knots or so. And but you can see the from her size, her length is almost same as the Mirai 128. Compared to the standard icebreakers, I think this is not a big one, rather small one, because based on the experience of our Mirai, we feel that Mirai is very convenient to conduct observation. And our research construction team tried to new vessel to be like a Mirai, but another new capability of the ice breaking. And the new vessel have we can have many participants, researchers comparing to the Mirai, okay, like this one. And also they adopt the new dual fuel diesel system. It means that they use not only the heavy oil, but also LNG, because we should be earth friendly using LNG compared to the heavy oil. Much emission of the CO2 should be reduced compared to the Mirai. And this shows the some schematic diagram of the major function of the facility of Mirai 2. We can see that, of course, the basic measurement system, we equip the surface meteorological sensors as well as the radar sound and the radar system. As for the ocean observation, the CTD or current meters and some graph, surface monitoring system. In addition to that, you can find several figure for the drawing, like in addition to that, several groups try to deploy the aerial or ocean underwater drone system to measure the over or under the ice system. But of course, I believe that such a system can be used for the other region. And also we using with the balloon carrying the some samplers, so to measure the aerosol like this one. And also this shows the general arrangement looking at the light side, or actually we call the starboard side. Anyway, you can see the we, in addition to the wide observation deck, we new vessel is equipped with the helicopter deck. Yeah, of course, we do not equip the helicopter always. Just in case, emergency cases, we prepare such a spaces. In other words, we will have a huge area for the, and you want to conduct the observation using this vessel, there is a possibility to deploy a lot of the observation tool over this area. And in addition, I'm not sure that moon pool is very popular English or not. Anyway, moon pool means that in a space, a hole inside of the vessel. From using this hole, we can deploy a system inside the ship. It means that even after rough conditions, we can conduct the city observation, or we can deploy any unmanned vehicle from inside from the vessel. Okay. And this shows the schedule for the construction. The already 3 years has already passed from the when we started after we started the construction of the new vessel. But you can see that just tomorrow, sea will be launched. At this moment in the shipyard, but even now, even tomorrow, sea will stay in the shipyard, but sea will be launched. And after that, we equip the many observation tools, and we conducted the various sea trials. And November 2026, it is expected to deliver to Jamstack. After that, we will start to the training cruises, and it will be used from, and first cruise to the Arctic Ocean is scheduled to the mid-2027. And 2028, it is expected we can use not only to the Arctic Ocean research, but also for others. So, and the point here is the, although the official name is Arctic Research Vessel, and as I showed that she has the capability of the ice breaking, and such a many meetings have been held to discuss the how to use such vessel for the Arctic research. Certainly, Arctic research is a first priority of this vessel. However, the detail of the management of this system of the vessel, as well as the some other point, is not being fixed yet. And in addition, it is highly expected we can use this vessel for other topics in other regions. Actually, that is the reason why I'm here, because from their name, many guys think that, oh, new vessel come, but they are only used for the Arctic research. Honestly speaking, even the Jamstack colleagues, including me, at first thought, but it's not. It can be used, of course, the monsoon research, we will. So that is why we want to collaborate, we want to discuss about the possibility of using this vessel, because since the research already started to the discussion about the international use, when we use for the monsoon research, of course, the international coordination or collaboration must be mandatory. That is why we need of course, we developing our idea, but we want to discuss with other monsoon researchers and how to use this vessel more effectively, efficiently, and also to produce the much new result from using this vessel. Okay, that's it.
Yeah, okay.
Thank you so much.
Thanks a lot, Dr. Kunio. Time for one quick question, please. Yes, Dr. Krishnan.
Yeah. Increase in 2018, 2019 was very rapid increase.
Yeah.
Also, many tropical cyclones that formed in the Philippines. So you see any relation between these two?
As for the
2018, especially many cyclones formed.
Yeah. Actually, basically ship should be avoided from the condition of the tropical cyclone. So we do not directly discuss. But of course, after the influence of the after the tropical cyclone passed by, and such a situation completely different. In such cases, we of course some guardians compared to the such a situation changes using such a surface temperature data set as well as the such a TC's behavior. Yeah.
Thank you.
I'm sorry.
It's fine. Thanks a lot.
Please wait for a moment. I request Chair to present a memento to the speaker, please. Thank you, sir. Thank you.
Our next invited talk is going to be from Dr. Pandidurai from IITM Pune on the atmospheric research testbed. Thank you.
Good afternoon. Thank you, Chair. You can remind me if I exceed time. So I'd like to introduce this facility, Atmospheric Research Testbed, which is a unique facility in the tropical core monsoon zone for process studies. So I would like to acknowledge our entire team, IITM, Atmospheric Research Testbed teams. There are several instrument PIs who have been contributing to this project across the institution from different groups. Now, the outline of my talk is so what is the importance of core monsoon zone and why do we need such a test bed for process studies, and some glimpses from monsoon campaigns, and I'll summarize. I think many of the research topics are presented in the conference. Earlier, one of my colleagues, Sachin, presented about the rain tip classification and convective clustering using a dual pole C-band radar. Also, there are many posters and presentations are there from our project. See here, if you see the summer monsoon season, the monsoon trough over the central India, which comprises the core monsoon zone, is one of the important semi-permanent systems of regional climate system. And you can also look at that there are several synoptic scale disturbances such as monsoon lows and depressions frequently pass over this core monsoon zone. So wherein we don't have observations which will be useful to understand the processes. So that's how this project was emulated. And if you look at the core monsoon zone, the variability of all India summer monsoon rainfall is highly correlated with that of summer monsoon rainfall over the central India. So if we can improve the prediction of variability in central India or core monsoon zone, so this will also should project into larger scale predictability. So considering this importance, an atmospheric research testbed in central India was established by IITM. It is near Bhopal city, about 50 kilometers northwest of Bhopal city for better understanding of processes governing monsoon convection. This also is a permanent observation facility and have a wide range of remote sensing and in situ instruments that will provide continuous observations of convection, clouds, microphysics, aerosol, radiation, and land surface properties. Also, if you note, these core monsoon central India is also a hot spot for land atmosphere interactions. So these data sets will provide a key resources for validating cloud resolving model and GCMs using both statistical and process oriented approaches. The objectives of this project is to realize a huge atmospheric observational facility in the core monsoon zone, to understand the atmospheric processes in the core monsoon zone using state-of-the-art observational system, and also to organize intense IOPs along with the weather prediction model runs so that we can test hypotheses and improve the physical parameterization schemes in the models which are related to convection and land surface processes. And the other component is the outreach, training, dissemination of RCA data sets. So these data sets will be used to test, validate, constrain the numerical models in improving the predictions of intense convective storms and high impact mesoscale weather events. So this is the core monsoon zone, and this facility is spread over 100 acres of land. So wherein the instruments were deployed, and some of the facilities are still coming up. The scientists, technicians, accommodation, etc. And you can see that there is a dual pole C-band Doppler weather radar and the 72-meter flex tower and instrumentation laboratory are all set up here. And these are some of the pictures of the instruments set up already in this facility. So ranging from the precipitation and cloud radar and radio sound. So during campaign, last monsoon campaign, we had 4 soundings a day, and we have instrumentation laboratory, and there are several radiation aerosol observing systems deployed already. And this is the history of this facility, how it evolved from 2021. So we started with a radar and microwave radiometric profiler and some disdrometers, ceilometer, etc. Then we added further, and presently we have about 17, 18 observing systems. So in future, in coming year, we are going to add SODAR for boundary layer wind measurements and wind profiler for vertical profile of winds, including the vertical winds, and LiDAR, and W-band radar, which is cloud radar for non-precipitating clouds. And we are going to set up a rain gauge network around this site. And also we are planning to have 5 mesonet sites, which will have both soil moisture as well as the eddy covariance measurements in the atmosphere to address the land atmosphere interactions. So this is how the facility is growing now. Idea is that how these observations will be used to improve the numerical weather prediction model or any models. So this idea is that people can use these observations into model in a single column version, and that's what I think already some efforts are already underway to use these data sets to improve the modeling processes. So this is a typical passage of a convective storm. During monsoon, I already shown that there are a lot of synoptic systems which form in the head bay will move into this core monsoon zone. And this is how you will see the heavy precipitation systems during the monsoon season. So like a squall line type of features we will see. See, one such event which you can notice that there is a heavy rain event which occurred in 22nd August 2022. So which you can see from this is IMD GPM merged rainfall data sets, and the rain categories are classified as per IMD criteria. So the 22nd August 2022, you can see a extremely heavy rain event, which the in situ measurements at the observatory recorded about 240 millimeter, and you can see that GPM emerge. So the same case was already discussed by Sachin, and he classified into the convective storm clustering and tried to address the rain type classification also. So here, if you want to look at the precipitation microprocesses, so what are different processes happens? So we can use this radar has a polarimetric capability. So these are about 3 days time series of vertical profiles of polarimetric radar variables. What you can notice is that initially you have convective, then there's a stratiform, and you can see there is a well-defined signature of a melting layer. And there are other processes which if you look at the complete stratiform case, there is a sagging of bright band, so which is melting layer, so which shows that there's a dominance of riming ice processes above 5 kilometers during this window of time. So then there is a aggregation which plays a major role in hydrometeor growth between 5 and 8 kilometers during 0 to 2 UTC. And there is a presence of warm, shallow rain during this time window of E2. So we can understand the precipitation microprocesses using the polarimetric radar data sets. So also we'll try to look at how many there are. So if you look at the spatial climatology of monsoon low pressure systems, so you get the histogram and the frequency of occurrence and how it starts moving. So from the radar domain also, if you look at the frequency of extreme rainfall events, so you will see such a similar southeast to northwest direction in the radar domain. So here, if you look at the storms or MCS, mesoscale convective scale in the radar domain, so the storm area increases, the intensity of the storm also, you can see that it gets increases. So if you look at the histogram of storm top heights, so you'll see a bimodal distribution, primary peak at about 7 kilometers, and the secondary peak is about 10 kilometers, which represents the deeper convective storms. So we also try to see how the convective storms and their association with the lightning data. IITM also has a lightning location network set up over entire India. So if you look at the radar observed storm frequency and if you look at the lightning stroke density over this radar domain, so you can see a similar pattern, and the diurnal cycle also have a similar variation. In the afternoon hours, you have a higher cloud to ground and intra-cloud lightning flashes. So this is one such time series in the last monsoon. So we try to look at the daily time series of ecotop heights, 0 dBc ecotop heights during the monsoon season. And so this is as Sachin presented in the morning. So similarly, the rain type was classified into the entire monsoon season, and see that so in the time series of different rain types. So the data sets allows us to quantify the rain types in the monsoon season. So I also just give some glimpses of some observations collected during the last monsoon season. So these are some time series of GPS radio soundings conducted during last monsoon. So almost every day 4 soundings were conducted. At the end of the season, I think there is a lack of some consumables, so I think they limited to one sounding a day. So you can clearly see that the variability and the variability of all the meteorological parameters like winds and temperature, humidity. And we also looked at the microwave radiometric profiler for the 2024. For the entire year, you can see that there is an annual variation of TNRH. It's a remote sensing, passive remote sensing radiometer, so through which you can derive the temperature and humidity up to 10 kilometer. And this is the variability of integrated water vapor and the liquid water content derived from microwave radiometric profiler. So these are the data sets. So in addition, there are radiation and the flux tower measurements, which I am not presenting here. I think there may be some presentations from my colleagues. In addition to this monsoon core test bed, our project also established a couple of other test beds, which is called as orographic research test bed in Western Ghats Mountain to understand the orographic convection and precipitation processes. And also the urban radar network test bed, which is set up in very recently set up in Mumbai metropolitan region, which I think one of my colleague Hari will be presenting in the next subsequently in this session. So with this, I think I'll summarize that this art facility, in core monsoon zone can provide important observations for atmospheric process studies. And further, the observing systems are being added based on requirements from modelers and other user communities. And we are also open to collaboration, and there are already the other departments are also putting up instruments. So recently the DRDO developed LiDAR, which they would like to test it in our test bed. And also some universities are also coming up with their observing systems. I think we are having a system to accommodate the guest users also, so that they can deploy their observing systems, and in turn they can also contribute to the project, and the data sets will be available to them also. So there is coordinated monsoon campaigns are planned in future, as Dr. Kishan mentioned that. So we have been thinking that we think we should replicate the MONEX in the next few years. By that time, I think we will have more observing systems over Indian region to address the not only the precipitation studies. I think there will be other atmospheric process studies also. Especially the precipitation process data sets can contribute to international projects. I think we are already discussing with the WCSSP India. There is an interest, and there are several regular meetings with the WCSSP groups to utilize the observations and improve the processes in the microphysics scheme and all, etc. in the model. And also it can contribute to the GPEX and AsiaPEX efforts under the GVEX and WCRP. So with this, I think I'll stop here, and happy to take some questions.
Thanks a lot. That was wonderful. So we can have time for 2 questions. Maybe the first one, if there is anything online, can we please check? Any questions online? Okay, thank you. From the floor?
Yeah, I'll go first.
Yes,
if
please.
there's anyone else, I don't know. This is obviously a huge volume of new observations. To what extent are they being used? Are they being assimilated in Indian and global forecast models?
Yeah, actually, our reduce on data sets are real-time going to NCMRWF for assimilation. So other the data sets, still we don't have a very good distribution system with the internet lacking in the rural region in that area. So I think we are planning that.
Great.
Thank you. One more question, if any? Okay. Thanks a lot, Dr.
Thank you.
Pandit.
I request the chair to please present a memento to the speaker. Okay, sir.
Thanks a lot. And the next invited talk is from Dr. Tara, also from IITM. And she is going to speak about, please correct me, Kai peaks. Yeah, okay, perfect. Thank you. I will let you know when you have like 2 minutes left to finish your talk. Thank you.
Yeah. Good afternoon, everyone. I'm going to speak about the KIPEX, which is actually Dr. Panditare already given an introduction on our observational efforts. And this is an experiment which is involving both ground-based as well as airborne observations. So actually, there is a big team behind this. I put legacy experiment because it started quite some time ago. So, and the team that was involved in the phase 4 of the experiment, and they have indeed made a significant effort in making this happen. So whatever I am going to speak, it is by them and for them. Yeah. Okay, so the experiment started in 2009 with a specific intention of studying cloud microphysics. Basically, in the first year, we have done the cloud microphysics studies all over India. And you can see in the, I'll use a pointer if possible. Yeah, you can see the number of the areas where we have flown in this particular plot, number of flights we have undertaken. And over the years, we have indeed done several experiments and kind of concentrated in the peninsular Indian region. So the star that you see here, indeed, that is the place where we have done the phase 4 of the of this particular campaign. So the KIPEX indeed stands for Understanding Cloud and Precipitation Microphysics, as well as Science of Cloud Seeding. A little bit of application twist here. So I will indeed demonstrate what we have done in terms of the cloud seeding. It is a scientific investigation, not an operational project. So why are we needing this particular experiment? If you see here, this is from IPCC AR6. We have this particular plot is showing the water scarcity over our region. So this peninsular India is having many places, even 12 months water scarcity in that region. So the circle here, that is our experiment region. And we have chosen this place, Sholapur, as our center. You can see that the monsoon rainfall is also quite less over that region, even though other regions get a maximum, a significant amount of rain in the monsoon. So we investigate the microstructure of the clouds, basically to understand how the rain forms, how the cloud forms, how they are impacted by the aerosol, properties of the aerosol and the thermodynamics, etc. So various topics we have discussed throughout these several years. So today I am indeed going to discuss about the cloud lifetime. So actually the cloud, so there are a number of papers available for you to refer since the start of phase 1. There are many more papers discussing about various aspects. So you may be familiar with the INDOX experiment. Actually, KIPEX is the only experiment thereafter looking at the cloud microphysics. What you are seeing here is culmination of the INDOX and the KIPEX observations with aerosol and the droplet number concentrations. So which is indeed indicating us the indirect effect of aerosols, which play a major role in the, especially here the what we are looking at is the continental clouds, which has been the main focus of KIPEX. So we have measured the drop size distributions, starting with the particle size distributions, aerosol, the cloud droplet, raindrops, and ice particles. I'm not going into details of it due to time constraint. And we have also looked at, this is a number of flights, nearly 40, 50 flights. So throughout the monsoon season, we have conducted. And the color indicates the liquid water content. As you can see, the liquid water content is quite large in these clouds, which are indeed very, very important for the intense rainfall events as well. So our experiment indeed focused first, indeed, we needed to see whether this cloud seeding really works or not. So we have indeed come up with a paper recently, and which is indeed illustrating whether the cloud seeding really works over this region. We have done scientific investigations, including a randomized study, and this has resulted in over 270 samples, which is unique in the world. No other place on Earth has this kind of samples done with an experiment like this. So we have penetrated many clouds. We have seeded many clouds. Some clouds we did not seed. And based on the randomized criteria, and we have come up with the idea for the cloud seeding experiment. So these are some of the aircraft that was used, 2 aircraft we used, and also the regions where we have flown. You don't see all the flight tracks because it is so many flights we have conducted over that 100 by 100 kilometer area around there. And we had also set up a rain gauge network in and around there. And there is an aerosol laboratory, a radar, and various other instruments, just like in any other experiment. So the one very interesting aspect is that all these clouds that we sampled, actually they have this is the mean volume diameter of the cloud sample that we sampled. And also the mean volume diameter of the drizzle, as well as the precipitation size particles. So you see the maximum at the top because most of the clouds we sampled were in the nascent, like in the formative stages. That is the reason why. And most of the clouds we sampled were up to like 9 kilometers. So we were able to get the most convective clouds sample in this case. So our experiment indeed yielded, we have found out certain criteria for for seeding the clouds to get the desirable result. And we have set that criteria, and then we have come up with certain results, and our results showed that there is an enhancement in rainfall up to 18%, which we have published in that paper. So the we also have seen very clear evidence of how the cloud microphysics is changing when we are seeding. Actually, this is an indicator, the drops diameter, actually when the drop size is less than 20 microns, those drops number had increased in the seeded cloud compared to a non-seeded cloud. And also we could see that the drops that are more than 20 micron, their number had reduced, because what we are doing is we are suppressing the rain very close to the cloud base. And then we also evaluated that with the help of radar, because we can look at the vertical structure. These are indeed many clouds, which are almost like nearly 5,000 plus cloud samples we have considered here. So that again shows this is a difference between the seeded and the non-seeded vertical structure. So that again shows an enhancement in that as well. So actually the results of the randomization experiment, indeed we are seeing an enhancement in the accumulated rainfall as well as the mean rainfall. We had samples of 150 seeded and 122 non-seeded cases. So now coming to the point of cloud lifetime, I just want to show that this particular left figure, you please have a look, where this I'm showing the maximum reflectivity of the seeded clouds and non-seeded clouds. The maximum reflectivity of the seeded clouds, the continuous lines, they show higher reflectivity, and the clouds are indeed lasting longer, and they have higher reflectivity at a later stage of their development. But in the cases where the clouds were not seeded, they were raining out very quickly. So, however, we did not see any impact when the reflectivities or the clouds were in the mature stage, like more than 30 dBc. We did not see any significant difference. And I am actually this is a result consisting of several clouds. We randomly chosen seeded and non-seeded. So the result is quite robust here. This is a percentile analysis here, a quartile analysis there. Then what we did is we have indeed taken a specific case study, and we did numerical experiments with that. And this is indeed showing the radar tracking clouds with rain. Like so, then the rain fallen in that area also we have investigated. These star points are the regions where we seeded. Sorry. And the downwind of that area, we could see an enhancement in the rainfall. So we have simulated that, and we investigated how it made more rainfall in the downwind of that area. So then these are some of the, we have indeed used the size distribution of the flare particles. Actually, these are the flares, calcium chloride flares we have used, and size distribution of those flare particles were used in the model to prescribe the aerosols. And this analysis was done with the WRF, little bit modified version of WRF, and then we came up with actually in the seeded area as well as in the downwind area, we investigated the drop size distributions in the control and the seeded cases. So we have seen an enhancement in the drop number concentrations in the downwind area as well in the seeded case. So then basically that downwind area developed more ice particles in the cloud. As seen here, it developed more ice particles in the upper reaches of the cloud. And also these clouds indeed had more graupel particle. That is what is important in this case. Actually, the graupel is formed by freezing of drops. So that is indeed contributed to this enhancement in the rainfall so that we could illustrate with our analysis. And this is again showing the downwind area, how even not only the rainfall, it is also the cloud liquid water increased in the downwind area. So that again we could illustrate, and which model again illustrated that and there is an enhancement in the cloud lifetime. So then we did, actually we were having radio sonde ascents daily. So we have done clustering of those radio sondes and found out what exactly, whether there are, these are the typical clusters that found in the radio sonde profiles of the relative humidity. And based on this, indeed, we have investigated whether there is a lifetime effect, which is indeed discerning, like for the high and low aerosol conditions, we have investigated that. So this is actually, it is quite revealing that this is a new analysis we have done, where right now you look at the blue and the orange color. These are the PDFs of the cloud duration. Actually, we select each of the cloud and which are indeed making some rain based on the reflectivity, and then track them and looking at their duration. We have found that these clouds are lasting longer when they are more polluted in the high aerosol conditions. So not only they are lasting longer, they are also making more rainfall. So yeah, this is a very revealing result. And how do they make this? That is by actually when we have more aerosols or more seeding happening near to the cloud base, actually it is taking part into suppressing the rainfall near to the cloud base and suppress collisions near there. And then since we have a greater warm layer depth, that is from the cloud base to the 0 degrees C, actually these drops have a greater time to grow and longer time to grow and to larger size drops, which indeed crosses the freezing level and lofting above this layer indeed result in more mixed phase processes that we have seen through the modeling study, that we can indeed get more graupel in that layer. So which indeed caused more rain, and the cloud indeed lasted longer because the aerosol indeed delayed the precipitation process. So this, I just wanted to summarize that. The key message is that the cloud scale investigation is done with aircraft, many clouds. And we see that there is an impact on the cloud lifetime as well as the precipitation in many of these clouds. We have tracked them, we have documented this evidence. So this is what I want to say. And also I want to I was little bit going little fast, because I also want to say that there is a conference coming, WMO conference on weather modification in November. If you are interested, please have a look at that. And also there is a mega conference coming in IITM, ICCP conference 2028. So that will also be hosted by IITM. And there is some problem with this font. Okay, it is not my problem. Actually, it has not. There is a problem with the font here. So I also want to shoot this particular slide because Nico is already here. He is actually driving us for this particular WWRP steering group. And we are forming people like P2P project, which is about a team. It's a task team, which is looking at the precipitation and meteorology. So we are, if any one of you are interested, please contact us and involve in the activity. And also we are doing another activity called, which is a International Commission on Tropical Meteorology, which is being formed. And we will be conducting several panel discussions on tropical meteorology. And the panel discussions, where we will collect all the summaries from the panel discussions and will be presenting to BACO 2025 meeting, YAMAS meeting. And our target is by 1st June, we will finish this. And if you are interested in participating, please let me know. Thank you. With that, thank you all.
Thank you so much, Dr. Tara. We have time for a few questions. Yes, Kali, it was first, and you go next. Thank you.
Okay, I'll go first. Sorry, we're kind of looking at each other. Thank you. That was, really interesting. I must be causing some interference. Anyway, yeah, really, really interesting. I mean, my first thought was it looks very similar, the results, which is really encouraging to what I remember seeing in the South African Rainfall Enhancement Program, which is now 25 years plus ago. What confused me was you put up the plots with the stratification, use the signs. What do you mean by polluted?
Yeah.
Because
probably I went too fast there. Yeah, because what happens is if we want to investigate the aerosol impact on the precipitation or the lifetime of the clouds, actually we should first look at the meteorology. Meteorology plays a very major role in deciding. And what we do with the satellite data is we gather all the data and we will make certain statement. That is not really helping us. We have to separate the meteorological effect. That is what we have done here.
Yeah.
We have done, we have looked at the thermodynamics. This thermodynamics belong to the time before our
storm
flight,
initiation,
before the storm initiation. And that indeed tells you that, okay, this is the boundary layer thermodynamic condition in which this storm is there. Okay.
Normally, though, if you have aerosols, they're usually the wrong type. They're more hygrophobic than hygroscopic, and they are the wrong size. So that will produce cloud rather than rain.
Yeah.
So what you're trying to do with the seeding is introduce more friendly aerosol.
Yes.
Induce more rain.
Yes.
So it's an interesting tension between the two. So I'll talk to you later. But it's a really interesting point.
Yeah, we are introducing hygroscopic aerosols. Calcium chloride I mentioned, that they are hygroscopic aerosols. Yeah. Yeah, please. Please ask me more question.
No, not now. Just one last question, quick one, and then we take it for lunch. Thank you.
Oh, okay. Yeah, so I was interested to know how did you ensure a random sample, and how did you check afterwards that it was random?
It was random. Yeah, actually we had a randomization table, and we constructed that randomization table prior to our experiment, and then executed that with certain, I mentioned about certain criteria for the seeding criteria. Actually, this we have established by this particular experiment. Indeed, it started in 2009. But we could do this randomization experiment only in 2018. One was infrastructure, and other was regarding coining the right conditions. How do we know what cloud, which is the suitable cloud? We needed to know that. So the background study was needed that made us to this level where we could select the clouds based on certain criteria and then conduct our randomization table. I'll tell you, actually it is a little lengthy exercise to select the cloud because the pilot and the radar need to be communicated in a particular way in order to indeed conduct this experiment. And it was done in a double-blind manner. Okay. So
I'm going to, sorry.
Sure.
Yeah.
So if we can move this for lunch, I think that would be great. Thanks
Thank
a
you.
lot.
Thank you.
Yeah, ma'am, please wait for a moment. Please wait, ma'am. I request the chair to present a memento to the speaker, please. Thank you, ma'am.
So next, we have a presentation from Dr. Kaustubh Chakravarti on IPEX, the Indian Precipitation Experiment. Dr. Kaustubh, I will let you know 2 minutes before your finishing time. Thank you.
Okay, thank you. Okay, is it visible? Yes. Hi. Okay, this one. Okay, so good afternoon to all of you. So right from the morning, this is a session of the PEX, precipitation experiment. So I am an Indian, so I thought I will put it as the Indian precipitation experiment. So nothing official about it. It's a simple name given by me. Well, I will go, this is my colleague who has done this sort of work with me. What we have done, I will just give a brief hint of what we have done for the last 3 or 4 years with respect to the precipitations which is happening over several parts of India with the help of the dysdrometer measurements, which is giving the variation of raindrop size distribution for every 30 seconds. So a glimpses of what has been done for the last 2 or 3 years. Yeah, we have taken for the case of Mumbai. I am presenting the results with respect to the published paper for the last 2 or 3 years. And finally, what we will be doing for the next 5 years, I will be giving a glimpses of what in this presentation. Well, we have taken taken the city of Mumbai. We have taken the precipitation, and the city of Mumbai, which experiences a rainfall of about 2,500 millimeter yearly, and the highest rainfall is 3,475 millimeter in 2019. We have taken an example of this. Along with that, we have tried to see what is the variation of raindrop size distribution which is happening over the city of Mumbai. We have seen that the number of larger drops of 2 millimeter and above are more happening during the pre-monsoon period with respect to the monsoon months. Now we move to, we have taken a co-located observation of the 4 different instruments to see that how these instruments correlate with each other. So we have taken the pre-monsoon events, total pre-monsoon events and the total monsoon months. What we have seen, the first one is the rain gauge data, second is the dysdrometer data, third is the S-band Doppler weather radar data, and the 4 is the lightning network data. All this has been pointed for a station where dysdrometer has been kept, that is the Mumbai International Airport. You can see from here the pre-monsoon period, see we have got 3 peaks of rainfall, one during the early morning hours, one during noon hours, and the other during the late afternoon hours. And those drops, those peaks corresponds to the number of larger drops with respect to the dysdrometer in the second column. And you can see from here in the second column, these larger raindrop peak stops are also accompanied larger raindrops. They are also accompanied by the larger radar reflectivity. You can see from here, and they are also accompanied with the larger lightning with respect to these peaks. But take the case of the monsoon period, we do not see the diurnal variation of the rainfall. The dysdrometer do not also see that larger raindrops. The radar reflectivity is always high because there is a continuous rainfall is there, and we comparatively see a less lightning. So these are the one of the important examples where we can see 4 different instruments which corresponds each other for the entire period of the pre-monsoon and the monsoon rainfall over Mumbai. So this proves that our observations which we are taking are more or less similar with the other various types of instruments. Now we go with that is a Chennai, Mumbai. Now we have done a comparison of the rainfall distribution Mumbai and the Chennai. See, the Mumbai is at the Arabian Sea and the Chennai is at the Bay of Bengal. So we can see the important features is that the Mumbai gets most of the rainfall during the southwest monsoon season, that is from the June to September, whereas Chennai gets the rainfall, most rainfall during the northwest monsoon, that is from the month of October to December. So what we can see from here is that this is, I have made a comparison, and you can see from the, as you have seen, the larger raindrops are more over the pre-monsoon period with respect to monsoon months over Mumbai. But take the case of the monsoon and the post-monsoon period over Chennai, we can see there is no such strong differences. Only the differences we see with respect to the monsoon month is that around 2 to 4 millimeter diameter, the larger drops dominate with respect to the post-monsoon period over Chennai during the monsoon months. The post-monsoon period is basically, we consider the rainfall for the month of October to December. Now we take the case, one important thing what madam is telling, that the Mahabaleshwar, yes, as Dr. Pandithurai was telling, we have a high altitude cloud physics laboratory at Mahabaleshwar. We would like to measure, the main objective was we would like to see the clouds, to measure the clouds by sitting inside the cloud. So Mahabaleshwar is one of the important region which receives a rainfall of 6,000 millimeter. So it is around 3 hours from this Pune. So what we wanted to see, that how the rainfall or the raindrop size distribution, microphysical features of the rainfall, they vary over the coastal region, Mumbai and the Mahabaleshwar. So what we have seen from here is that during the pre-monsoon period, the Mahabaleshwar rainfall is, the number of larger drops are more over the Mahabaleshwar, that is the orographic station, with respect to the coastal station, while in the monsoon period, the situation completely reverses when the number of larger drops are more in the monsoon period over the coastal station with respect to the orographic features. So this is one of the important characteristics which we have seen for the coastal region and the orographic region, which are hardly separated around 50 kilometers. Now we can see from here, we have done the diurnal variation of this Mahabaleshwar and the Mumbai. What we have seen, that the Mahabaleshwar rainfall, they do have a strong diurnal variation during period, while both the stations do not have that diurnal variation during the monsoon months. The important features we have seen for the Mahabaleshwar rainfall, that is the orographic rainfall, is the number of smaller drops is present in higher number in the Mahabaleshwar with respect to Mumbai, while such features are not observed during the pre-monsoon period. Why this thing happens? We have done our diurnal variation of the Cape, which we have done here. You can see from here that the Cape, just go to the Mumbai rainfall and the Mahabaleshwar, you can see the pre-monsoon period, the Cape, the total Cape is much more greater with respect to the monsoon period. You can see from here that the 14 hours to 16 hours, the Cape is increasing over Mahabaleshwar. Go to the previous slide. You can also see from here that from the 14 hours, we can see the larger raindrop peaks, rainfall peaks are there in the Mahabaleshwar region. Similarly, go to the next slide. You can see from here, there is also a peak of the rainfall observation from the 9 to 13 hours over Mumbai. Go to the previous slide. You can see the similar type 9 to the 14 hours. Please note that these are the two observations. This is from the satellite era intermediate analysis, and this is from the disdrometer data over the region. So we can able to say that the observations which we are taking with respect to the satellite era interim, whether with respect to the ground-based observation of disdrometer, they are entirely matching with each other. So this is one of the important features from which we can able to say that how the rainfall variation is happening over the coastal region and the orographic region. Now go with respect to the orographic station Mahabaleshwar and the Bhopal, that is Central India station, as Dr. Pandithurai and my colleague Sachin was telling, that it is one of the important test bed which we have, IITM has provided here in the Central India region. We have also tried to compare the orographic region and the variation over the Bhopal, what has happened. So you can see from here, we can see the completely opposite features. The pre-monsoon rainfall has the comparatively more larger drops over Mahabaleshwar, while the monsoon rainfall is completely become the opposite over the Bhopal region, the Central India region. So that we can see, we can able to tell that how this precipitation, that are inter-city differential with the precipitation with respect to the microphysical features or the microphysical aspects. So this is what we have done. This is some of the works which we have done and has been already published in various journals. You can see from here. And finally, what is missing? The missing is a comprehensive analysis of raindrop size distribution over the region of India, which differ widely with respect to the geographical and the climatic variation. For that, what we have done a network of the disdrometers that has been in operation over 17 regions of the India, covering all the major stations which differ widely with respect to the geographical and the climatic variation. The last three, that is Sholapur, Turjapur and Guwahati, I give my credit to my colleague Dr. Mahen Kunwar. He and his group has taken special initiative to put these 3 disdrometers at these places. And we can able to see that all the parts of the India we are trying to cover with the raindrop size distribution, which will give the variation of the raindrops or the microphysical features of the raindrops for every 30 seconds, and all the stations are working. So what we have see from here, these cover the major metro cities like New Delhi, Mumbai, Chennai, Kolkata, the island stations, that is the Andaman and the Lakshadweep, which is at the Bay of Bengal and the Arabian Sea. And also we have the Eastern India Himalaya stations, that is the Itanagar and also at Dharmshala. Also we have the station at Guwahati, and the urban rural station, that is as Bhopal and Silkheta. This is Bhopal is a totally urban station, and the Silkheta is a rural station which is separated by the 50 kilometer. And you can see we have also the orographic station, as I told, at Mahabaleshwar. We have the station, the leeward side of the most western Ghat, that is the Pune, Sholapur and the Turjapur, and also the station which is at the northeastern part of the India at Guwahati. So by this disdrometer, a small step, what we have done analysis is that initially we have taken a thunderstorm rainfall of the 8 stations of the India at the same time period. So what we have seen from here, that this thunderstorm rainfall contributes to about 12%. Some area it is contribute 12%, some area it's contribute 4%. So what are the features of the thunderstorm rain? We have taken 3 years continuous data for this thunderstorm rainfall over these 8 different places of the India. So these are some of the, one of the important common analysis which we have seen, the thunderstorm rainfall occurs mostly in the afternoon hours. There are some exceptions, but the common point is that it occurs mostly in the afternoon hours for all these 8 stations of the India. We have also done the drop side distribution over these 8 stations during the thunderstorm rainfall. I mean the pre-monsoon rainfall. I am correcting it, not thunderstorm rainfall. It's a pre-monsoon rainfall where most of the thunderstorm showers occurs. And we have tried to see what is the contribution of the continental, maritime or the intermediate clouds. We could able to see from here, we have got this analysis from the Rosenfield paper. We can able to see that the rainfall which is happening over Mumbai, Mahabaleshwar is basically maritime in nature, and the rainfall which is happening over Kochi, Bhopal and Pune rather than Chennai, they are mostly intermediate, and the rainfall which is happening over New Delhi or Calcutta, it is basically continental in nature. This is happening during the pre-monsoon period. So this is all we have done with respect to the other places. And finally, I'm coming to my end. And what we propose a coordinated field campaign with the presently available disdrometers at different sectors of India for 4 years. We are planning to make all these, because some disdrometers has recently been installed. The main objective of this field campaign is to enhance the understanding of microphysical characteristics of terrestrial precipitation over diverse hydroclimatological condition for improved prediction and disaster mitigation. So what we gain, this will be for the first time the highlight the contrasting microphysical features of the Indian monsoon in different time scale simultaneously over various regions of the India. This will be the part of the monsoon campaign of IITM or MOS, which is happening from 2025 and which was also there initially, and it will be also happening 2025. This can be a part of any international monsoon campaign. It's I have not decided, it's GPEX or AsiaPEX or whatever is thing. And as this is happening by taking into account of the various regions of the India, hence I coined the term as the Indian precipitation experiment and put it as the heading. So this is all from my side, and I'm sincerely acknowledged to all the persons who involved for these experiments and organizing committee of IMW, and this is all from my side. Thank you.
Thanks a lot, Dr. Kaustup. One rapid question. Any questions online?
Yeah, Mohanty
please?
sir, shared. Yes, sir. Sir, let me tell you, I have taken only the pre-monsoon rainfall. Pre-monsoon rainfall,
Thunderstorm mainly.
mainly it is thunderstorm.
And always thunderstorm as the air mass, what type, small or mara. And then it move from the land towards ocean and dissipate. That is the. So why it's continental, both is.
Okay. I will answer.
Dr. Kautz, yes, please. And I think we will have to move on now because
Okay, I will answer this. I have an answer for that.
yeah, maybe over lunch should be perfect.
Okay, I will
Even
answer
30
you.
minutes for lunch.
Okay,
You can
thank you.
discuss or
Thank you. Thank you. I will answer you, sir.
So we now have, right before lunch break, a special talk by Drs. Pierre Kurtzetter and Robert Palmer, please. Thank you. No, that talk will be for after, because since we have to start at 2 p.m., we are starting with many online presentations. So Dr. Hari's talk will be right after. Thank you.
Good afternoon. So I am fully aware that I am standing between you and your lunch. So I will not be offended if you don't have any questions about this talk, but I will welcome any questions, of course. So this is this talk will provide a kind of a different perspective on precipitation in India. It is about a project that is focusing on a collaboration between the University of Oklahoma in the US and India on forging global alliance for climate, weather, and water. So my name is Pierre Kurtzetter. I am from the University of Oklahoma, OU, and we have a number of team members from OU, but also from India. And one of the key players in India with whom we are working is the Indian Institute of Tropical Meteorology. So I want to acknowledge also my co-authors, Dr. Robert Palmer and Dr. Venki Timularai, who are in the audience. So what's the need and significance? So all nations are becoming more vulnerable to extreme weather and climate events. For example, to illustrate that, the World Economic Forum regularly classify climate failure and extreme weather as one of the most likely and impactful type of risk at the same level of impact of weapons of mass destruction, but much more likely. So this is something that impacts everybody. And in order to address this big challenge, we need to identify what are our current gaps of knowledge. In this case, we have identified 3. Regional risk awareness with weather and water. That involves observation and modeling, observation infrastructure and modeling means. Second, we need to understand what are the associated processes on the shorter time scale, weather, and longer time scale, climate. And finally, even if we are able to observe these processes and make a forecast, these information is of no use if it is not provided appropriately to receivers, deciders, and the population. So we need also operations to produce forecasts and long-term risk assessments in ways that will reach more people and increase public intelligence. And in the long term, inform urban planning and water resources infrastructure. So the significance here is to share approaches for effective climate weather response and resilience-driven systems. So India is home to more than 1.3 billion people and is one of the most reliable nations to climate and weather. And that's, I guess, one of the major reasons that is gathering us here today. So what is a vision? This is a project that we are that is starting only, and we are trying to put forth this vision of propelling India to the forefront of monitoring and forecasting climate and weather and water phenomena. So the approach is to co-create better decision-making processes for weather and climate resilience adaptation, and by doing so, forge global collaborations to tackle these complex challenges. So now we are going to talk a bit about this collaboration. We have there are already some ongoing partnership between the University of Oklahoma and partners in India. So yesterday, Dr. Palmer and Timulai, we were visiting IIT Bombay, where we were welcomed by Indu, associate professor. And we have also alumni, Shruti Upadhyaya, who is at the Indian Institute of Technology, Hyderabad, and Manabranda Saharia from IIT Delhi, who with whom we are actively working, and we have already signed memorandum of understanding. And this collaboration proved fruitful during the International Precipitation Conference that took place in 2023, where we organized a pre-conference workshop that was online and was focusing specifically on India. And the quick fact is that not only it gathered participants from India, but also from 12 other countries, and gathered participants from academia, industry, governmental, and nonprofit research institutes, which gives you an idea of the diversity of actors who have interest in this kind of topic. So Dr. Timulai is spearheading also another level of collaboration on the decider side with, we are going to visit with the scientific advisor to the Prime Minister, the Secretary to the Ministry of Earth Science. Today and tomorrow, we are visiting the Indian Institute of Tropical Meteorology and Search. So the idea is to gather momentum both at the academic level, on the operational level, and get the buy-in from deciders in India. So why OU? Well, OU has a strong expertise in weather and climate, especially in terms of observing weather phenomena at fine scale. And what I have particularly in mind here is an expertise in weather radar. There is OU hosts the only institute of AI, artificial intelligence in the US that is focusing on weather. The Advanced Radar Research Center provides the best global academic program in weather radar, and currently spearheading the development of phased array radar technologies that will enable us to scan storms in a more continuous way, both in space and time, and reveal the signature processes that we haven't been able to correctly identify thus far. There is also a rare connection on the Norman campus between academia, the private industry, and federal entities like the NOAA National Severe Storms Lab, which enables this community to formalize solutions, test them, and make them operational. This is a strength. And I want also to highlight the Institute for Public Policy Research and Analysis, which works already with NOAA on public policy challenges and perception by the public of extreme weather warnings and changing climate information. So what is the approach? We want to co-create an ecosystem of academics and operational agencies in India and in the US. And that will be the starting point for global collaborations to tackle complex challenges. So at IIT Bombay yesterday, we were talking about a dual PhD program between IIT Bombay and OU to train a workforce that will focus on this big challenge. We are talking about infrastructure of observation network. And now is the moment because India is investing in their weather radar network. So in Norman, there is an expertise in using observations from the radar networks in order to derive weather intelligence. And I'm going to deliver actionable information. And that involves this particular aspect of the project involves especially the Indian Institute of Tropical Meteorology, the Indian Meteorological Department, and IITs. So what I'm talking about here is radar observations that are mosaicked across the US in real time at very fine scale, and a number of products of information can be derived, like precipitation estimates, severe weather maps. Here we are talking about the vertically integrated water content and hydrologic impact for flash flood monitoring. So second, we wanted to renew our approach for risk quantification by leveraging these real-time observations. And we need to cross the estimates and the forecasts we are making with weather radar infrastructure with our other infrastructures that will be confronted with these weather patterns, and also renew construction practices that will allow us to build a long-term future. So that involves mainly actors in civil engineering departments. And finally, as I said earlier, society-led efforts to enhance risk awareness and lead to improved society intelligence with respect to weather forecast. So I will pass quickly. Expected benefits are obviously on the science. This is a scientific conference, so we will learn more about extreme weather events and climate patterns. We will also that will also increase the visibility of involved partners because we will be sharing knowledge with each other in order to promote self-reliance and sustainability. Academic impact. We wanted to create a workforce that will enable this kind of effort, like operating the radar network, processing the data, warning the population. So that gathers, that involves a number of disciplines: atmospheric sciences, weather radar engineering, civil engineering, social science. The expected benefits also are in terms of a synergy between academia, government, and industry. And finally, that will enable co-production of knowledge. So all that to benefit society and create a framework for weather climate forecast systems that will increase the resilience of society by improving awareness and understanding of what's going on. So I am finishing with this slide, which summarizes all the actors we have at OU. We are all from different departments with different disciplines, and we are focusing on India. And I list also here the partners in India. We are with Dr. Palmer and Timolai. We are spending the week in India, and we are discussing all this collaboration and setting up the next steps for this project. Thank you very much.
Thanks a lot, Doctor. A very quick question. If not, maybe we can move this over lunch, because the next session has lots of online presentations. So we would like to keep them on time and not waiting. Yes, Rupa Kumar, please.
Yeah, this is an excellent initiative, but what I would like to know is that WMO, as part of its programs, also has many activities almost on the same lines that you have described. So how do you complement and to make sure that you are actually aligned with the international efforts being made with WMO, maybe other partners? An example that I can mention is the Global Framework for Climate Services, which has the co-production and co-development as one of the key approaches that they promote. It's important for us to be part of that rather than doing independently.
Yes, thank you. Thank you for this question. So we started by focusing on something that OU can contribute to the weather community in India, which is the ability to process data from radars in order to derive a number of diversity of information for weather intelligence. So that is kind of the cornerstone of our current effort. And from there, we intend to connect with existing efforts like the ones you mentioned in order to integrate all these efforts together. We are also, we have put together a proposal to organize an international workshop at the Royal Society. And we hope that we will be able to discuss about these various efforts that are happening and create some synergy. Thank you very much.
Thanks a lot, Doctor. So I think, thanks a lot. Dr. Krishnan, do you want to say? No, okay, that's fine. It's now time to break for lunch. It's going to be a very quick lunch. I'm sorry for this. So we reassemble back here at 2 p.m. Run. Okay, sorry. Just a moment, please.
I request Dr. Rup Kumar. I request Dr. Rup Kumar, Rup sir, to kindly present a memento to the chair. And I thank Dr. Hindumati. Yes. And I thank, no. And I thank you for chairing the session. The lunch is arranged in the basement of this hall as well as in the guest house. Please enjoy your lunch, and we will supposed to be gathered at 14 IST. Excuse me, sir. Please wait for a moment. Yeah, I request Dr. Hindumati to please present a memento to the. Yeah, thank you all. Thank you.
Good afternoon, everyone. So we are about to begin the next session on regional monsoon of the world and their multi-scale processes. I am pleased to introduce Dr. Surachandra Rao, who will be chairing this session. Dr. Surachandra Rao is a senior scientist at IITM and leads the Monsoon Mission Program of Ministry of Earth Sciences, Government of India, which involves researchers from across the world to work on operational dynamical models in India. He also leads the high-performance computing program of MOES, that is Ministry of Earth Sciences, and he has made significant contributions in dynamical model developments and diagnosis for improved Indian monsoon simulations and predictions, as well as advancing AI/ML applications in climate science. I now request Dr. Surachandra Rao to start the session.
So can I begin? Okay, good afternoon, everyone. And we have about 9 present in this session. So I request all the speakers to keep the time. And so first talk in this session is invited talk from John. So he'll be talking about a planned international program for Asian, Australian, and African monsoons. I hope he's ready. Yeah, he's there. Oh. So we
Okay.
can start. So you want us to share your PPT or you will do it?
Okay,
yourself?
I share my
Okay.
my PPT.
So you have about 15 minutes, then we'll leave 5 minutes for questions and answers.
So can you see my PPT?
Yeah, we can see you, your PPT.
Okay.
Go ahead. Yeah.
Oh, thank you, Chairman. And good afternoon, ladies and gentlemen. It is a pity that I didn't get the visa to India, and I can't attend the meeting face in face, and so I have to give my talk online. And the title of my talk is a brief introduction to a planned international program for Asian Australia Africa monsoons. We call it the Triple E monsoons later. And my name is Renhe Zhang from the Chinese Academy of Meteorological Sciences and also from Fudan University in Shanghai. And the outline of my talk is composed of the four parts. And the first part will be the background. And we talked about the triple E monsoons, and here we show the geographic distribution of the triple E monsoons. And the triple monsoons include the East Asian monsoon, West North Pacific monsoon, and Australian monsoon, and the South African monsoon, West African monsoon, and also South Asian monsoon. That's also called the Indian monsoon. And here the region we considered in our program. And we know that the Triple monsoon region is a typical region for the ILC interaction and island interaction. And also the monsoon, not only a local phenomenon, but it also impacts significantly on the global atmospheric circulation through the teleconnections. Here we show the teleconnection here. And also another feature of the Triple monsoon region is that a high population density. More than 2/3 populations in the world living in this area, and this area is a global hub of human and economic activities. Here I show two maps. One is for the sky brightness which got from the satellite. We can see that the Triple monsoons region is the human activity is quite severe, and also this is also optical thickness. And we also can find the Triple monsoons is region which have severe air pollution. And another feature is that the region of tropical monsoons is a major disaster area severely affected by the extreme weather climate events. For example, the extreme floods and heat waves and wildfire, and also the drought. And here we show some statistics, but I will not explain in detail. And we can see that that's very heavy disasters occurred in this region. So in the Triple monsoons region, we have the typical atmosphere ocean land interaction, and also the human activities, and also the disasters. And here is the region we selected. And next I will talk about the scientific challenges dealt with in our program. And the challenge one is the Triple monsoons are connected as a unified system. Here we show the map we can see the horizontal circulation like the monsoon flow, and from Australia to Africa to South Asia and to East Asia, and also the cross equator flows from Australia, around Australia and to the East Asia, and also we have the horizontal vertical circulation like the hardline circulation and the walk circulation, and the Type A monsoons should be a unified system, but previously the previously the studies mainly focused on a specific monsoon region, but not look at the monsoon region as a whole. So integral investigation is needed for an overall understanding of monsoon systems as well as each monsoon system. And that's the challenge one. And the challenge two is the East Asian monsoon region has a very significant intra-seasonal, interannual, and interdecadal variations. Here it shows the precipitation averaged in the triple A monsoon regions, and we can see the very multi-scale atmospheric values very clearly. And previously, the individual variability like such as intra-seasonal, interannual, or interdecadal variability are well studied. However, their influence on the weather and climate extremes are not well understood, and how the multi-scale atmospheric variability affects the extreme events, we do not have not well understand. And the challenge three, we know I mentioned that the Triple A monsoon region is a region of typical multi-scale interactions. But however, how the multi-scale interactions affect the extreme events is also not well understood. And the Triple monsoon region is a typical region for the land atmosphere ocean interactions, but how the land atmosphere ocean interactions are also not well understood. For example, I show some examples here. Here is ocean surface flux. This is global ocean surface flux obtained from different data source, and we can see a very large difference can be observed from among the different data sources, and also here is the land surface heat flux that's over the Tibetan Plateau, and we can also see very large uncertainties in understanding the land surface heat flux. And here we show a LC gas exchange rate based on carbon 414. That's the different schemes adopted in different climate model, and we can see the exchange rate is the difference of the exchange rate is small when the wind is small, but when the wind become larger, the difference is quite large, and so we don't understand well the land atmosphere ocean interactions, and that will have major impact on our understanding and also prediction and simulation of the Triple A monsoons. And the challenge 5 is the impact of the human activity on the extreme events. And for example, the Triple A monsoon region is is a place that has plenty of greenhouse gas and also pollution, and also the land use change and the land use cover change, and also the urbanization and also air pollution, and how all these human activities influence the extreme events are not also not very well understand. And the challenge 6 is the predictive skills are low for the climate anomalies in the region, and also the regional extreme weather climate events. For example, here shows the ACC scale for the summer precipitation. We can see that the North American monsoon region has much higher ACC than the AAA monsoon region. And here also an example of the extreme events, which extreme heavy rainfall occurred in 2020, in the summer of 2020 summer. And here is the ensemble prediction from the Z2S models, and we can't find the signal from leading time of 3 weeks until the leading time of 1 week, and it's not well predicted for the extreme events, and so we propose the program. And the simple goal is the mechanism of simulation and the prediction of the weather climate extremes in the region of AAA monsoons and the global warming background. And we will try understanding the impact of air, land, sea interactions on the variability of AAA monsoons and its link to extreme weather climate events, and also the understanding the modulation of human activities on changes in extreme weather climate events, and also understanding the impact of multi-scale variability of AAA monsoons on extreme weather climate events. And we are based on these understandings, we will enhance monitoring, simulation, and prediction of extreme weather and climate events in the region of AAA monsoons. And we have surrounding the weather and climate extreme events, we have planned preliminary planned 6 research directions. The first one is variability and interconnections of the AAA monsoons, and the second, regional and global impacts of the AAA monsoons, and the third is the AAA monsoons and atmosphere ocean land interactions, and the third one is the relations between the AAA monsoons and the human activities, and the fifth is the interactions between the AAA monsoons and the typhoons, and the typhoon is a very important feature in the AAA monsoon region, and the sixth is the monitoring, simulation, and prediction of the AAA monsoons. And we also planned field experiments in the program, and we have also planned 3 international projects for modeling and prediction comparison in the region of AAA monsoons. The first one is the international project of prediction comparison for subseasonal to seasonal, that's S2S climate variability. And the second one is the international project of simulation comparison for land atmosphere, ocean atmosphere interface flux that we have mentioned just now. That's uncertainty is quite big. And the third one is the international project of simulation and prediction comparison for extreme weather climate events. And for the field experiment, we have considered the observational experiments for atmosphere, and the experiment will focus on the monsoon circulations. As I just mentioned, the horizontal circulation and the vertical circulations, and also what vapor transports, which closely related with the heavy rainfall and drought, and also convective activities and atmospheric components. That's mainly among the atmospheric chemistry, and also urban meteorology, and also physical and chemical processes associated with heavy rainfall. That's the observation in the focus in the for the atmosphere, and also for the ocean, we will focus on the physical, chemical, and biological processes in atmosphere and land ocean interfaces, and also exchange of energy and materials through land atmosphere and ocean atmosphere interfaces, and oceanic currents, and ocean thermal conditions, ocean vortices. And this is a figure which shows our planned region for land atmosphere interaction and land ocean interactions. For example, the red shadings are the land ocean atmosphere ocean interaction regions of the Western Pacific and South China Sea, and also tropical Indian Ocean, Arabian Sea, and also the Bay of Bengal area, and also South China Sea, and also the maritime continents. And for the land atmosphere interaction regions, including the Africa, South Asia, South Asia, East Asia, and also the Australia region, and also around the maritime continent and Indochina Peninsula, which is not very clear, this figure. And we not do all of them by ourselves, and we would like to cooperate with the current observational networks in the region of tropical monsoons. For example, in the Western Pacific, in the South China Sea, in the tropical Indian Ocean, and around the maritime continent, and also the Bay around the Indian Ocean. And at last, I'll give a brief conclusions. This program aims at establishing an international collaborative research platform for the study of AAA monsoons. And we would like to utilizing and sharing observational resources among participation countries. And the third one is enhancing understanding the predictive capabilities for weather and climate extremes. And this project could not fulfill by only one country. We would like to have a wide international cooperation, and we will try to do this, I think, later. And the last, we have a slogan, we would like to work together to unveil the secrets of AAA monsoons, a global collaboration for a sustainable future. Thank you.
Thank you, Professor Jiang, for an excellent presentation. Any quick questions to Professor Jiang? Okay, so no questions from the audience. Any online questions? Just check.
Nice.
Okay. So thank you, Professor Jiang. So we'll move to the next presentation. Elena. She'll be
Okay,
talking
thank
about,
you.
yeah. So she'll be talking about breakthrough in
So
forecasting.
I
monsoon onset.
quit.
Yeah, please go ahead. You want to say something?
No, I quit. Thank
Okay.
you.
Okay,
Quit
thank you.
sharing my PPT.
Yeah, thank you. Request you to wrap up your presentation in 10 minutes, Elena, so that we can have some time for questions.
Good afternoon, everyone. My name is Elena Suravyatkina. I'm physicist in theoretical physics with expertise of critical phenomena and at Potsdam Institute of Climate Impact Research, and also Space Research Institute of Russian Academy of Science. So at the beginning, let me quickly explain what does it mean critical phenomena, because it's a crucial question about forecasting monsoon onset and withdrawal. Let me show you some experiment. I'm holding this bottle in my hand, and then it's stable. But if some fluctuation appear, this bottle became less stable. But if fluctuation increasing, it's going to fall down to another stable state. And if any other fluctuation can be forced to this state, this bottle never going up. So this is a theory of concept from theory of critical transition that I'm working on in different fields from medicine, engineering, and forecasting monsoon onset and withdrawal. So my contribution to the field to monsoon research. Together with my colleague, Veronika Stolbova, we discovered onset and withdrawal of monsoon are critical phenomena. We reveal universal regularities across all regions of monsoon zone on the Indian subcontinent. We developed new theory of critical transition from pre-monsoon to monsoon and to post-monsoon. We identify new regularities in special temporal propagation of monsoon. This is regarding of tropic and subtropic connection. So we create universal approach to forecast onset and withdrawal of monsoon more than a month in advance. So this approach is fundamentally different from numerical weather forecast and climate climate modeling, etc. This is absolutely another approach to go to solve the solution of this problem. So let's go further. So let me explain what is the difference between my approach and meteorological study. So according to climatology, transition to monsoon happens gradually. You see, this is climatology 1993-2021. And this is smooth gradual transition. The question is when monsoon starts? Here, here, here. This is uncertainties. And there's no any definition when it started. But let's go further. If I put on this the same plot individual year, 2016, what we can see here. So this is abrupt transition from pre-monsoon to monsoon. So this discovery allowed me to apply theory of critical transition. establish two stable states, pre-monsoon and monsoon, and determine value of critical threshold right here. The monsoon season begins once temperature crosses critical threshold, when this bottle turns to another stable state. So, another critical transition actually smooth from monsoon to post-monsoon, but this is also critical transition. So, I propose universal definition of monsoon onset based on the critical value of three atmospheric variables: temperature, relative humidity, temperature, critical temperature is here, relative humidity here, and outgoing long wave radiation. Three critical values of atmospheric variables. Outgoing long wave radiation is a crucial indicator for upcoming monsoon characteristic convective activity, implying scarcity or deep conventional clouds. So now, whatever we're working around the tropics, we are looking for transition to monsoon, and we have very reliable indicator. So from year to year, it would be not absolutely the same. For temperature might be changing 1 degree or 2 degree, but this is not so much difference. So in 2016, we published paper when we developed methodology how to forecast monsoon onset and withdrawal in central part of India, 80 north, 20 north, 80 east. And this is a performance, our predicting scheme retrospectively. From 1965 to 2014, 74% of success rate. And for withdrawal, this is a 84% of success rate for monsoon withdrawal. For central part of India, as I said, 80 north, 20 north, 80 east. So, and you can find this in our JRL paper 2016. So, since 2016, I forecasted monsoon every year. So, from 2016 to 2024, this is my forecast 40 days in advance. I'm doing forecast on first week of May. And then observation of Indian Meteorological Department is here. And withdrawal of monsoon. Again, I'm doing 70 days in advance, and observation of Indian Meteorological Department. As you can see, it's working. It's working very well. So this is for one particular location. What's going next? The next, actually a few years ago, I started to forecast in Telangana and in Delhi. And then in 2024, I decided to go to contribute my research to 200-year history of monsoon research. So in 2024, I successfully predict the onset of monsoon of 22 out of 36 meteorological subdivisions in India. I made the first ever forecast of monsoon withdrawal dates across whole India in 2024. Let me quickly show you results. So this is my first result. There is the same 7 regions in India. You see on May 9, I produce forecast. This is onset period for every location. And also I forecasting dry spell in pre-monsoon season, before monsoon start. It's very important for farmers, and I'm doing this for that reason. Then here you can see verification of my forecast by Indian Meteorological Department observation. So in 2024, so all previous 6 regions was very in line with Indian Meteorological Department. However, IMD close advance of monsoon at the end of the June. However, if you remember, it was very hot condition in Delhi. It was not continued rainfall, it was few, and monsoon started in Delhi on 21st of July. So, and it was, let me say, very, I forecast this daily on May 9. So this is 2 months in advance. It's working. So after that, I decide to make it monsoon zone in India. So, and this is why I made first time forecast over 22 regions. Able to see my mouse. Okay, 22 regions. And you can see this is the first 7 and around. Everything is documented that you can see on my monsoon webpage. Every time I deliver talk here every year. And also you can see all this verification in my monsoon page. So in Potsdam Institute of Climate Impact Research, and also I'm right now I'm developing website when you find everything about history of my previous forecasts and future forecast. So, and at the end, first ever forecast of monsoon withdrawal date across whole India, starting from Gujarat and Rajasthan till Kerala. I predict this monsoon. I made this forecast on 15th of September, and this is my forecast, and here is result. It's very well suited with observation of Indian Meteorological Department. That means first withdrawal forecast already done. So also very quickly, I have been collaborating with International Rice Institute in Bihar. And this is like one of the example of my collaboration over the India. So the idea is that they improve coupled rice wheat cropping system. And I made forecast from 29 to 29, 21st to 29 of June. Monsoon start on June 24. So it was correct. And scientists from agriculture scientists estimate that if farmers know when monsoon start, productivity of this system increase in 64%. So you can also find details on my website. And I'm doing in different countries around the globe. So India show you, then I have been in Africa and forecast in Ethiopia and southern Tanzania, and also in Peru and Colombia, not Colombia, Bolivia and Brazil. And my next step, Western Africa and South China and Japan. And also I'm doing forecast for ice season on the Sea of Okhotsk using similar methodology. So finally, conclusion. Theoretical advances. Establish robust scientific foundation for dynamics of transition from pre-monsoon to monsoon and post-monsoon. Introducing universal definition of monsoon onset based on the critical threshold of 3 atmospheric variables: temperature, relative humidity, outgoing long wave radiation, critical values. Identified 2 types of critical transition to monsoon onset it's bringing gap in current understanding of local monsoon arrival. In previous years, I show that actually monsoon come in two types. One is really abrupt monsoon, and another monsoon is going during this, it's stuck close to critical value, and after that it's going dry spell, and then monsoon start. Two types of transition to monsoons, another topic. And then practical implementation, enable monsoon onset and withdrawal forecast across India monsoon zone when prediction were previously unavailable, and provide 40 days in advance forecast, offering only available monsoon withdrawal forecast in India. And this methodology can be extended around the world in tropics. In tropics, and paving the way for more resilience and adaptive climate strategies. And then, thank you to my co-authors. And then this is my new website. If you would like to know when will the monsoon come, you can type my name without dot, YelenaSuroviatkina.com. So you will easily find my website and find when monsoon start and when monsoon withdrawal. Thank you very much for your attention.
Any quick questions to the speaker? Yeah, please. So before Mike reaches him, so what is this model based on? The prediction model? Yeah.
Prediction model based on the definition of monsoon, it's critical transition. So once I identify critical values, and then once, for example, temperature past critical value, monsoon start. It cannot like this bottle going back. This is a really physical basis for many disciplines. Actually, critical transition, this is 80 series of books for critical transition for different fields in the science. So, in this concept, once, why I able to work in different fields? Because when I see sign of critical transition, then I can solve this problem.
There we go. Spasiba. The monsoon is not a closed system, right? So there's a lot of influence from the region around it, and that information would not be contained in those predictors necessarily. Now, I understand the underlying theory, but I mean, for something like a monsoon break, that could easily be averted in advance by, say, a cyclone type phenomenon, right?
Not exactly. This is a universal definition around the tropics. To where you're going, to Africa, to South America, to South China, South Asia, everywhere would be this kind of transition, that it would be critical transition. But when you're going out of tropics, there is no critical transition. But when I'm going to work on north forecasting, ice season forecast, this is also type of critical transition. So once I found this feature around the tropics, it's valid every year forever, because tropics, there is a special, I will not explain meteorologists what is the difference between tropics and subtropics, everyone knows this.
Okay.
Okay.
Can you also predict active spells of the monsoon using this technique? Like you talked about breaks and withdrawal, but what about active spells?
I didn't get it. Which monsoon?
Active spells during the monsoon, like you talked about breaks or the monsoon onset and withdrawal.
During monsoon breaks.
During monsoon,
so
you have
This is another story.
Okay, we'll talk later. Thank you.
Yes, this is this is really another story because this is no critical transition. Critical transition from pre-monsoon to monsoon is once happens. What's going on in between? This is another challenge. We have to work on this and think about and find solution. But this solution, transition from pre-monsoon to monsoon and from monsoon to post-monsoon, it's done.
Okay. So we'll move to the next speaker.
I have a question.
Yeah, maybe we can, because we are running out of time.
All right.
Can have a discussion offline. So we have next speaker is Ambrosio. He will be talking about Lagrangian analysis of the dynamics of Indian summer monsoon active and break events. Maybe that will answer your question. Ambrosio, can you hear me?
Yes, yes, can you hear me now?
So, you can start your presentation. Yeah.
Yes, I'm sharing my screen. Okay, so let me just put my slides in presentation mode. Can you hear me well?
Yeah, we can hear you very clear.
Okay, very good. So Lagrangian analysis of the dynamics of break and active events in the Indian summer monsoon. And this work, well, it's part of two projects, this UK Research Council project on mid-latitude influence on the monsoon onset and progression, and another project called Outbreak. It's a WSSP India project that really focuses on breaks during the progression of the monsoon. So, well, I don't need to spend time telling you how important the Indian summer monsoon is for agriculture and the whole society in India. I would only like to stress that interseasonal variability can really change, well, can really have a big effect, because if we have a season with a series of break events, that can have like severe impacts on agriculture and farming. And if we look at break events, like a very famous one was the July 2002 monsoon break, when India received only 50% of its usual rainfall. And the study by Butt revealed the importance of mid-level intrusion of dry air coming from the west on the Arabian Peninsula. So instead of being moist flow over the Arabian seas, there was dry air flowing from the west. And instead, looking at the 2009 extended break, Krishnamurti et al. Highlighted the role of dry air coming from northwest, so from the desert regions in Western Asia, helping to suppress convection. So there are different regions from where this dry air could come from, and we need to really understand where it's coming from, how it's getting to the Indian subcontinent, and what processes are happening along the air as it moves towards India. So that's why we use Lagrangian methodologies, or Lagrangian trajectories. We've applied Lagrangian trajectories in the last few years to a number of studies of the Indian and East Asian monsoon, because we applied trajectories on UK Met Office convection permitting simulation of the 2016 monsoon onset, highlighting the interaction between dry air and moist air at the interface at the edge, the northwestern edge of the monsoon progression, and the sort of tug of war going on that drives this progression as the onset goes on, and also the influence of extratropical synoptic trend dynamics, let's say like a trough coming in from the northwest. We also looked, as I said, at East Asian summer monsoon, again highlighting the interaction between dry air flowing to the north of the Tibetan Plateau and moist air coming from South Asia, the South China Sea, and how this drives the northward progression of the Mayu front. And very recently, and I think actually is going to present this, we've also looked at the withdrawal of the Indian summer monsoon, illustrating how during the withdrawal, the importance of dry air from northwest increases over time. So what I'm presenting today is this study in which we use the Lagranto trajectory tool on 6-hourly ERA 5 input data from 1940 to 2023. We identified a monsoon causal box, and we started trajectories at 850, 700, 600, 500 hectopascal every day at 0Z from the 1st of June to the 30th of September in this 84 monsoon season. So we have an awful lot of trajectories. And we also identified break and active events based on standardized precipitation anomaly for at least, being at least plus or minus 1 for at least 3 consecutive days over the coast zone. So we identified 188 breaks and 261 active phases, and we selected the middle days of all these events. Let's say if an event has 5 days, we select the 3rd day. So that's the middle day. And we created like composite subsets. And we traced relevant physical quantities such as pressure, specific humidity, and potential temperatures along these trajectories to examine the variations in properties. So here we can see trajectories for break, doing the middle cut is released from the middle days of break events on the top row, and from the middle days of active events on the bottom row. And if you go from left to right, you can see trajectories released at 850, 700, 600, and 500 hectopascal. And if you compare the two, these are density plots. They represent the density of trajectory points. You can see the differences between the two subsets. Because even at 850, even for trajectories that arrive at low levels over the coast zone, there's a difference in how they impact with India. You see this like this southwards extension, which shows how the inactive events, the air is traveling very close to the surface and has to deflect. It's deflected around the Western Ghats. Something that doesn't happen during break events because the air is flowing from slightly higher levels. And we also see that during breaks, we see some trajectories coming from coming through terrain gaps, like the Persian, the Red Sea, the Persian Gulf, and from like Central Asia. But these differences are more dramatic if we look at trajectories released at 700 hectopascal, because for active events, the Somali jet classic monsoon flow is still prevalent. But if we look at break events, we see that the highest densities are for air that is coming through this gap between the Hindu Kush Karakoram mountains and the Iranian plateau. So it's the air that is definitely not tropical in origin. It's coming from the extratropics, from the Caspian Sea area, and is going through this gap to get to the Indian subcontinent. And if we look at trajectories starting from mid-levels, we see that for break events, the influence of air coming from remote regions much further west is more evident than in active events. So we see densities, trajectory densities coming all the way to the central Mediterranean. So this shows the relationship with the subtropical westerly jet in these cases. So something that we did to understand what was going on in these trajectories was to calculate time series of processes, time series of relevant variables. So we have pressure, specific humidity, dry potential temperature, and equivalent potential temperature for break in red and active events in blue. And I'm only showing, for reasons of time, trajectories released at 700 hectopascal, but you can see the difference. It's clear if we look at pressure, because for active events, the air is flowing around 850 hectopascal, so quite close to the surface, and then it ascends to 700. While for break events, the flow is pretty much flat, horizontal at 700 hectopascal. And as a result, in doing break events, this air that reaches the core zone at 700 hectopascal is gaining much more specific, much more moisture than in break events. And this is also indicated by the by the variation in theta and theta re, because we see an increase in theta re, which indicates mixing with warmer air above the ocean, while theta is flat, and theta being flat while theta re is increasing suggests the presence of latent cooling by evaporation, which is also confirmed by this increase in specific humidity. The final decrease then in specific humidity suggests condensation going on as the air starts to ascend. So it's all conducive with like air becoming very moist as you get to India and then ascending and producing precipitation. Well, none of this is going on during break events. It's very dry air that is flowing horizontally to 700 hectopascal. And to understand this a bit more in detail, we can look at case studies. So, for example, here I'm just showing a break event that was part of the very dry August 2023 period, I'm sure you remember, and then an active event from 2022. And in this case, the trajectory starts from a slightly smaller core zone and only computed back for 6 days, but the idea is the same. And the trajectories are really at 700 hectopascal. And starting from the map, we see really a big difference between, like in the path of the trajectories, because in the active events, we have this classic Somali jet flow, C-shaped, and then a very evident cyclonic circulation over Western India here, possibly a monsoon depression or a very active monsoon trough here. Instead, in the break events, we have two main branches, one coming from the northwest, going through the mountain gap we talked about before, and another one in which the flow is constrained by the terrain, and the air goes through the Red Sea, the Gulf of Aden, and then crosses from west to east, the Arabian Sea. So these are the two branches that were identified in two different events by Bhatt and Krishnamurti, and we see here in a single event that we have these two branches. And very interesting, there isn't anything in between. So it's either air coming from the northwest or from the Red Sea and then the Arabian Sea. And separating these two branches, we can see that the air in the southern branch, this Red Sea branch, is flowing at fairly low levels, lower levels, closer to the surface compared to the air coming from the northwest. But nonetheless, if you look at the colors, it still contains much less moisture than the low-level air in the active events, which is really much more moist. And so I'll go quickly because I know I'm probably a bit short on time now. What we're starting to do now is to try and make sense of these Lagrangian results, is to step back a bit and look at the large scale in a Eulerian sense now. So, for example, to look at the pattern of geopotential height and the upper level jet, mid-level vorticity, and low-level potential temperature and potential vorticity. And I will just mention the difference between break and active events in geopotential height and in the jet, because we see higher heights at 500 hectopascal in break events. This average was computed 2 days before the middle day of break and active events. So we see a stronger anticyclone over like the Arabian Peninsula and the Persian Gulf. And the more evident anticyclonic curvature of the jet in the Caspian Sea area. So this is consistent with the Lagrangian results showing the arrival of dry air over the monsoon core zone being more favored by break events associated with like this anticyclonic tendency over Western Asia. So to conclude, these are really interim results. This is analysis that we are doing now and is not complete, and any feedback on how to improve it is more than welcome. But these interim results are clearly highlighting the differences in the evolution of air masses arriving on the monsoon core zone during active versus break events. And yeah, further analysis will be conducted to fully detail the drivers and processes behind these differences. And it looks like particular importance, but we need to place particular focus on the intrusion of dry air, either coming from the northwest or crossing the Arabian Sea during these break events. And that's it. Thank you very much for the attention.
Yeah. Thank you very much for an excellent talk. Any questions from the audience? Nothing. Online? Okay. Thank you, Amrujo.
Thank you. Thank you.
So next presentation is from IITM, Dr. Subodh Saha, monsoon variability and predictability associated with antecedent remote land surface temperature.
Good afternoon. I would like to thank my colleagues who have contributed in this work. So let me begin with some backgrounds, which we all know that ENSO is a single largest predictor, which explain about 20 to 25 to 30% ISMR variability. And also it is on the later phase of monsoon, not in the beginning. Beginning it is quite weak. So what are the other source of predictability? It's an important question. And also we know that Asian monsoon, it is a very giant interhemispheric circulation pattern, which initially begins with a gradient of land ocean temperature. And that part, the initial phase of monsoon is important. And there is a lot of interaction, different interaction with land atmosphere. But we don't know much because there are lack of observations. And as yesterday's talk, we have seen that initial phase of monsoon, when you see, it goes very rapid transition, very dramatic changes in land surface condition, atmospheric conditions. So there are a lot of feedback goes in, and there is also some many subseasonal extreme events in the initial phase, which contribute significantly to not only H2S prediction, but also contribute to seasonal predictability. So from predictability point of view, the subseasonal component is very important, and land surface is one of the important component. So here is one study which shows that how the subseasonal component is related with ISMR variability and predictability. You can see the x-axis is a periodicity and y-axis is the correlation. You can see the maximum correlation with subseasonal variance with seasonal anomaly is in synoptic band. So synoptic activity, there is lows and depression, they have a maximum contribution to ISMR anomaly, and they are also sorry, they are also related with predictor like ENSO. You can see. So this is on internal time scale, but if you look on multi-decadal time scale, the same figure, but in a 31-year running mean, we can see different bands, how they are varying with time, 31-year running window. So this relationship is not static. They changes, they go through dramatic changes like let's say 10 to 20 days. So for a decadal prediction system, not only seasonal, if we think that for subseasonal is not important, so it will be a mistake probably that in decadal prediction system, we also should have very reasonable simulation of subseasonal component. So this is all background, and this is probably the first study which clearly or very specifically showing that how the synaptic system is contributing to ISMR, and this is the major contributor of ISMR variability. So it goes in a contradictory to other belief. So this paper met with a lot of rejections, and when it published, also we get a comment from a renowned group who are doing monsoon research. Now coming back to pre-onset land surface conditions and its relation with monsoon. So first phase of monsoon, here we have considered June, and pre-monsoon is April, May. So this is a study from our group that shows that if we take June rainfall of all India and correlate with April, May temperature, surface temperature everywhere, you get very strong correlation over this region. Similarly, if you take rainfall instead of 2-meter temperature as a proxy of soil moisture, you get a correlation, but it is little weaker. Okay, so this is about South Asian monsoon. Now, if you go East Asian monsoon, there are several studies. One of the study by Yu et al., which shows that if a Tibetan plateau temperature has a strong relation with East Asian monsoon rainfall in June. Around the Yangtze River, you have a dipole pattern. And there are several studies, some studies with the western part of the Tibetan plateau, some eastern, and they also that it has a strong relation with East Asian summer monsoon rainfall. Sorry. So if you see the how the monsoon evolves, this is the mean rainfall during May. You have a rainfall started already in East Asia, some in Bangladesh, and something in South India. And if you go to June, monsoon almost covers the entire country and South Asia, and you have a full monsoon in June. And if you see the standard deviation, internal variability, so you have very strong internal variability over India, also in East Asia during May, and June also you have a strong variability there. So often we study monsoon regionally, and sometimes we overemphasize and forget about large scale. What is the large scale? So you can see that in a contour plot, you have a Tibetan plateau sitting here, which is a heat source, which is a heat source, sensible heat source, which hits the upper atmosphere. And pre-monsoon condition, pre-monsoon, first phase of monsoon, this is quite important. And so we ask the question that as this is the large scale system, is there any mode of variability in the first phase of Asian monsoon that is related with land surface condition? If it is so, how it looks like, how it is related to other things like this. So to do that, the easy thing is that we did that, take the UF of 119-year rainfall of June. So this is the first UF, which explained about 12% variability, and then second, third. I will talk about first UF. What you see here, that it has a very clear dipole pattern in East Asia, okay, and then monopole pattern over India and the Indo-China Peninsula. So this is matching what we saw the two earlier studies independently they have done, and this is done with actual data, not detended. So you can see there is no trend actually in these species. Okay, so now the question is how this first mode is related. First mode actually explaining this both earlier study what I showed, how this mode is related with land surface temperature. To do that, we correlated with PC1, April temperature and May temperature everywhere. So you can see there is a correlation over this part. And then in May also a very strong correlation over western Tibetan plateau. We can see the contour, western part of Tibetan plateau. It is 1.5 kilometer height contour. And at the same time, you can see in the China Peninsula region, you have a negative correlation, which are very significant. So this region also we know that it is hits up the atmosphere. It creates the tropospheric temperature gradient, and it has some relation with monsoon onset. Monsoon onset also there are many studies shows that it is clearly related with tropospheric temperature gradient. So we try to see how it is related with Kerala onset, this temperature over Western Tibetan Plateau, the box you can see. So you can see the Kerala onset, it is the data from IMD, more than 100-year data. You have very robust correlation. And this region temperature is also related with local condition like glaciers. This region is a home of many glaciers, mountains. So Karakoram height. So you can see there is a very strong correlation between snow water equivalent over this region and surface temperature. So this is clearly related with some local land surface conditions. Okay, now just we assume that it can affect the troposphere, but is there any link, really any link with this temperature, surface temperature of Western Tibetan Plateau with atmosphere, upper atmosphere? Okay, so to do this, we correlated with simultaneous correlation with monthly temperature and regression with vertical velocity, what you can see in arrow. Okay, and it is a month. So you can see in the April, May, you have very strong positive correlation and vertical ascent there. And when you have a monsoon, it is little weaker. This is understandable because when you have a monsoon, so this upper troposphere heating is mainly contributed by latent heating, so it is suppressed. And then when monsoon gets over, you have again heating from low. So this heating actually, this region actually clearly links with the heating of the troposphere temperature. Now, I have shown both correlation positive and negative. Okay, so this negative correlation, why this negative correlation? Some study shows there is a Bay of Bengal in May, there is convection. This convection may generate westward propagating Ross wave. So this temperature may be response of this. Okay, this is the possibility. So to trace this, what we did that we plotted annual cycle of climatological annual cycle of temperature over this region and rainfall over this region. You can see. So there is clear shift in annual cycle. So first you have a picking up temperature and then you have a rainfall. Furthermore, if we regress this to annual cycle in lead lag, you have a clearly 50 days lead of temperature over Western Tibetan Plateau. So this clearly that this is the first leading, and this enhances the tropospheric temperature gradient, this enhances then rainfall and the convection over Indochina Peninsula. Now, how such rainfall pattern is created? Now you have a correlation with heating over this region, but how we get rainfall pattern of complex rainfall pattern of like this? What is the mechanism? So to understand this, we regressed temperature WTP temperature of May with geopotential height simultaneously, and then you can see a wave stationary wave pattern is going around, and then also over US also probably it has effect some in a remote region. And if you regress with June also, June 200 hectopascal geopotential potential height, so you get also this pattern persistent remaining. So this is clearly dynamically linked and it is affecting the remote region. Okay, now coming to the second phase, that this is all observation. So how are our model? Okay, are this model able to get those benefit of this land atmosphere interactions? So that is a project GVX, and this is under GVX LS4P initiative with how the initial land surface condition affect the first phase of monsoon, that is June. And there are several participants, more than 40 models participated, including our IITM model. So we have taken 5 models from this project, and 30-year reforecast all started end of April and simulated up to June. So you can see the first UAF from observation. What do you see? Observation, and then the rest are the model. You can see this CFS is doing little better, but all model are not good over East China. They are good in over India, but not over East Asia. Okay, and if you see the correlation between Western Tibetan Plateau temperature and everywhere. So this is observation for 119 years. This is for last 30 years, 81 to 2010. And this is a model, 4 model, and this is multi model. You can see CFS is not so good, but all model are doing better over India, but not over East Asia. All model are failing. So except ECMWF, it is little better over East Asia. Okay. Now, if you look in the temperature, surface temperature, 2 meter air temperature, this is very important. All model, how they are simulated June temperature, May temperature. So this is a CFS, AF is
FES, E3SM, ECMWF, and NASA GS5. So except ECMWF, very promising. All model are very poor in monthly simulation. The model all started in end of April, and this is a scale of May. So one zero lead scale is quite poor. So clearly, all models are not able to get the benefit of these land atmosphere interactions, and that may be the one area where we have a possibility to improve scale. So now coming to the conclusions, that we identified a dominant mode of variability in June rainfall, which cover entire Asian summer monsoon region, and this mode is linked with spring land surface temperature over Western Tibetan Plateau, or some people call it Western Third Pole or Third Pole Tibetan Plateau, and a strong relationship with LST, with snow water equivalent, vertical wind, tropospheric temperature. It suggests that there is a strong land atmosphere interaction which affect the first phase of Asian summer monsoon. And clearly we have a deficiency in model, and we need to work out, and then probably we get better skill. Thank you. So if you want to know more, this is the paper we can look for. Thank you.
Thank you, Subodh. Any questions to the speaker? So I myself have a question. See, all these models are initialized with the same land in data set. Initialization is done with same.
Not same. Some like CFS, we use CFSR, ECMW, their own initialization.
Okay.
So these are
different models have different initialization.
different initial. Yeah.
Hi. So you don't detrend before you compute the EOFs, but that means that you'd probably be overestimating the amount of variance that's due to the first EOF, and your first EOF is probably going to be quite strongly coupled to the trend as well. Why did you not detrend first?
We detrended, and without detrending, we have done. There's no difference. Because I showed here without detrend to see the PC, how the PC different modes are changing with time. But if you detrend, you will see same, more or less same. This is 119-year data, so this is quite robust.
Okay.
Thank you.
So we'll move to the next presentation by Yuan Recheck. How well do reanalysis represent the dry to wet season in the southern Amazon? Is online talk? So is there? Chen, are you?
Okay.
Yeah.
Can you hear me?
Yes.
Can you hear me?
We can hear you clearly.
Okay, so I will begin. So thank you for this opportunity to participate in this very interesting workshop about monsoon. And for me, I'm Yuan Rui from the Tsinghua University, and I'm supervised this work by Professor Wright, and who will just give a talk after me. So for this talk, we are focusing on how well do recent reanalyze represent the dry to wet transition in the southern Amazon. So I'd like to first show some idea about what is the southern Amazon. It's just a transitional zone from tropical rainforest to the subtropical savanna, which is kind of a grassland. And it's make up about 30 to 40% about the Amazon, and it's very important for the global water and carbon cycles. There are two factors that make this area more interesting in recent years. First is the hydroclimate margin for the substantial reinforcement, and the second is the recent rapid land use changes. So the rainforest in this region is very vulnerable to the climate change. And for this talk, we will focusing on the transitional dry to wet transitional, which is widely talked in this workshop about like the monsoon onsets. So in this area, we are divided the transition into 4 parts: the pre-transition, the earlier transition, the late one, and the wet season beginning. We will see such a propagating of the precipitation pattern, and then we will have two distinctions that is very critical for understanding and projecting climates in this region. So first is that what's the effects of deformation on the on-site time? So if the sensible heat, there are some errors in the PowerPoint. So if the sensible heat driving is very important, then we will expand a very increase in the on-site. But if the reinforcement evaporation is driving, then we will see a delay of the on-site time. And the second question is, how do we understand the increased drought frequency? So if the local boreal rates speak for the story, then it will be irreversible. So if we expect the large-scale mode to be the character, then the natural variability is what we will expect. However, the poor climate model presentation on this area indicates that the studies are often rely on the reanalysis. So here come our question: how well do this reanalysis reproduce this evolution? As the complexity and content of the reanalyzed intercomparison is a little bit complex, and I'm going to avoid you falling asleep with following such a table. So first, we will begin with the onset pattern. Here is the timing and variability. And arrow 5 best reproduce the variation in the onset time, as we can see from the green box on the right side. And also, we have that all reanalyzed as show very strong agreement with the satellite-based estimates than with the Gauss-based DPCU. And another thing is that for the down panel, we have the observation and the reanalyze. We will show that the observational suggests a very strong long-term delay of these things, but are not unanimous thread in the observations. Well, this trend toward earlier onset is observed from the reanalyze. So for these parts, we do observe some difference between observations and reanalysis. And then for the timing and the variability, for the left 4 boxes, we having the observational analysis, and it's mostly consistent in the on-site timing, which is about 59 pentads around October 22. The onset in Mary 2 is generally very late compared to the observation, as we can observe from the red bar. For the blue bar, we have the arrow 5 and arrow intern, which is a little bit slightly earlier, but is generally consistent, while the JRA3Q in this round prevail, as it's most close to the observation. And for the precipitation bias, we now select the late transition time, and we can see that arrow 5 is very similar to the trim and the JR3Q, and both Mary 2 are kind of overestimate the precipitation. And we have too much moist export in the Mary 2 as we observe from this pattern. So for the first parts, we can see that the arrow 5 and the JR3Q do kind of a good job for the onset and pattern, but Mary 2 have some difference with both the onset time and the pattern distribution. So for the next time, we will following on the transition. And for the transition, the first we will see the OLR. Here we use the clear sky minus the all sky to show the deep convection. And we can see a very strong deep convection propagating southeastward from the northwest as going through the time. And for the arrow 5, it's very similar to the Ceres. And for Mary 2, we see too much convection in it, which accompanied with the contour is the geopotential, which shows that it have a distortion of these geopotential heights. And if we're moving on to see that, we will also show a very strong dry season divergence and weak convergence in the Mary 2, which is the red line on the upper panel during both transition seasons. Also, we can see that the JR3Q is kind of overestimate the high clouds in the middle panel. And for the Mary 2 models, it struggle to capture the shallow convection, which is kind of limiting the pumping effect. So for next part, we are showing the evaporation. And for the evaporation, still arrow 5 is good. And the JR3Q in this term have a very bad performance as it overestimates the local evaporation. And if we see from the integration, we will see that the purple line indicates this evaporation of JRA3Q is very large compared to the observation black line in both transition seasons. And also for the relative humidity and the heating rate, we will show that the MERI2 shows a very large relative humidity close to the surface, which could kind of suppress local evaporation transpiration. So now we have a callback on the precipitation bias. And we will see here the bias are connected to the what we've discussed about the transitions, with the MERI2 is kind of too much deep convections and overestimate exports, and the JRA3Q have overestimate evaporation. So now we partly summarize that for the transition parts, MERI2 kind of underestimate local evaporation and overemphasize the moisture exports. And for JRA3Q, yeah, it's just overestimate the evaporation. So for the next parts, we'd like to explore the energy budget as it's not closed in the realized products and need a simulation to compensate these effects. Before I would briefly go through such a shallow convection moisture pump. So it just contains 3 processes with the diurnal mixing across the boundary layer, and then it's the shallow convection, which followed by a deep convection in the blue. So here, if we see from the lower panel from the cloud cover, we will show that we have a low cloud cover increase earlier than the high cloud, which kind of supports this pumping effect. So the reason that we are focusing on this pumping effect is that this shallow convection pumping is very important for preconditioning the atmosphere for deep convection. And here is a very complex figure, but if one figure can leave you an impression of this talk, I think it will be this one. So for this, we are focusing on the equation downside. We divided the tendency into the dynamic part, the physical part, and the residual part. With the physical part on the upper panel is then for the turbulence and the moisture convection, which we will see a very flat moistening in the MERI2. While for the dynamic advection parts, we see an earlier convergence in both Aero5 and JRA3Q, but a strong divergence in the MERI2 as we discussed before. What is most interesting is about the simulation parts. We observe a strong systematic errors in the MERI2, which is a very large positive assimilation increments. This could partly explain the origin of why we have such stronger divergence, but still have a general pattern in the theta E that we showed before. So here we come to a final conclusion of this talk. So we have energy budget that both Aero5 and JRA3Q have earlier convergence, but for the MERI2, it have a strong assimilation increments offsetting the moisture convergence. So if doing just a brief summary, we provide the Aero5 with the rank A, but the MERI2 with the rank C, because it had problem on both onset and the pattern, which is related to the transition parts and can be partly understood by the assimilation increments, which provided by the energy budget. And here is a large-scale SST. Limited to the time, I won't spend much on it. So the general idea is MERI2 does not capture the relationship in the large-scale SST and local precipitation. So here is a brief take-home message. How well do you reanalyze represent the transition in South Amazon? Our result shows that we have bias in reanalyze, and this bias is very large in MERI2, and is smallest in the Aero5. And the origin of the bias in MERI2 is the reduced moistening, which is compensated by large-scale positive assimilation. And for the outlook, we have 2 questions. So the first one is, how do we understand this bias in reanalyzed products? Because we need to use it. So we need to kind of understand one and where could we expect to have such bias? And the second is how could this bias or how could this reanalyzed products perform on different area like the India monsoon that we talked in this workshop? And I think this kind of question would be partly understand or answered in the talk just next me. So here is my presentation, and I'm very looking forward to your questions.
Thank you, Jonathan.
Yeah, I'm not Jonathan. Yeah, I'm Yuri. So we are using the same accounts.
Okay. So any questions from the audience? No, I think. So have you done a similar analysis for Indian monsoon transitions?
Yeah, for the India monsoon things, I think the next talk will partly answer this question. Yeah, this is very interesting.
So we'll wait for the talk then. So
Yeah.
Yeah.
Sorry, thanks for the nice presentation. Yeah, very clear. You were showing that Era 5 performs the best. You ranked at A. But if you were going to do a study that was using the reanalysis data set, would you still see benefit of using, say, J3Q as well, like not just relying on the one data set? Or do you think?
Yeah, that's our main philosophy. Yeah, to use more than one reanalyzed data set, because you can see from this talk that different reanalyzed have different biases. So if you want to provide a solid work, its best option is to use at least more than one reanalysis. Thank you.
So actually it is coming out very clearly that using assimilation increments for process studies is not so good. Okay, so we'll continue to the next topic. I hope you are going to give the same. So next talk is about climatology and covariability, dynamics and composition in the Asian monsoon tropopause layer.
Thank you very much. So I've changed things a little bit, climatology and covariability in the Asian monsoon tropopause layer. And for the sake of time, I've eliminated a lot of the covariability part. I also was feeling a little bit out of place in this session at the beginning, but as the session has gone on, I think there's really a nice theme developing about the connections between the different regional monsoons. And the upper level circulation represents a key component of that connection, not just among the different regional monsoons, but also between the monsoon and the Northern Hemisphere as a whole. For the purposes of this talk, what we really need to know about the upper level circulation in the monsoon is that there's relatively little ozone, there's lots of water vapor, and the air that collects near the tropopause can be quite polluted, forming what's called the Asian tropopause aerosol layer. In this talk, we'll represent that through carbon monoxide rather than aerosols. Right, so the observations are largely coming from the Aura microwave limb sounder. One of the main motivations for doing this work is that Aura MLS will soon be retired. And when Aura MLS retires, there won't be very frequent observations of this part of the atmosphere at all. And so as a consequence, we really need to assess the ability of reanalysis products to reproduce the composition in this region because it's a major conduit to the global stratosphere, and also the potential for reanalyses to do this without relying on Aura microwave limb sounder. So a lot of the figures will follow the same kind of approach. You can see here on the south face, this is an east-west transect between 15 degrees south and 15 degrees north and 25 degrees north. So representing the south flank of the monsoon anticyclone. On the east face, there's a zonal average across the entire domain from 30 degrees to 130 degrees east. And on the top face, we're vertically integrating from about 150 hectopascals up to about 70 hectopascals to give a partial column value for water vapor, ozone, or CO. We're using reanalysis products, and just to kind of introduce exactly what goes into a reanalysis, we have three components. First is a global atmospheric model. Usually this is a well-tested earlier version of an operational weather forecast model. And in this talk, we're looking at two different types of reanalyses. Reanalyses like ERA5 and JRA3Q that focus on the meteorological components, and reanalyses like CAMS and M2 SCREAM that focus on atmospheric composition and chemistry. So there are some substantial differences between these in terms of how they approach data assimilation. The second component is input observations. And in this part of the atmosphere, this is especially important because reanalyses make very different assumptions about or limitations on what observations go into the data assimilation system, and particularly how they influence water vapor. And the third component is a data assimilation system. And here again, there are key differences because in some reanalyses, assimilation increments are suppressed above the tropopause. So you don't get these spurious influences from assimilation in the troposphere influencing what's happening in the stratosphere. Other reanalyses don't suppress, and other reanalyses still will relax stratospheric water vapor to a climatology, and that essentially eliminates all interannual variability. And so understanding these differences and seeing how they influence the representation of composition is one of our main objectives here. All right, so first off, I want to introduce, so on the left-hand side, we again see this climatology from the Aura microwave limb sounder. And on the right-hand side, this is from JRA3Q. And we can see there's a slight moist bias in the partial column. This moist bias is actually somewhat larger in the lower levels. And there's some compensating biases. So JRA3Q is not necessarily doing quite as well in the absolute humidity as you might interpret from that number. This moist bias is pretty consistent across reanalyses. Almost all of them are indicating more water vapor than Aura microwave limb sounder. However, the reanalyses do a very good job of reproducing regional anomalies. And so what that tells us is that those biases are hemispheric in scale. And so if we want to look at the variability within this region, we have a very good chance to do that with the reanalyses. In particular, because the reanalyses provide this means of breaking the budgets down in a mechanistic way. Right? And so again, we can see here the different regional anomalies from the zonal mean. MERA2 and ERA5 have absolute wet biases that are slightly smaller than the zonal mean. JRA3Q, CAMS, and M2 SCREAM, it's very similar to the zonal mean. And so that implication is that the biases in water vapor are hemispheric, and they're not specific to the monsoon region. Right, so now I'm going back to something that Yare introduced, which is these budgets. In our case, we're using a water vapor budget. Right? And so we have a tendency of water vapor, which is related to the moisture flux convergence in the horizontal and vertical dimensions. And then on the right-hand side, we have physics, assimilation, and a residual. Right? So the changes result from dynamics, physics, which is processes that are smaller than the cell, like radiation, turbulence, and clouds, in this case, turbulence and clouds, and data assimilation. The residual in this formulation, because we are explicitly calculating the assimilation increment, belongs to dynamics, but I won't spend more time on that. And so we can break down those budgets. This is showing us what we see from the dynamics. We see very strong moistening in the east, and associated with the vertical moisture convergence. And then in the west, we have a horizontal moisture convergence, which is balanced by a vertical moisture divergence. The physics terms are generally negative, right? And so this is indicating the influence of large-scale condensation. Turbulent mixing will tend to moisten the upper levels, and that's associated with the convective moistening effect. And so the dominant balance in the reanalyses is, as we should expect, between advective moistening, this is actually taken directly from the forecast rather than calculated afterwards, and condensation drying, as we see here. Right? So JRA3Q dynamics and physics are producing the dominant balance. If we look at the assimilation increments, they look relatively small compared to the dynamics and the physics terms. However, if we think about the balance being between dynamics and physics, and that those two are compensating each other quite substantially, the assimilation increment is actually a very large component of the budget. Here we're looking at ozone. In the monsoon region, we generate a low in ozone concentration that's contributed by dilution of the background ozone by strong convection. And this is represented to different levels by different reanalyses. Here We can see JRA3Q and ERA5 are not doing quite as well as MERA2. So MERA2 is the only meteorological reanalysis to do well in this aspect. However, if we look at the budget, so here we can see this is dynamics in the upper left, and this is assimilation in the upper right. We have chemistry and physics in the lower panels. The chemistry and physics are quite small, and the dynamics and assimilation are producing the dominant balance. And in particular, this ozone valley is being maintained by the data assimilation. So MERA2 relies heavily on data assimilation. It would not be able to reproduce this feature nearly so well if it weren't assimilating or MLS. We've also looked at carbon monoxide, and here I want to really emphasize that very few reanalyses are including carbon monoxide at the moment, but this is something that really would be very valuable for model evaluation, and so it would be extremely valuable for more reanalysis centers to include carbon monoxide. Both in terms of the variability and in terms of the climatology, we see very good agreement, qualitatively speaking, with Aura MLS. And it's a very valuable transport tracer, especially in these altitudes. And so I'll just briefly recap. All of the reanalyses have hemispheric moist biases, but regional anomalies are captured very well. The main balance for water vapor is between advective moistening and condensation drying, but the data assimilation is comparable to the sum of those. The reanalyses broadly capture the ozone valley, but this seems to depend quite a lot on data assimilation. But overall, our conclusion is that reanalyses are increasingly able to capture, especially intraseasonal to interannual variability in the UTLS water vapor, especially in active troposphere to stratosphere conduits. I've skipped over a lot of the variability part just for the sake of time, but I'm very happy to address that in the questions if there is sufficient time to do so. What we also find is that trends in long-term variability are much less reliable. And this is true not just for UTLS composition. If you were looking at reanalyses for trends, you want to do three things. You want there to be consistency across reanalyses. You want there to be a very strong and compelling physical mechanism for the trends. And you want to be able to identify the trends in ideally independent observations to be able to be confident that it's not resulting from changes in the data assimilation. For the outlook, the end of life for Aura MLS is going to leave significant observational gaps. And there's a lot of variability here. It's really critical for the evolution of the global stratosphere. There's recent work indicating that very short-lived chlorinated compounds reach the stratosphere through this conduit very effectively, and that has an important impact on the stratospheric ozone budget. Development of retrieval-based assimilation tools for sparser UTLS water vapor observations show some promise. There have been some recent experiments looking at incorporating SAGE 3 or assimilating SAGE 3 observations. They're very sparse in space and time, but because this balance is between advective moistening and condensation drying, really, if you have a few constraints, you can generate a very good distribution overall. The ECMWF reanalyses do better in water vapor, and primarily that's because they prohibit increments above the tropopause, and they basically just let the model do its thing. JRA3Q shows substantial problems above the tropopause, primarily because there's still this leakage of assimilation increments from below. So observations in the troposphere are influencing the humidity in the stratosphere. And so prohibiting those increments in more reanalyses would make these products much more useful and more useful also in a kind of ensemble sense, right? To get a broader picture. An inclusion of CO or CO-like tracers would be very valuable, even if they're not assimilated, for model evaluation and for process studies, right? So I want to give a brief plug. A lot of this is work that's come out of what was previously the SPARC Reanalysis Intercomparison Project, now APARC. You're very welcome to contact me at the email address here if you're interested in learning more about this. And you can also get more information from the report that we published in 2022. In particular, the documentation in Chapter 2 should be very valuable for anyone who's using reanalysis products in terms of understanding what goes into them and how they might be different between each other. Thank you very much. I'm very happy to take questions.
Thank you, Jonathan, for a very Excellent talk. So any questions from audience? Yeah.
Perhaps I missed it, but could you briefly explain how you calculated the increments from the data assimilation, that bit?
Yeah, absolutely. Right. So for Mera 2, this is provided directly. So that makes it easy. For ERA 5 and for JRA3Q, because these are incremental 40 var systems, what we do is we take the forecast fields and the analysis fields, calculate the difference, and then multiply that by the number of cycles per day to get a rate. Right? And in both cases, we can show that this reconstructs what the increments ought to be.
Okay. Any other questions? So next presentation is on interactions between the triple dip. I don't see it here.
Thank you. I'm Ankush Srivastav, and today I'll be talking about the interactions between the triple dip La Nina, the Indian monsoon, and the Indian Ocean dipole. But let us make things more interesting. I would like to call this as a multi-year negative Indian Ocean dipole of 2021-22. The reasons for which I will come in the next few slides. So this is a collaborative work between our colleagues at the Met Office, Dr. Jill Martin, Dr. Sarah Arneson, and my colleagues at IITM, Dr. Surya and Dr. Maheshwar. So as we the plot here shows the NINO 3.4 index for the period of 2020 to 2022. And as we all know that these 3 years saw the triple dip La Nina, which you can see clearly here. And we all know how the La Nina interacts with the Indian monsoon. There is an associated modulation of the Walker circulation so that you have increased convection over the maritime continents and the Indian longitudes, and you have suppressed convection over the eastern central equatorial Pacific. So La Nina events are often but not always associated with above normal monsoon rainfall. So the question we wanted to ask here, and from the motivation for this study came from, how did the triple dip La Nina impact the Indian monsoon? So if you look at the rainfall maps from the Indian Meteorological Department for 2021 and 2022, what you can see is that the country average departure was 99% of long period average and 106% of long period average. So 2022 saw somewhat above normal monsoon conditions, but not such a large excess which we usually associate with La Nina, which can go up to 110% of long period average. So the question we want to ask is, why such a persistent and large scale signal which lasted for 3 years in the Pacific did not have an intended impact on the Indian monsoon? So then we looked at the second most important modulator of the monsoon, which is the Indian Ocean dipole, and which is associated with warmer temperatures over the IOD East Pole region along the Java Sumatra coast and cooler than normal temperatures over the Western Arabian Sea. And this, whenever you see a negative Indian Ocean dipole, there's a modulation of the regional Hadley circulation, which can suppress the rainfall over India. So if you look at the dipole mode time series since 1960s, for the September to November season, what you can notice here is that it was the strongest and a negative IOD event on record since 1960s. And if you look at the monthly evolution, if you look at the monthly evolution of the dipole mode index, you would note that the dipole mode index was negative since May of 2021, and it remained negative till the end of 2022. So the dipole mode index was negative for an unprecedented 18 months. And we hypothesized that the negative IOD opposed the La Nina's impact on isomer. Then we looked at the other negative IOD events that have occurred since 1960s, and the black curve here shows the evolution for the 2020 to 2022 event, and the year -1 means the previous year. The event year means that 2022 event. And what you can notice here is that you do not see such a long 18-month negative Indian Ocean dipole conditions in any other event. So this is the first documented occurrence of a multi-year negative IOD event. Now we also know how La Nina interacts with the Indian Ocean dipole. Often negative IOD events are associated with La Nina type events. Why? Because of the modulation of the zonal Walker circulation. You can expect westerly winds to intensify along the equator, allowing warm waters to concentrate over the IOD East Pole region, and which can set up a temperature difference across the tropical Indian Ocean. Therefore, we wanted to look at the zonal wind anomalies. So the plot at the top shows the evolution for 2020 to 2022. These are the daily wind anomalies, and you can see a persistent westerly wind forcing during these events. And if you contrast it with other negative IOD events that have occurred, you do not see such a long and persistent westerly wind forcing. There were some episodes of easterly wind events in between, but they were very short-lived. Then we looked at the statistics of the westerly wind bursts. So shown here are the counts, the number of westerly wind bursts that occurred in bars, and the cumulative duration in days. So for the 2021 and 2022 event, these 2 years witnessed a record number of westerly wind bursts in the Indian Ocean, and the cumulative duration was about 21 days. And even the 2022 year had a cumulative duration of 12 days, which was the fourth largest since 1980s. So how do westerly wind bursts interact with the Indian Ocean is also known. These strong westerly wind bursts can cause Wertke jets in the Indian Ocean, which are important for the heat and mass transfer in the Indian Ocean. So what we believe is that what you see here is the 2 degrees south to 2 degrees north average zonal currents in the upper ocean, and the y-axis is the longitudes. And what you see here is that the vertical blue lines are the occurrences of the westerly wind bursts. So first, you will note the first event which occurred in January 2021, which is highly unusual. The wind bursts are never seen in January, but this happened, which stretched the fall Wertke jet of 2020 to the initial months of 2021, and this caused a large ocean heat buildup in the eastern Indian Ocean, eastern equatorial Indian Ocean, and the subsequent events which occurred during late May 2021, and the event just close to monsoon onset. So this persistent westerly wind forcings caused a change in the climatological cycle of the Wertke jet, so that they occurred earlier than they are supposed to occur, and the demise also was later than. Just before monsoon onset, you can see the Wertke jets, but you can see they lasted beyond June, and then there was another westerly wind burst during the summer monsoon of 2021, which caused these zonal currents to be weakly eastward, and these led to the development of negative IOD type conditions in the Indian Ocean. Now, if you look at the 2022, similar events occurred here. But what bridges the gap between these 2 seasons? What caused the dipole mode index to be negative for such a long time was the intervening period between December 2021 and March 22. So you can see there was strong westerly wind activity during February and March as well. And these were not strong enough to qualify as westerly wind bursts, but indeed they were so strong that they could cause the early demise of the currents of the westerly currents in the Indian Ocean. Okay, so then we wanted to know whether these westerly wind bursts were caused by the MJ or the BSISO phases. So what you see is the dates of the westerly wind bursts and the associated BSISO and MJO phases. So what we note here is that 5 out of the 8 events were caused by BSISO phase 3 or 4, during which the convection is located over the Eastern Indian Ocean. And if you do a scatter plot of the wind speed during these dates and the Southern Oscillation Index, which is a measure of the Walker circulation, so you will see there's some relationship between the Southern Oscillation Index and westerly wind bursts. Now, people believe that the westerly wind burst occurrences are random, and it is true to some extent, because you can see many of the events between this ±7 envelope, but you do see events do occur when the Southern Oscillation Index is more than +7, which indicates a La Nina type of state in the tropical Pacific. So we would like to state here that the 5 out of 8 westerly wind bursts in 2021-22 were supported by the La Nina state and were also supported by the BSISO phase 3 or 4. Now, how did they influence the Indian monsoon? So shown here are the Walker circulation in the top panel for summer of 2021 and 2022, and at the bottom are the regional Hadley circulation. So what you can clearly see a La Nina signal here, where there's anomalous subsidence over the Pacific and uprising motion over the maritime continent region and the Indian longitudes here. But when you look at the Hadley circulation, you can see there's suppression of convection over northern India during both these 2 years. So the competing effects of La Nina and Indian Ocean dipole, negative Indian Ocean dipole, are what resulted in a near normal sort of monsoon rainfall during these 2 years. So to conclude, the triple dip La Nina was witnessed in these 3 years, but the rainfall during 2021 and 22 were not in large excess. So the prolonged La Nina conditions conditioned the Indian Ocean towards a negative Indian Ocean dipole state. And there were a record number of westerly wind bursts which were caused by the BSISO phases 3 and 4, and often supported by the La Nina state in the tropical Pacific, and which could help the event to sustain for such a long time. And the competing effects resulted into a sort of near normal monsoon rainfall. And I would like to leave you with a couple of questions. Recent studies have shown that in a warming scenario, the triple dip La Nina events are projected to increase. So there are 2 questions which we would like to address in the future. Do prolonged IoT events become more likely, or do they increase in amplitude? Are questions which we will look into in more detail. Thank you, and I'm happy to take any questions.
So, any questions to the speaker? Yeah.
Hello. In a warming environment, we should expect more El Nino than La Nina. Na? So how triple dip La Nina persisted in spite of a warming, global warming?
Yes, it might be true. You can expect more El Nino, but if you look at the consecutive occurrences of these events, then you will what it is found that the multi-year La Nina events are increasing. So if those are increasing, then we would expect a similar modulation of the Indian Ocean conditions.
Any more questions? Yeah. Are there any online questions?
No.
Okay,
thank you.
Good. So next presentation is again online by Pratik Kad. We'll be talking about dynamics of monsoonal orographic rainfall in the eastern Himalayas. Pratik, can you hear us?
Yeah,
Okay, so go ahead and start your presentation.
yeah. So I'm not able to start my video. Can you help me?
Yeah. You have a video here? Hmm? Yeah, we can see your presentation clearly.
Okay.
No problem. Go ahead. Yeah.
Okay. So, good morning, good afternoon, everyone. So, my name is Pratik, and I would like to talk about the dynamics of monsoon orographic rainfall in the eastern Himalaya. So I did this work when I was affiliated to Busan National University, South Korea. So 80% work is published in a paper. You can access that paper using this barcode. And right now I'm affiliated to NORS at Bergen and Berkeley Center. So today I would like to give my talk in four parts. First, I would like to talk about the background of my study, then the motivation, and after that I would touch on results and then summary. So this is the background. Like we can see there how lot of things are happening due to the flooding events in Brahmaputra River. So like the flood in Bangladesh, in India, also in Nepal, and there is also threatening like the glacier is melting in the Himalayan region. So also we can see there is a like natural hazard which coming in a Kaziranga Park in Assam state. So these all are extreme event which is linked to the monsoon in this region like eastern side of Himalaya. And in order to understand those factors, the topography where which plays the important role for triggering these events. So we can see here the steepness and the topography which is like 3 kilometer, around 2 kilometer, where we can see more than 50% of steepness that we call as a Himalaya. And if you see the population density in this part, the population density is below to this region. So this means that this region, like downstream of this region, is a vulnerable region for lifeline for the populationally dense region in the world. And also we can see there is a big river system like Ganga and Brahmaputra, which are also occurring in the same region. So what is the motivation for this study? So motivation is that right now, due to the global warming, we have more extreme events is due to the rising temperature. Also, there is the snow melt and flash flood is causing flooding in Himalayan river. But at controversially, we have decreasing trend in mean monsoon rainfall and extreme in this region. Also, there is a limited study available on the Himalayan domain, like Himalayan monsoon and its variability. So that triggered me to dig more. So in this figure, you can see that the upper panel is mean climatological rainfall for JJS, and the below is the rainfall trend. We can see there is in an eastern side, we have decreasing trend in rainfall. Still, we have more extreme events. Secondly, we can see the climatology, like precipitation climatology, is also matching with the variability. When we have more mean climatology, there we have more variability. Secondly, the rainfall, the annual rainfall over the Cherrapunji, like you all are in Pune right now. So Pune annual rainfall is 800 mm in a whole year, like annual mean. But for Cherrapunji or in Meghalaya, it's too much high, like it's the wettest land in the world. We can see that, and this region is also belongs to this the Himalayan monsoon system. Another thing is that the question which motivated me, like why we have the dominated variability over the steeper range of Eastern Himalaya. So in order to answer those questions, I have used the different data sets available from 1979 to 2021. And here these data sets are in two kinds of data set. One is a reanalysis data set and another is an observational data set. So this panel is showing the precipitation climatology. And we can see that the precipitation climatology in all data sets are varied, but they're matching with where we have stiffness in the eastern side. There we can see more precipitation. Also, the variability in this region, we can see that is dominated, and ERA5 and IMDA is matching with each other. If we decompose this in a power spectra, we can see that even though the data set are different, they're matching with the correlation is really high among them. So the data validation says that even though they have precipitation amount is different in different location, but still it's captured the climatological mean feature and the precipitation variability. As my objective to deal with a global thing, so I use the ERA5 for my study. So now this is the result part. So here in upper panel, we can see that there is a precipitation map for variability. And we can see that the precipitation anomaly are more dominated over eastern slope of Himalaya. And if I took those high variability as a matrix, then I can detrend those precipitation signal, and I can plot the composite for wet and dry year. So the detrended time series is below, and we can see the standard deviation when higher. I have chosen as a wet year and dry year. And so the another thing is that in previous figure I showed about the precipitation, but there is also the role of melting snow. So most of people they are blaming like the ice sheet is a dominant factor, or melting snow cover is causing the floods in those regions. When I decompose those things in a wet and dry year, we can see that during the wet years we have anomaly, the high flooding anomalies. And when we see in a dry year, it is a list. And I have plotted the anomalies like river discharge, snow melt, and rainfall, we can see that most of contribution is coming from the rainfall, which is 0.88, and the snowfall here, the snow melt, which I have plotted, which is also following similar kind of feature, but I have multiplied by that factor by 5. So overall, the precipitation, which is rainfall precipitation, is a major contributor for this reverse discharge from this decomposition. If you want to know more, you can just see this paper, and then you can understand. So in order to see the climatology and the atmospheric feedback, I have taken the cross section over 94 degree, and the upper panel is showing the climatological temperature, relative humidity, mass static energy, and buoyancy. And the middle panel is showing for wet years, and the below panel is showing for dry years. So in the upper panel, the temperature, we can see that temperature is showing decreasing with the height, and the relative humidity is more over the stiff orography, like it's more than 90%. And the moist static energy also followed by temperature and the relative humidity, which we can see there is a least moist static energy over the summit of mountains, like here in this two summit, we can see that. And the buoyancy is followed by the tendency of vertical motion, which is also in the valley of this Himalayan range. And the point when I had looked the wet years and dry years composite, we can see the positive anomaly in this region, and the negative anomalies here. So it means that the physical parameters like for this dry and wet year are consistent. And secondly, now the important question is that is due to the moisture or due to the dynamics. So the thermodynamical parameter are more important for the monsoon, which we know. But in this case, what I tried, I had decomposed 3-dimension moist static, the moist flux conversion into dynamical and thermodynamical part. And here we can see that in wet year, we have low level conversion at the low level. And here we have low level diversion for dry years. So when I have split this thing in a dynamical and thermodynamical things, I need to multiply the thermodynamic factor by 10 because it is a JJS mean. But still, we can see that the dynamical factor modulate this moist flux conversion, and the most of contribution is coming from the dynamical moist flux conversion. So it means that this plays a leading role for the wet and dry events in a Himalayan monsoon. So this dynamical moist flux conversion is connected to the Hadley circulation, which we call as a monsoon circulation. So what I did here, like I took a monsoon Hadley circulation for wet years and dry year. We can see that during the wet years, this circulation is so strong, but during the dry years, we can see the stream function is not that strong. And in order to understand those things, at some point, the monsoon is nothing but ITCZ, intertropical conversion zone. So what I did, I took a vertical average from 700 hectopascal to 300 hectopascal stream function, and that will tell us about the ITCZ. So here we can see the ITCZ map, and so we can see during the wet years, there is a narrowing of ITCZ. And during the dry years, we can see the wider ITCZ. And here is the degree, how much reduction and increase in ITCZ. So this ITCZ is indirectly, or the Hadley circulation is indirectly connected to the Walker circulation, which has the equator. So here I have chosen the Walker circulation for wet years and dry year. So this seesaw will play the important role for driving this meridional circulation in the monsoon, which is connected to the Himalaya. And here you can see in the upper panel is the atmospheric Walker circulation. And for the down panel is a background sea surface temperature. And for the wet year, we can see there is a strong convection in Eastern Indian Ocean, and there is a reduction, this increased convection is coming from the warm SST in maritime continent. And for the dry year, we can see there is a reduction in those regions, like over the Indian Ocean. So that's mean that the Walker circulation is playing important role to the Hadley circulation. And in summary, this is schematic diagram. So in schematic diagram, I'm proposing that we have a stronger convection over the Indo-Pacific warm pool that triggers a Walker circulation. Then this Walker circulation is connected to the meridional returning circulation and ITC shift, which is like local Hadley cell of monsoon. And then this local Hadley circulation is interacting with the locality of mountain region in Himalaya, like eastern side, and which will impact the moist flux conversion there. And at some point, due to those things, we have dominated variability in eastern steep Himalayas. So I would like to give you 3 points to take home message. Like first is this study found the natural variability in eastern Himalaya over the steep topography, and the dynamical moist flux conversion plays a leading role in monsoon, which is driven by the moist processes and shift in ITCZ. And last thing is that there is the importance of atmospheric dynamics for monsoon dynamics is shaping for variability in this river. So if we know this thing, we can able to predict the flooding things or the Brahmaputra and Hima and Ganga. So I'm sincerely thank you all for your kind attention and this opportunity. The 80% the work which I've presented, it is published in this paper, so you can access this paper. And thank you very much for your kind attention. Thank you.
Thank you, Pratik. Are there any questions? No more. Here.
Hi, Pratik.
Hi.
I guess a couple of quick questions. The first one is that the shift in the ITCZ that you mentioned is only 50 kilometers. That doesn't seem like that would have a statistically significant effect on the area that you the area of the size that you had in the Eastern Himalayas. But also, I wondered if you'd had a look at the role of extratropics. In my area of interest is the Western Himalayas, and there the extratropical variability is much bigger as a driver than tropical variability, even when it comes to thinking about the monsoon.
Yeah, you're right. But what happened, like in eastern side, we have blockage. So due to the orography, like the mountain range, the extratropical stuff is not able to push away. And the another thing is not just 50 kilometer, it's just a 0.50. So it's really huge, like because it is in degree. And if you convert in a kilometer, it's really high. And the thing is that there is a possibility like extratropical things can interact. But for instance, what I was thinking, because we need to put this monsoon thing in ITCZ framework. That's why I did that. And at some point, when we are talking about ITCZ, the headly circulation is also connected to the extratropical things. So maybe.
Yeah, that was why I asked the question.
Yeah.
I think it is 50 kilometers because it looks like half a degree.
Yeah,
to
it
me.
is 50 kilometers. But in the dry monsoon, it is much lower, 20 kilometers.
Yeah. But this is just a shift in this thing. But here, if you see, this is just a mean position. The mean position 50 degree, the 50 kilometer will also make a more impact. But if you see here, like the width of ITCZ, it is more important because it is connected to the Walker circulation, which is coming from the equator, like from 0 or to 10 to 10. South or north.
Okay.
Yeah, that's
Thank
my
you,
mind.
Prateek.
Thank you.
Yeah.
Thanks,
Yeah.
Aaron. Thank you.
So next presentation is by Spencer, and he will be talking about more extreme Indian monsoon daily rainfall in El Nino summers. This is supposed to be last presentation of the session, but don't be very happy. We have one more presentation coming up.
All
Spencer,
right.
you can start your presentation.
Wonderful. Good afternoon to you all. You can hear me?
Yeah, we can hear you.
Great. And slides are visible? Great. Okay. Thank you all for your attention here on the late afternoon for you, morning here in New York City. I really wanted to be there, my first trip to India, and it was going to happen, but then it sort of fell apart in the last minute. Nonetheless, I'm really excited to share this work with you about extreme daily rainfall within the Indian summer monsoon and how it varies with ENSO. This work was funded initially by the Indian Ministry of Earth Science Monsoon Mission to Colombia when I was a postdoc there, and it's also received funding from the US National Science Foundation. I am an assistant professor at the City College of New York in New York City. This is based on two papers, one in 22 in Geophysical Research Letters. That was with Adam Sobel, Michaela Biasuti, and Mark Kane that looked on seasonal mean rainfall in ENSO. And a second is still under review. It's been a very frustratingly long review process with the same authors as well as Destiny Myers, Mike Tippett, and Fayez Ahmed. So as many of you know very well, the Indian summer monsoon rain is quite spatially heterogeneous within the subcontinent on the seasonal mean basis. This is a map just from IMD's quarter degree gridded daily rainfall data set from 1901 to 2020 of the JJAS mean rain. And we see largest values in the southwest, this narrow coastal band hemmed in by the Western Ghats mountain range. We see very dry values in the rain shadow just to the east and southeast India. And we have elevated values in the central or core monsoon zone of the northern sort of central eastern part, and then dry values again up in the northwest. In all that follows, we're going to mask out sort of northeast and far northern India, mostly due to data quality issues with the gridded data set up there. So interannually, however, also as you all know very well, El Nino summers tend to bring less summer mean total rain throughout the subcontinent, as well as less number of days within the summer that are raining. So these are correlation coefficients, the maps with the summer mean rain on the left and the number of rainy days on the right, just straight correlation coefficients with the JJAS Nino 3.4 value, again over this 1901 to 2020 time scale. The browns pretty much everywhere signify that these are decreasing with El Nino. So that's pretty all well understood. What has been surprisingly understudied in the literature and what the rest of this project will focus on is what the extreme daily rainfall events are doing under ENSO. There's been a lot of work on trends and the link to warming of extremes, but very little on the interannual ENSO story. I'm going to argue the following. First, that within the wet regions, the southwest and the central monsoon zone, you actually get increased extreme daily rainfall under El Nino summers. And in the climatologically dry regions, you get the more intuitive decrease in extreme daily rainfall. We try to interpret these mechanistically using a metric called B-sub-L of convective buoyancy, and that does a pretty good job of capturing that overall behavior. And then finally, somewhat more speculative, we link these buoyancy changes themselves to shifts in synoptic monsoon low pressure system tracks. Okay, so the left panel here is just repeating that JJS mean climatology map that you saw before. And now the right panel is at each point the correlation coefficient between a metric of extreme rainfall called the cutoff. This is from a literature spearheaded by David Nealon's group against Nino 3.4. So blue values are positive, meaning that the extremes, as it's signified by the cutoff, are more prevalent in the El Nino summers compared to more La Nina conditions. And you see blue positive values over much of central India and much of the southwest Western Ghats band. And conversely, we see decreases, drier, less extremes in the southeast as well as the northwest. The black contours enclose regions that are individually statistically significant based on a field significance test. And if you compare the two panels, you see the broad correspondence. The climatologically wet areas are where the extremes go up with El Nino, and the climatologically dry ones, the opposite. Given this spatial consistency within the subregions, we define, you can see overlaid on the left here, these CMZ, Western Ghats, WG, and Southeast India, SEI domains, as well as the whole monsoonal India domain on the right. Given this spatial homogeneity within the regions, we create aggregate statistics of the extremes for each one. The left panel here I'm showing is just the daily rainfall PDF for each of these four regions in a log scale. And I want to use that to identify this cutoff metric. Okay, so we have this sort of shallow power law from low to moderate rain rates in each region, and then this sharper exponential decrease in probabilities as you get to the extreme accumulations. This is a hallmark of quasi-daily timescale daily rainfall distributions. The circles here signify the cutoff. The cutoff is simply that sort of transition point between the weaker and heavier rain regimes. And this is for all years on the left. The right now is this cutoff value for each region. So all monsoonal India, central monsoon zone, Western Ghats, Southeast India, going left to right. Now composited just for El Nino years in red, La Nina in blue, or all years in gray. And what you see is that for the full domain, for the central monsoon zone, for the Western Ghats region, The El Nino composite cutoffs are larger than the corresponding La Nina, so extremes are enhanced, and it's the opposite in the drier southeast. The other symbols here, so the dashed lines on the left and the open circles on the right, we've repeated all of the analyses using the IMD's 1 by 1 degree data set, in addition to its quarter degree data set, and all of the take-home results are consistent there. I should also say, some folks, the cutoff isn't quite as prevalent as, say, exceedance counts or daily max, block maximum, other more conventional metrics of extremes. Anyway, we've tried to be very careful about looking at all of the different plausible metrics of extremes, and they all tell a consistent story. So we don't think there's anything methodologically sensitive here for the big picture stuff. Now we'll look over the full daily rainfall distribution. And to do that, we'll look at risk ratio plots. So the risk ratio is simply the empirical probability of exceeding a given rain intensity in the El Nino years. And then you divide that by the same probability of exceedance in the La Nina years. So I've done that here for each of these 4 regions, going from 1 millimeter per day all the way up to 300 millimeters. And if you're above this 0 line, that means it's more likely an El Nino summer. And if you're below, it's less likely. And the thicker shading of the lines is where it is statistically significant based on a permutation test. In all of the regions at the low to moderate rain rates, you have decreased probability, right? So consistent with intuition and published literature about ENSO, El Nino summers, you get less of these moderate events. In the southeast, that continues all the way to quite extreme events. But in the whole domain and the 2 wet subregions, you actually get significant increases in these very heavy events, right? And that uptick begins roughly around the climatological cutoff, which is these little vertical bars. So that's sort of a hallmark of an increase in the cutoff rain rate. And quantitatively, for the central monsoon zone, for example, at these very high values, this is something like a 60% increase. And for the domain as a whole, up to exceeding 40% increase, El Nino compared to La Nina. Okay, so now we want to understand how this is happening. And as I mentioned, we're going to use this B sub L convective buoyancy metric. This was introduced by Fayez Ahmed et al. In a 2020 paper in Journal of Climate. This is a metric of convective buoyancy of the lower troposphere, and it is the sum of 2 terms. The first is simply an undilute buoyancy of a subcloud layer relative to a lower free tropospheric layer. So you can think of that just sort of as a gravitational instability. And the second term, it incorporates the diluting effect of subsaturated air in the lower free troposphere. So you can think of that just as like a moisture contribution for shorthand. This curve, this plot is showing rainfall mean conditioned for each of the 4 regions, conditioned on this buoyancy metric. So going from the lowest values all the way to the largest. And you see this hallmark sort of kinked curve where there's essentially no mean rainfall at very low buoyancy values, and then this really sharp uptick once you get towards positive buoyancy. And that location where the rainfall goes way up is right around, in the dotted now are the PDFs of the buoyancy itself. And you can see once you hit that kink, then the buoyancy gets rapidly consumed and the rainfall goes rapidly up. Okay, these relationships between rainfall and buoyancy occur not just for on a conditional mean basis, but also on conditional quantiles. So this is now just the all monsoonal India domain, and the 10th percentile all the way up to the 99th percentile conditional quantile, you have this sharp pickup. And you also have a very similar story as a function of ENSO. So it's probably hard to see the red underneath the gray and the blue. These are El Nino or all year or La Nina composites. And that's sort of the point. This relationship between the convective buoyancy and the rainfall is not strongly ENSO dependent, which means that we can then use the changes in the buoyancy itself under ENSO to better understand what the rainfall extremes are doing. So the more extreme convective buoyancy days we get, for example, in a particular location, then we would expect there to be more extreme rainfall days in that location. And that is largely what we see. So on the right-hand side, I'm showing, again, the cutoff rain rate versus Nino 3.4. This is our measure of extremes. And now on the left, I'm showing you the correlation between the rainy day 99th percentile full convective buoyancy value in a given summer against that summer's Nino 3.4. And again, the black contours encircle statistically significant areas. So there are, over much of this sort of central sort of core monsoon zone, we see positive values for the buoyancy, consistent with the extreme rainfall there. And the decreases in the high percentile buoyancy in the southeast and the northwest, consistent with the decreases in those regions. It isn't perfect. The extreme rainfall values, excuse me, are more positive overall, but we feel that this is a useful mechanistic starting point. And when we consider the two individual terms of this buoyancy metric, the undilute instability and the lower free tropospheric subsaturation, we see that both largely contribute in concert to the overall picture. So in the central India region, both your gravitational instability and your very nearly saturated days increase with El Nino, and the opposite signals from the southeast and northwest. The Western Ghats coastal band in the southwest is a little more complicated. There's not a moisture signal at all. In fact, it's strongly inhibiting this decrease in especially moist days. However, that's more than compensated for by this increase in gravitationally unstable days there. Okay, the last part is this connection to low pressure systems that I mentioned. This is sort of a busy plot, but apologies. Let me walk you through it. The black contours are simply the climatology of low pressure system track density. And you see those maximize just inland from the northern Bay of Bengal. And the tracks are mostly to the west and northwest, sort of from there. The shaded contours are the ENSO composites, El Nino minus La Nina, of these low pressure system day metric of the tracks. What you see is the browns in southern Bay of Bengal through sort of the peninsular India and in the northwest mean less LPS days in El Nino summers. The greens and blues in the sort of eastern northern India signify an increase in the number of LPS days and tracks in El Nino minus La Nina. The overlaid circles are the corresponding extreme rainfall events associated with LPS events. So this is work by Yuja Yu. If there's a LPS event within a certain radius of an extreme rainfall event, she considers it LPS related. And the blue circles mean increase with El Nino, red mean decrease with La Nina, excuse me, with El Nino. And you can see overall correspondence with the extreme rainfall maps we saw, right? And perhaps least of all for the Western Ghats, but the southeast, you get less LPS extreme rainfall, the northwest likewise, whereas in the sort of central, eastern, domain, you get these increases. What in turn is causing these LPS track shifts is totally up in the air. Actually, we're exploring that now in a manuscript in preparation. But the take home there.
Sorry to disturb you.
Yes.
So you have to summarize the talk.
Oh, sure, no problem.
15
Sorry,
minutes is-
I may have lost track of time. Yeah, this is the last results. This is the last slide, in fact. It is possible that the buoyancy signal we saw was actually the sort of more in the tail, not the dog, that it's more driven by the synoptic scale dynamic events. But regardless, it's a very strong result that we have this increase in the wet regions of monsoonal India in the extreme rainfall in El Nino summers, despite the mean drying. Okay, I very apologize for losing track of time, and thank you very much.
It's okay. It's very interesting talk actually. Due to lack of time, we cannot entertain any questions now. So if anybody is interested, just drop a mail to him. And to coming to the next and the last talk of the session is by Hari Krishnan. He will be presenting about the study of heavy rainfall events over Mumbai.
Good evening, all of you, respected dignitaries and my colleagues and my friends. Good evening. Thanks for giving this slot. My talk is postponing since morning, since like morning tea break, lunch break, and now also one more break. I'm taking your time. Sorry for that. I will complete as soon as possible. So I'm Hari Krishna Devshetty, working as scientist B at IITM under Dr. G. Pandit Rai sir. So today I'm going to present a study of heavy rainfall over Mumbai region using X-band radar network and mesonate rain gauge observations and simulations of WRF model. So these are some co-authors. Yeah. This is the outline of my presentation: introduction, data and methodology, and results and discussions, conclusion, and future scope of work. And introduction. Extreme rainfall challenges in urban areas like nowadays it is means urban cities like Mumbai, it is exaggerating like floods, and it is necessitating that it is means accurate rainfall and weather monitoring is required for any urban cities like Mumbai. So what is the role of radar observations in these urban cities? So radar observations will give high temporal and high resolution real-time data. So these are means very important observations to predict means nowcasting any means predict nowcasting means any weather events, extreme weather events or any city like. And one more significance of X-band radars. So X-band radars is highly sensitive, means it is like accuracy is more, means it is like 9.5 gigahertz frequency range. It is accurate, means we can predict the means any weather events like over cities, and it is like so it is very useful for localized convective storms and prediction like that. So Mumbai first urban radar network, this is IITM initiative like under art project. So we have installed 4 X-band radar network over Mumbai that spatially 30 kilometers distance. And recently inaugurated, means as Dr. G. Pandit Rai sir already morning he spoken about that. And September 2024, we have inaugurated this radar over Mumbai. And Yeah. And this WRF model simulations also we have conducted how in one case we have taken September 2024 only, we have heavy rainfall happened over Mumbai region. So we have simulated the some simulations, how it is looking some that same case. And data and methodology. So what are the different means in this study, we have utilized some different types of instruments like X-band radar network. So here we can see there are means how X-band radar installations is going on, and Mesonet rain gauge network also we have installed around in city 137 rain gauges we have installed. It is coming real-time data. So every 15 minutes update accumulation rainfall we will get with this sensor. And the digitometer data also we have used. This is also precipitation measurement sensor. And lightning network also we have IITM's lightning location network we have. So we have installed different places. So we'll get to know that wherever it is happening, thunderstorm events like lightning, how it is happening. So how much lightning activity is related to means with rainfall, we can get to know this. So these are the some data sets we have used. Are apart from that, ERA 5 reanalysis data also we have utilized in this study, and satellite data like GPM, U, METSAT, brightness, temperatures, and rainfall information we have utilized. So Mumbai's first radar network, it is as I previously talked, means September 14, 2024, it is inaugurated IITM's first urban radar network over Mumbai. So these are the some glimpses of that day. Means it is formally inaugurated by Secretary MOS. Yeah, and the technical specifications and topography of X-band radar and topography of the study region. This is the 4 X-band radars like Amity University and DJ Sangvi and VSET and KDMC. Different means 4 places we have installed our X-band radars. So this is the Mumbai topography, and it is near to Western Ghats region. It will start. So these are the different frequencies, 4 center frequencies of our X-band 4 radars. And see, as I told, means 139 means rainfall, rain gauges also we have installed across the city. And there is like mosaic image, mosaic product that is called multi-radar and multi-sensor integration for total coverage. That is first time we are doing for using 4 radars in India. Means it is already doing by Nexerad S-band radars by Oklahoma University and NOVA. They are making their around 80 or 100 radars they are utilizing, and they are making mosaic image products. So same way we have trying with our Mumbai 4 radars compromising, and we are making that means mosaic images at 2 kilometers above mean sea level. Yeah. And the importance of urban radar network, why it is required? Why means we have one single radar cannot see, means it is not suitable, not it is means why? Because like urban cities like huge buildings and skyscrapers, it will be objected by radar beam, it can't cover. So that's why it is very important to cover the our spatial coverage of rainfall information real time. That is very important. That's why we are installed 4 radars. So you can see again one more thing, it is very difficult to find a site, radar site to install like Mumbai stations, like Mumbai city is very difficult. Even our teammates like Dr. Subrata sir, Sachin sir, and Pandit Rai sir, it is lot of efforts and it is tireless efforts. Like that's why we got these minimal blockages of 4 sites we have identified and we have installed. So by this mosaic product can give this about 2 kilometers height, means spatially you can see this left side reflectivity images at spatially, means without any blockage. If one radar is there, we can't see anything like lower level clouds, upper level clouds only we can see. So that's why this is very important for urban radar network or like developing cities, like metropolitan cities. So apart from that, we have means as I told, WRF modulation simulations also we have conducted for the same case study. So these are the initial configurations we have utilized. Like there are vertical resolutions, 40 vertical levels we have utilized, and horizontal resolutions like 4 nested domains we have utilized 27, 9, 3, 1 kilometer horizontal resolutions like microphysics, Kessler. These are the advanced microphysics we have utilized in this study. This is the, we thought, best microphysics and means configurations of this model to study this event. So this is the nested domain we have utilized 1:3 nested domains, like as I told. So this is the D04 is our study domain. So why we have taken 4 domains means we want to see allow and means all large scale features in our study domain. That's why we have taken like 4 domains in this study region. So results and discussions, as I told you, that 25th September 2024, it is huge rainfall over Mumbai region. Around 232 rainfall happened. That is like a flood kind of situation that day. So how we can see with compromising 4 radars like composite pictures, it is we can see in this. But this radar can cover up to 120 kilometers range. But after beyond 120 kilometers, what happening? Why it is rainfall happening? Means we want to see. That's why we have taken this brightness temperature of IWM8 set data, and this we have generated. Just I will show you that video. Yeah. So this is what happened that day. Means the 23 to 26. This is during this event. Means all over India that is happening. Some distributed rainfall happening due to this low pressure system. After seeing this image, brightness temperature of IWM8 set, we came to know that there is a low pressure system like all over India. Means as last speaker, as Spencer, Dr. Spencer has told, it is over Bay of Bengal, means near Kolkata region is low, more LPS occurrence is happening. So due to this, there is distributed rainfall over happening, means all over India. We have captured and we are studied in this. Yeah. And means we want to see this low pressure system by using ERA5 reanalysis data, and also and we have generated these same simulations with WRF model with different dates 23 to 26. It is well matched with means ERA5 reanalysis and WRF simulations. It is showing similar low pressure systems, and it is first initially it is generated means over Bay of Bengal, and it is moving towards west coast, our study region. So due to this only it is like, sorry. Due to this LPS only over India, there are distributed rainfall happening, and we this means ERA5 and ARW simulations 23 to 26 we have generated in this region. So now mosaic product means we have as I told, NextRad radars, they are generating polarimetric data also, means by using different data sets. So same way we want to generate a mosaic product, means as OEM of X-band radars, they told that they can generate only reflectivity. They can't generate mosaic of polarimetric data. So on our own, our team is developing our own code like to analyze polarimetric data. Polarimetric, why? Because it is means we can study microphysics and macrophysics of clouds or any convective storms. It is very useful for means polarimetric variables like ZDR, means correlation coefficient, differential phase 5dB. These are the different polarimetric variables we can get it from dual polarization Doppler weather radar. So we are generating those polarimetric successfully, and it is almost it is matching. And it is fine tuning of Python code. We are fine tuning of these polarimetric parameters also. These results are first means mosaic products for Indian region. Nobody means not done till now, means by using 4 radars. This is first mosaic product for Indian regions. So spatially means Mesonet rain gauge network, we have installed 139 stations. So spatially how it is distributed rainfall. So that we want to study. So you can see 23 and 24, 25, 26 rainfall distribution, how it is moving. First initially it is started land, means it is moving from like northeast region to means west coast. We can see here 24th it is happening, some rainfall happening. It is detected by our rain gauge network, and 25th is heavy rainfall. It is moving land to ocean. Means this low pressure system. It is happening. More rainfall happened here. So this is spatial, and this is line plot. Also, we have means taken over 97 stations. Also, we have taken GPM rainfall, spatially averaged over Mumbai region. So how it is looks like, it is matching with groundfall rain or not. We want to study. That's why we have means analyze. It is pattern is similarly matching, but a little lag will be there. Why? Because GPM can see top of the clouds, and groundfall measurement is we can see our rain gauge network. So both are well matched. Means GPM and groundfall means observations. So lightning distribution also over the study we want to study, means we have ILL and sensor. So we as I told, so these are the distribution of a lightning sensor, means lightning activity over that period during that study. So this is line plot. Same, it is similarly matching with rainfall observations. So you can see here 125th 232 mm rainfall happened. It is corresponding 11,471 lightning strikes happened that day. So that is huge rainfall, means huge lightning strikes also we have observed. Means this is like multi-sensor, multi-radar observations for the Mumbai region, but we using with WRF simulations like. So like rainfall distribution also we have utilized, means simulated GPM and RFI and WRF simulations. WRF simulations, it is well matched with zonal wind and zonal directions, but it is mismatched with means with advanced physics we have simulated, but it is intensity is matching, but spatially it is not matching. So we can see ERA5 and GPM is well matched. Means observations and satellite, means ERA5 reanalysis data and GPM satellite data, it is matching, means rainfall distribution. But WRF model, it is little underestimated. So that find out means that we have noticed in this study.
How many more slides are there?
Sir, 2 slides, sir.
Okay.
Yeah. That low pressure system, due to this, we have installed a disrometer network also. Dr. Kaustav sir has means already talked about IndiaPix. So in this low pressure means LPS system, how distributed means over Indian region, how rainfall is distributed. So we have analyzed that data also. So there are like Port Blair, Kolkata, means RC, means Bhopal, and Pune, and HSCPL, Mahabaleshwar, and Gumbe. And these are the means due to this, the LPS system contributed over rainfall different cities, like different overall station. So maximum means 24th Agumbe is like Western Ghats region, and HSCPL is Western Ghats region. Due to this Western Ghat orographic, there are huge rainfall happened. Means we have means we have observed in this study. So this is conclusion. So multi-radar urban network effectively eliminates the blind spots caused by the skyscrapers, improving accuracy of rainfall monitoring and nowcasting densely populated cities like Mumbai. This analysis September to 26, like rainfall exceeding 200 meter per hour, and 11,400 means lightning strikes also observed in this study. And this LPS contributing widespread of heavy rainfall across this region, and WRF ARW simulations aligned with zonal winds, as I spoke already. But there is some little mismatch between GPM and ARA5 rainfall data. This is the future scope of means work. We want to study why this means WRF model simulations are not means there is a mismatch. We want to study that parameterization and model configuration to identify the causes. So what is the reasons behind means why it is not means getting exact rainfall by comparing GPM and RFI. So real-time observations, data assimilation also we want to means pipeline in this work. We want to assimilate the data, real-time data X-band radar. So under macro and micro physical characteristics by using X-band radar mosaic polarimetric products. We want to study that also in this feature. So acknowledgement, I would like to express my sincere gratitude to our director IITM, Dr. R. Krishnan sir, and my project director, Dr. G. Pandit Rai sir. Continuous support in this means fostering scientific research, and their guidance is invaluable. So I also extend my appreciation, like our group, Radar and Satellite Meteorology Group and Mesonet Group. So I want to thank, and IWM8 organizers and LOC greatly acknowledged. Finally, sir, completed.
Thank you. Thank you, Hari.
Yeah.
Any questions to Hari? Anyway, everybody is now tired. So they will talk to you during tea break. Thank you.
Yes.
Let us thank all the speakers for excellent presentations. And with this session is concluded.
I would like to sincerely thank our session chair for leading this session. I request Dr. Nico Caltabiano to present a memento to Dr. Surya sir as a token of appreciation. With that, let's proceed to the poster session accompanied by tea and coffee on the first floor of the Rijuranga complex, same as yesterday. Enjoy the session and refreshment. Thank you.